Well, hello, dear friends. So in this lesson, we're going to examine the answers to these questions. What is machine learning? What are some of the terms used in machine learning? But alas, before we go digging into the details of machine learning, we're going to go through a bit of a history lesson. All right? So we'll get started. Machine learning. It sounds like it's a relatively new concept, but it was defined way back in 1959 by Arthur Samuel. By definition, machine learning is the workspace that gives computers the ability to learn without being programmed openly. Professor Samuel was an employee of artificial intelligence at IBM, and he developed a program that could play chess better than a person. Now, artificial intelligence, which became especially popular by the 1980s, continued to be developed to make reliable predictions in more specific areas after it was seen to be successful in certain other areas. So basically, machine learning was developed in the 2000s. So this system, which can interact naturally with people as part of cognitive science, it's gained the ability to find solutions to complex problems thanks to its ability to predict. Yes, my dear friends, let's get into some of the details now. So what is machine learning? Machine learning is a data analytics technique, getting computers to learn and also act like a human. Machine learning algorithms use computational methods to learn by feeding data and information. And it also is known as a field of data analytics to make predictions depending on trends and insights into the data. Machine learning algorithms use statistical tools to find important connections in large amounts of data. Now, the data we're talking about here covers many things like numbers, words, images, as well as clicks. So if this data can be stored digitally, it can be fed into a machine learning algorithm. So in short, the main basis of machine learning is to create algorithms that can process its data and predict the result using statistical analysis. The new data obtained during this process continues to be learned and used to update and become better with its results. Machine learning, which can analyze data without any human intervention, it offers the best estimates, and it's also used in many corporate applications. But by the same token, it also helps many professions with the opportunities it'll provide. Machine learning is becoming an increasingly needed application in today's world, with its functions like ease of data analysis and giving the top estimates, defining abnormalities, and solving problems. Machine learning algorithms are used in an extensive variety of applications, such as recommendation engines, customer churn, new pricing models, email spam filtering, pattern and image recognition, predictive inventory planning, purchasing trends, credit scoring, and sure, the list could go on. So in this lesson, gave you a little bit of an introduction. We've learned what machine learning is and how it can be used, where it is used typically. So we're going to take a brief pause here and we'll come back into the next lesson. Well, hello, dear friends. So in this lesson, we're going to examine the terminology of machine learning used in the machine learning world and consequently the upcoming lessons throughout this course. All right, so let's get started. Observations. So observations is a piece of data used to learn for the model. Each row in a data set represents an observation. For example, each email could be an observation. Features. Features represents a measurable piece of data that can be used for analysis. For example, name, age, gender, size, fare, date, etc. Features are also sometimes referred to as variables or attributes. Each column, except the label column in a data set, is called a feature. Labels. Now, the label, it's often called the target column. This is the thing we're predicting. So briefly, the features are input and the label or target is the output. For example, churn, spam or not spam, price of a house, this kind of thing. All right, so this picture here demonstrates a very simple data set. So in this data set, each row is an observation. Name, age, gender columns are the features of the data. And here's the churn column. This contains the labels of the data. Now, what about the training and test data? Training data is a subset of the full data set to train a model. Test data is a subset of the full data set to test a model. So to summarize, our data is divided into two: training data and testing data. Then we use our training data to train our model. All right, so now it's time to test the model. And yes, indeed, we have tested our data according to the trained model. So then the next step would be evaluate the accuracy of the result that we have achieved. Now, since we haven't learned the metrics, we're going to end the lesson here. All right, dear friends, so in this lesson, we've talked about machine learning and the terms that we've used in machine learning. I hope to see you in the next lesson. Until then, have a nice day. Hello, dear friends. In this lesson, we're going to try to install Anaconda distribution for Windows. So let's get started. Now, you may encounter throughout your life more than one way to use Python programming language. That's a good thing, right? You should always have options. In this particular course, we're going to examine the Anaconda IDE and Jupyter Notebook and Jupyter Lab. And that's all within the IDE. So, of course, you might be saying, what is IDE? Well, IDE are tools that combine different programming languages that programmers can use when writing computer programs. Now, later on in the lesson, you're going to have a much deeper understanding of what I mean as we're using Anaconda. But the interface is just the intermediary applications that allow us to use a programming language directly in the IDE. We will be able to use Jupyter Notebook and the Jupyter Lab interface from within the Anaconda distribution. Therefore, we will first download Anaconda, then we will finalize the installation process by activating the Jupyter Notebook and Jupyter Lab that's waiting for us, just chomping at the bit. It's ready and waiting in Anaconda. Okay, so let's get started without wasting any more time. Our first job will be to open our internet browser, and I'll just use Google Chrome. So I'll click yes, my browser opens. Now I'm typing Anaconda in my browser to download Anaconda. So when you hit the enter key, Anaconda.com comes up. It is the world's most popular data science platform after all. So just by clicking on this link, we can enter Anaconda's site. And that'll take you to a screen like this. Now we need to find the download option for Anaconda. And actually, here's a Get Started section up here at the top right. So let's click it. Now, there's a few different options about Anaconda service products. So just click on the Download Anaconda Installer option. See, so after clicking, this is the screen that you got. And here we've got to choose according to our operating system. Now, if you don't happen to know what operating system you're running or the version of it, we can always find out what system version we're running just by saying Show Processor Information from the Start menu, usually 64-bit. Now, since my computer is 64-bit, we'll click on 64-bit from the Windows section and perform the download. All right, so that starts the download process. So here we are waiting. And that'll complete the download. All right, so now let's go to the downloads to continue the installation process through that file that you downloaded. So we can enlarge the screen. All right, so we're running the setup file that we downloaded from here. So let me just get this down. And let's see, now we will need to apply a few actions. So first of all, statements about the contract. And I'll just click on agree. So in other words, we'll accept. And let's continue. So it asks, who are you establishing it for? It's just going to be me. So you will also be me. Well, no, you won't be me, but all right, just click it. Anyway, let's continue. Here is a directory and a file path. So it's more logical to use a directory given here, and I really do recommend you not to change it. Now, when we say next in advanced settings, two options are presented to us. But you know what? That's not going to be that much of a head scratcher. Don't worry about the first option. Second option just refers to the predefined Python version when using Anaconda. So for the latest installation, we call install. See, the installation process starts, and we'll wait for a bit depending on your computer and my computer, actually. It might take a little while longer. So I'll just say next. Now, here we are presented with an IDE called PyCharm Pro. So remember, I asked you earlier, what does IDE mean? Well, it calls interfaces that makes our work easier when using programming languages. So here we will use Jupyter Notebook and Jupyter Lab. Now these are also located in Anaconda, not PyCharm Pro, even though it's offering us this addition. Now, we are just going to be looking at data science and artificial intelligence. So that means that we will be doing this interactively. So we choose to work with Jupyter Notebook and Jupyter Lab interfaces that also happen to be within Anaconda. So we will click Next and complete the installation just by clicking Finish. Cool. So after completing the installation, it'll direct us to a web page like this. Now, we don't need to do anything here, so we can just close these pages. But now we can go ahead and see how we can access Anaconda that we've installed. There are various ways for this. I'm going to show you the most difficult, and I will explain the other. So right now, just open any folder. I'm going to enlarge the screen to make it look a little larger. Anyway, it'll be more clear for you to focus. So see here the section on the left that shows us the file paths. I'll click on this computer and type Anaconda in the search section. So here we're going to try to find Anaconda Navigator. Then we click on it, and our Anaconda is, it's waking up like it's becoming active, and now we're just waiting for it to open fully. Cool. So now the Anaconda Navigator is open. You can see this IDE and interfaces, that there are more than one interface, yeah? So there is data lore. There are interfaces such as Jupyter Lab and Jupyter Spider and Jupyter Notebook. Now, we're pretty much going to be sticking to Jupyter Notebook and Jupyter Lab, but it's always good to know what else is going on, right? Now, let's look at some of the other services of Anaconda. This is the environment part, and this is the place where the installation of modules and library institutions will be done. There's also learning and community sections. There's always documents and learning section that you can look at later, of course, not while I'm here. Also some variety of events and news in the community section if you're interested. But now we're going to go back home and run our Jupyter Notebook. So let me show you this. If we just hover over Jupyter Notebook and click Launch, that's going to direct us to the interface. All right, so once our interface is open, we will be able to continue our work with Python programming language over here. So you can also try the same interface opening process with Jupyter Lab. But I do want to explain a little bit about how we can access these interfaces in a different way, and it might be more easy for you later. I don't know. We'll see. Anyway, you can enter the Start menu, write Anaconda Navi. Now, in order not to write it every time, we'll just pin it to the taskbar. So that it'll come in here, and again, we'll go to Start for Jupyter Notebook, our interface that we will use most frequently, and look at that, it's now in the taskbar. So let's close all the tabs and try to open our interfaces again, and sure enough, they close, and when we press the Anaconda icon, you see how it all works. So we'll wait for it to open. Okay, cool. So now our main screen has arrived. We can choose what we want to from here, as I've explained above. All right, so let's click on Jupyter Notebook icon, and we're going to start to use it. You see how that opens? Very cool. So that's it. We've learned how to install the Anaconda distributor on Windows and how we can open this distributor and activate our interfaces within it. So in the next lesson, we're going to examine the Jupyter Notebook. All right, so I hope to see you then. Until then, have a nice day. Well, hello, my dear friends. In this lesson, we will install Anaconda distribution system for Mac OS. So let's get started. Can't wait to get started, so let's just get to it. Our first job, of course, will be to open your favorite internet browser. I'm just using Google Chrome here, so I'll click yes. My browser opens. So now I'm typing Anaconda into my browser to download Anaconda. And when you say enter, there's an expression such as anaconda.com. That happens to be the world's most popular data science platform. So just by clicking here, we enter Anaconda's site. So next we come across a screen like this. So we'll need to navigate to the download option of Anaconda. And here, what do you think? There's a Get Started section right here on the top. So let's click it and find out what happens. And of course, there are options about your Anaconda service products. And we'll click on Download Anaconda Installer option. See, so after clicking, the following screen shows up. Here we have to choose according to our operating system. If we don't happen to know what our operating system is, well, you can always find out what the operating system type is by saying Show Processor Information from the Start menu. So we'll click on a 64-bit graphic installer from macOS section and perform the download. So see, the download process starts, and while we wait, the download. Let's see. So now we will need to apply a few actions. First of all, we'll click Continue. And if we do that, we can give permissions to the package installation. And let's continue. On this screen, Anaconda Installer will try to guide us through our installation journey. So just click Continue again. Now here, the Anaconda Installer gives us some important information. That's a guideline for the installation process, like change install location. But I tend to keep things by default, so let's click Continue again. And here are the statements about the contract. So we'll agree to that, and we will accept. So let's continue. It asks for whom it will be established. Just say me, and that's it. just me. All right, so we can continue from here. We'll get a directory and a file path. Now, it's probably more logical to use a directory given here. I'll say it. I'll commit to this idea that I do not recommend that you change this place. Now, for the latest installation, we just call install and see the installation process has started. So here we can wait depending upon the computer and the speed and the internet access. Of course, you might be waiting for a little while, but here we are done and we are presented with an IDE called PyCharm Pro. So again, it begs the question, what does IDE mean? Well, it's called an interface to make our work easier when using programming languages, right? Here, like I told you in the beginning, we're going to be using Jupyter Notebook and Jupyter Lab. These are also located in Anaconda. We're not going to use PyCharm Pro. And of course, Anaconda offers this in addition to anything else that we want. But we pretty much consider the Python programming language in terms of data science and artificial intelligence and teach it with a mutual interaction with you. So we'll be working with Jupyter Notebook and Jupyter Lab interfaces that Anaconda also offers us. All right. So we therefore can click continue, and that way it'll complete the installation just by clicking close. Now there is one more step here. After our installation is complete, we can delete or keep the Anaconda installer files. That's entirely up to you. I'll just move it to the trash. So now let's see how we can access the Anaconda that we just installed. So I'll open Applications, find Anaconda. And when you click this, Anaconda becomes active, and we'll just wait for it to open fully. So look here, the Anaconda Navigator opens, and look, you see this IDE and interfaces. There's more than just one interface, huh? There's data lore. There are interfaces such as Jupyter Lab, Jupyter Notebook, and Spider. We will be using one of the Jupyter Notebooks and one of the Jupyter Lab interfaces. So again, we can go to the Start for Jupyter Notebook and our interface that we will use most frequently. And there it is in our taskbar. Yeah, so that's it. We have learned how to install the Anaconda distributor on Mac OS and how we can open this distributor and activate our interfaces within it. So that's cool. In the next lesson, we will examine the Jupyter Notebook. So see you in the next lesson. Until then, have a really nice day. Hello, dear friends. In this lesson, we're going to try to install Anaconda distribution for Windows. So let's get started. Now, you may encounter throughout your life more than one way to use Python programming language. That's a good thing, right? You should always have options. In this particular course, we're going to examine the Anaconda IDE and Jupyter Notebook and Jupyter Lab. And that's all within the IDE. So, of course, you might be saying, what is IDE? Well, IDE are tools that combine different programming languages that programmers can use when writing computer programs. Now, later on in the lesson, you're going to have a much deeper understanding of what I mean as we're using Anaconda. But the interface is just the intermediary applications that allow us to use a programming language directly in the IDE. We will be able to use Jupyter Notebook and the Jupyter Lab interface from within the Anaconda distribution. Therefore, we will first download Anaconda, then we will finalize the installation process by activating the Jupyter Notebook and Jupyter Lab that's waiting for us, just chomping at the bit. It's ready and waiting in Anaconda. Okay, so let's get started without wasting any more time. Our first job will be to open our internet browser, and I'll just use Google Chrome. So I'll click yes, my browser opens. Now I'm typing Anaconda in my browser to download Anaconda. So when you hit the enter key, Anaconda.com comes up. It is the world's most popular data science platform after all. So just by clicking on this link, we can enter Anaconda's site. And that'll take you to a screen like this. Now we need to find the download option for Anaconda. And actually, here's a Get Started section up here at the top right. So let's click it. Now, there's a few different options about Anaconda service products. So just click on the Download Anaconda Installer option. See, so after clicking, this is the screen that you got. And here we've got to choose according to our operating system. Now, if you don't happen to know what operating system you're running or the version of it, we can always find out what system version we're running just by saying Show Processor Information from the Start menu, usually 64-bit. Now, since my computer is 64-bit, we'll click on 64-bit from the Windows section and perform the download. All right, so that starts the download process. So here we are waiting, and that'll complete the download. All right, so now let's go to the downloads to continue the installation process through that file that you downloaded. So we can enlarge the screen. All right, so we're running the setup file that we downloaded from here. So let me just get this down. And let's see, now we will need to apply a few actions. So first of all, statements about the contract, and I'll just click on agree. So in other words, we'll accept, and let's continue. So it asks, who are you establishing it for? It's just going to be me. So you will also be me. Well, no, you won't be me, but all right, just click it. Anyway, let's continue. Here is a directory and a file path. So it's more logical to use a directory given here, and I really do recommend you not to change it. Now, when we say next in advanced settings, two options are presented to us. But you know what? That's not going to be that much of a head scratcher. Don't worry about the first option. Second option just refers to the predefined Python version when using Anaconda. So for the latest installation, we call install. See, the installation process starts, and we'll wait for a bit depending on your computer and my computer, actually. It might take a little while longer. So I'll just say next. Now, here we are presented with an IDE called PyCharm Pro. So remember, I asked you earlier, what does IDE mean? Well, it calls interfaces that makes our work easier when using programming languages. So here we will use Jupyter Notebook and Jupyter Lab. Now, these are also located in Anaconda, not PyCharm Pro, even though it's offering us this addition. Now, we are just going to be looking at data science and artificial intelligence. So that means that we will be doing this interactively. So we choose to work with Jupyter Notebook and Jupyter Lab interfaces that also happen to be within Anaconda. So we will click Next and complete the installation just by clicking Finish. Cool. So after completing the installation, it'll direct us to a web page like this. Now, we don't need to do anything here, so we can just close these pages. But now we can go ahead and see how we can access Anaconda that we've installed. There are various ways for this. I'm going to show you the most difficult, and I will explain the other. So right now, just open any folder. I'm going to enlarge the screen to make it look a little larger. Anyway, it'll be more clear for you to focus. So see here the section on the left that shows us the file paths. I'll click on this computer and type Anaconda in the search section. So here we're going to try to find Anaconda Navigator. Then we click on it, and our Anaconda is, whoa, it's waking up like it's becoming active, and now we're just waiting for it to open fully. Cool, so now the Anaconda Navigator is open. You can see this IDE and interfaces, that there are more than one interface, yeah? So there is data lore, there are interfaces such as Jupyter Lab and Jupyter Spider and Jupyter Notebook. Now, we're pretty much going to be sticking to Jupyter Notebook and Jupyter Lab, but it's always good to know what else is going on, right? Now, let's look at some of the other services of Anaconda. This is the environment part, and this is the place where the installation of modules and library institutions will be done. There's also learning and community sections. There's always documents and learning section that you can look at later, of course, not while I'm here. Also some variety of events and news in the community section if you're interested. But now we're going to go back home and run our Jupyter Notebook. So let me show you this. If we just hover over Jupyter Notebook and click Launch, that's going to direct us to the interface. All right, so once our interface is open, we will be able to continue our work with Python programming language over here. So you can also try the same interface opening process with Jupyter Lab. But I do want to explain a little bit about how we can access these interfaces in a different way. And it might be more easy for you later. I don't know. We'll see. Anyway, you can enter the Start menu, write Anaconda Navi. Now, in order not to write it every time, we'll just pin it to the taskbar. So we are checking yes, so that it'll come in here. And again, we'll go to Start for Jupyter Notebook, our interface that we will use most frequently. And look at that, it's now in the taskbar. So let's close all the tabs and try to open our interfaces again. And sure enough, they close. And when we press the Anaconda icon, you see how it all works. So we'll wait for it to open. Okay, cool. So now our main screen has arrived. We can choose what we want to from here, as I've explained above. All right, so let's click on Jupyter Notebook icon, and we're going to start to use it. You see how that opens? Very cool. So that's it. We've learned how to install the Anaconda distributor on Windows and how we can open this distributor and activate our interfaces within it. So in the next lesson, we're going to examine the Jupyter Notebook. All right, so I hope to see you then. Until then, have a nice day. Hello, dear friends. So in this lesson, we're going to try to install Anaconda distribution system for Linux users. So let's get started. Now, depending on your experience, you may have encountered more than one way to use the Python programming language. But I just want to be clear that in our course, we will be looking at Anaconda IDE in the Jupyter Notebook and the Jupyter Lab interface in IDE. So what is IDE? Why would we be using it? Yeah, good question. So we can say that there are interfaces that programmers use when writing computer programs. And then by the end of the course, you'll be able to clearly understand what I mean about setting up Anaconda. So we'll be able to use this Jupyter Notebook and Jupyter Lab interface within our Anaconda distribution. So first of all, we will download Anaconda. We're going to finalize the installation process by activating Jupyter Notebook and Jupyter Lab, and that way they'll be waiting and ready for us to be using in Anaconda. So I just want to get started quickly. I'm here using Ubuntu as the operating system. Of course, Ubuntu is open source, free, and as a free operating system, it was actually developed based on a Linux kernel. So we'll fire up our internet browser, so I choose Firefox. And now we will need to write the name of our distributor that we want to download into our browser, and that will be Anaconda. And just look for anaconda.com, and you can use whatever sort of search phrase you like. But it is absolutely one of the most popular data science platforms out there. Anaconda site, and we'll come across a screen like this. And you see here, we'll need to go to the download option for Anaconda. All right, so here it is. My friends, look at this. There is a Getting Started section on the top right, so just click there. Now, there are a few options about Anaconda service products, so we can click on the Download Anaconda Installer option. And then see that after clicking, the following screen will come up. Here we have to choose according to our operating system. Now, we do want to install on Linux, and that's why I'll click the Bit Installer section under the Linux option. Cool, so now our browser asks what to do with the file. And here I'll just check the Save File option, say OK, and that begins to download. Okay, so now that our download has started, I just want to follow the process here. And the duration of the process, of course, depends on your computer and internet speed. But that's mine done, so I'll just click on the file. And so here we need to enter the downloads file. And yeah, see, here's where the file's been downloaded. And it is a file with the extension sh. Now, of course, because we are in Linux, unlike any other of the operating systems, we will have to run it on the command line. So in other words, we will run it on a terminal with the term Linux. So that way the installation process can be a little daunting for those who have not used Linux before, but that's why we are going to check it out, and we are going to do a step-by-step introduction by going to the Anaconda's website. So when you go to the site, see, so when I scroll down a bit, there's a section about documentation in here. You can always learn a bit more, and there's a Learn More option. Just click on that. And you see there is an installation option related to the installation. So we click here. And since we want to install it on Linux, we will need to click on the Installation on Linux option. So see here, we are now where we want to be. And if I scroll down a little bit more, there's some sequential information about the installation. There's a section about downloading Anaconda. Yeah, we already did that, so we've got the first step done. Now, the second step is, of course, related to validation, not necessarily our concern. So I want to bring your attention to the third step. This is what interests us. So there's a command example that we need to write into the terminal for installation. Now, here's something critical that we'll need to do before using this code. This is the same version as the version in the code and the version that we downloaded. So what do I mean by that? Well, I'll just make this page smaller. So open up a terminal where we'll write the code. So I'll right-click this terminal anywhere on the desktop and select Open Terminal. And now let's take the terminal down. So we'll do a version check. So we come to the downloads, see the file with the SH extension that I downloaded, 2021.05. So what is the version that I will write into the terminal? 2020.02. Well, then the first thing will be then to fix it. Yeah. All right, so I'm just right-clicking and copying this code written here for us to use, and I'll come to the terminal that I previously opened on the desktop and paste this code in. And sure enough, we are going to change the version. So let's see what our current version was, 2021.05. All right, cool. So that's why you check. I'll just delete 2020.02 from here and write 2021.05 instead. So see, it says here to continue the installation process, review the contract. So I'll say enter. Now, unlike any of the other operating systems, all contract-related clauses appear one by one in Linux. So I'll just try to finish the whole contract by pressing enter repeatedly. Okay, it looks like I pressed it a couple of times too many. Anyway, okay, so here we get a question, and it says, do you accept license terms? We got to say yes, so we'll write yes in here. So now it asks for the directory where Anaconda will be installed. Now, my advice, of course, is just don't make any changes in this series, my friends. Let's just perform the installation under this directory by saying enter. So now we'll hit enter, press it, and starts the installation. So the duration of this process, of course, depends on the computer and internet speed. So we'll just wait until the end of the process. So now it looks like it has installed all of our packages. And again, we've got another question to answer. Do you want the installer to start Anaconda 3? Well, let me think about it. Yes. So we write yes here. Installation completes. All right. Now, here we are presented with an IDE called PyCharm Pro. And remember, I asked you earlier, and you were probably thinking, are you just not going to answer? What does IDE mean? Well, it was called interfaces that make our work easier when using programming languages. So here we will use Jupyter Notebook, Jupyter Lab, which are also located in Anaconda, not this PyCharm Pro that Anaconda offers us in addition. Because, well, I'll be honest with you, we consider Python as a programming language in terms of data science and artificial intelligence, and we teach that with mutual interaction. But here we'll be using with Jupyter Notebook and Jupyter Lab interfaces that Anaconda will offer us. So therefore, we just don't want to go down that road. So that means right here we'll start Anaconda. And let's take this terminal down and come over here to our documentation page and examine the next steps. And I'll just enlarge the screen a little bit. So looky here, we have applied these steps. And last step, the 12th step, we are presented with an option to verify the installation. All right, so I'll just click here. Now look, here are some of the demos for Windows, for Mac, for Linux. Let's go here to the Linux part. And see, there is an article here. So it says, open Anaconda Navigator with Anaconda Navigator command. So if Anaconda is properly installed, the Anaconda Navigator will open, and it gives us a code to write to the new terminal. Then right-click and copy the code. Cool. So now we're going to close all of the terminal units that we have opened before. And let's get that down too. All right, my friends, now we'll open up a new terminal on the desktop and we'll paste the command that we copied in the documentation section, right? So this time when we run the code, it will start to open in our installation of Anaconda. So let's enter it. And you see, my friends, they are starting to open. So after that, you can open Anaconda with this command. All right, so it finally opens, and look at this. You can see all the interfaces in our Anaconda distribution. There is more than one interface, my friend. So this is data lore, and there are interfaces such as Jupyter Lab, Jupyter Notebook, Spider, and what we're going to do is use one of the Jupyter Notebook and Jupyter Lab interfaces. So we'll have a look at some of the other services of Anaconda. There is an environment part. So this is the place where the installation of modules and library institutions will be done. There are also learning and community sections, which are often lots of fun in your downtime. There are some documents in the learning section. There are various events and different news about the community in the community section. We won't be going into that at all here, but I don't want to dissuade you from doing that, my friend. So for now, we're going to go back to the home section and run our Jupyter Notebook and Jupyter Lab. So we'll start from Jupyter Notebook first. And sure enough, if we hover over it and click Launch, it will direct us to our interface. So that's pretty cool. And you see how our Jupyter Notebook opens with a new web tab interface. Now, since we will examine the Jupyter Notebook in detail in the next few sections, I'm only just going to open it here and show you how to do that. So next, we will open our Jupyter Lab. And here we are back to our Anaconda distributor. And I'll just hover over the Jupyter Lab and click Launch. And it's opening. All right, so this is yet another interface that we will use. And again, since we will examine Jupyter Lab in detail in the next sections, we will end the lesson here just by showing you how to open it. So just review or poke around a little bit, have a quick read of some of the documents, and we will see you in the next one. So that's it. We have learned how to install the Anaconda distributor on the Linux operating system. We can also open the distributor and activate our interfaces in it. So in the next lesson, we will examine the Jupyter Notebook itself. All right. So I hope to see you in the next lesson. Until then, have a great day. Hello, dear friends. So in this video, we're going to talk about Jupyter Notebook and Google Colab. Jupyter is a loose acronym meaning Julia, Python, and R. So these programming languages were the first target languages of this Jupyter application. But these days, notebook technology also supports many other languages. Jupyter Notebook is one of the most successful tools that we can use to keep our notes and calculations together. It's frequently used in repeatable research and data science. All right, so let's see how to use it. So when we first open Anaconda Navigator, we'll choose Jupyter Notebook and click Launch. And Jupyter will open up a web page. So now we'll create a folder and change the name to Python Lessons. First click New in the top right corner and choose Folder. Now we can rename our new folder here. Open up our new file and click New Python 3. Now open a blank page. So this page is our editor, and we can write our code, our notes. So why don't I write an example? Hello world. And press Shift and Enter at the same time. And that runs the code. So the result is shown in the outbox. Let's do another example. 3 plus 4. And run. And the result is, wait, is that right? It's 7. So as you can see, we can also make mathematical operations in Jupyter Notebook. All right? So we'll have a look at Google Colab. So Exploratory, or Colab for short, is a product from Google Research. Colab allows anybody to write and execute arbitrary Python code through the browser and is especially well suited to machine learning, data analysis, and education. But more technically, Colab is a hosted Jupyter Notebook service that requires no setup to use while providing free access to computing resources, including GPUs. Technically, Jupyter and Colab are the same thing, but there are some differences between them. So Jupyter is, of course, the open source project on which Colab is based. Colab allows you to use and share Jupyter Notebooks with others without having to download, install, or run anything. Colab notebooks are stored in Google Drive or can be loaded from GitHub. So let's have a look and see how to use it. So first up, we'll just open up our browser, type in Colab, click on the URL. Now on this page, you've got a Google account, you got to log in. If you don't, you're going to need to create one. So then after we log in, just click the File tab up here at the top right of the browser and select New Notebook, and our notebook is ready to use. So actually, we use Colab like Jupyter, so let's give it a shot. Let's do up an example. Hello world. And again, you can use Shift and Enter at the same time, and that runs the code. And the result is shown here. So let's do another example. 3 plus 4. See how it does complex mathematics? There's your result. Now, here's a very useful feature. You can change runtime types. So with the help of this feature, we can accelerate our processes. So when you start to develop machine learning projects, you're going to realize that speed is really important. And with the help of this feature, we can increase our speed. We're not going to get into that any deeper because that's it for now. We went over some of the basic things about Jupyter Notebook and Google Colab. So now I think we're ready to start some of these lessons in machine learning. All right, so I'll see you in the next lesson. Until then, have a nice day. Hello, dear friends. So in this lesson, we're going to learn the difference between classification and regression. So let's get started. Supervised learning is the most common type of machine learning because it is much easier to train a machine to learn with labeled data than with unlabeled data. So in other words, depending upon what we want to predict, supervised learning is used to solve two types of problems: regression and classification. So now let's consider them separately and start with classification first. So classification is simply a way to distribute data between the various classes defined on a dataset. Classification algorithms learn this distribution form from the given training set and then try to classify correctly. In the classification, the group membership of the problem is defined. The data is categorized under different labels according to some parameters, and then the labels are estimated for the data. So if there are two classes, this is called binary classification. If there are more than two classes, it's known as multi-class classification. All right, so now let's talk about regression. Regression is the prediction of the behavior of a random variable using a model. For example, let us have a model trained with a data set. So with this model, we can predict a value that we want to learn or another value that corresponds to a value. This process is called regression in statistical science. Basically, regression calls a relationship between two or more variables. So the task of measuring the level and scope of this relationship is called regression analysis. It's necessary to obtain the relationship between parameters as a function. Now, parameters can be independent or interdependent of each other. So, my friends, that's the evaluation of regression and classification. So let's dig into some of the differences now. So some of the main differences between classification and regression. The main difference between classification and regression is while a categorical variable tries to estimate in classification, for example, patient or not patient, 0, 1, a continuous value is attempted at estimation in regression, for example, car or house prices. While classification predicts unordered data, regression predicts sequential data. Now, another difference is evaluating the performance of each. So while classification is evaluated by measuring techniques such as accuracy and precision, a regression can be evaluated using mean square errors. All right, so there you go, regression and classification. In the next lesson, we're going to learn about the criteria used to evaluate them and how to interpret all of that. So until then, have a nice day. Well, hello, dear friends. Welcome to this lesson. So right now, we're going to talk about classification problems in machine learning. So you got to understand the logic of classification, as well as we want to have a look at the metrics that we're going to be using in order to evaluate the result after solving the classification problem. I say problem, but I mean sort of a challenge because there's, well, like most things, it's multifaceted. So why don't we just dive right in without doing anything else, especially talking. So we're going to first tackle this question of what about classification? What is it? Why is it so important? Well, my friends, we've got a lot of data, right? This is the age of big data. We're going to create a model after training this data. So the model now makes a prediction when it sees new data. Right, so you know all that. But if this prediction belongs to one of the labeled classes that we have predetermined, we're going to call this problem a classification problem. So let's make sure that we know this subject thoroughly, just by making a concrete example. So I want to show you Let's say we have many pictures of tomatoes and apples. Okay, so from each image, we can, of course, determine the color and the size of the fruits. Yes, tomatoes are actually fruit. So the first step for supervised learning is to acquire labeled training data, right? So in our example, data actually means we get many images of fruit labeled as either tomato, or apple, or apple. Never mind. So we can extract color and size information from these pictures and associate them, right, with being a tomato or an apple. So for this example, we can graph our labeled training data, as you see here. Red, the round shape, is labeled a tomato, and blue, the hexagon shape, is an apple. Now, as you can see, of course, there seems to be a pattern in this data, right? So the red circles are clustered over here on the left. The blue hexagons are clustered over there on the right. But here we want our algorithm to learn these patterns as well. Okay, so our aim for this problem is to write the algorithm that we will be able to separate the two labeled groups with a decision boundary. Now, a simple decision boundary could just be the way that you see it in this picture. But do you notice this decision limit is a little simple? It does quickly separate tomatoes and apples from each other, but is it always like this? Well, no, of course not. That's why we're going to dig into some of these details, my friends. Right, so in the picture, a more complex machine learning algorithm can also create a decision boundary. So yeah, to summarize all of that, our model is, according to our algorithm, learning the pictures with the tomato and the apple labels in a training set. And the algorithm will apply its, we'll call it experience, to the pictures that we haven't trained it on. Yes? Yes. But more clearly, this is about making the assumptions about these pictures that the algorithm's never seen using this historical or experiential, whatever you want to call it, data. For example, when we give a picture of a particular fruit, well, it can classify the picture as an apple based on the decision boundary that we draw. Okay, so this is sort of a broad example of a classification problem in general. Okay. Now, likewise, we can apply this strategy, of course, to many different problems. For instance, classifying tumors as benign or malignant, classifying an email as spam or raw, whether there is risk of a heart attack, all these kinds of things, right? So these are the types of machine learning examples that are called classification. Okay? So the algorithm that solves the classification problem is called the classifier. And the guidance from the predicted examples to the classes is called the classification model. Okay, so can the classification model that we've created make a 100% correct decision? How could we distinguish the errors made by the classifier and then the types of errors? Right, so these are the kinds of questions that are probably coming up in your mind, but the subject that we need to address first is classification error metrics. So we can test the accuracy of the classification model that we created according to these evaluation metrics. So I just want to take you through these so that you can learn them now. I want to first start with the confusion metrics, my friends. Now, when you're talking about binary classification, one of the most comprehensive ways to represent the evaluation result is by using a confusion matrix. Now, a confusion matrix is a table basically summarizing how well a classification model predicts. Sounds simple. It gives information about the model's performance, the errors made by the classifier, as well as the types of errors. So what you're looking at now on the screen is what we call a confusion matrix table. Right, so according to this table, the x-axis represents the actual values. The y-axis represents the estimated values. Now, let's get into some of the meaning of the values in this table with a good example rather than just, kind of explaining them hypothetically. So here is our example. We have a parrot, and we keep it home, and we want to train this parrot, because believe me, if you keep a parrot at home, you're going to want to train it. Anyway, our aim here is if the parrot sees a person trying to enter the house secretly, stealthily, it's going to shout out that there's an intruder, a thief, something, a burglar. So in this example, the parrot represents a model that we trained. The classes of the model represent whether the thief exists or not. So just imagine for a moment that we trained this parrot very well, and now we want to test to see whether this parrot will alert us correctly. Now, let's say that we've worked with a parrot 100 times, and now we're going to discuss the true and false warnings and their consequences with our confusion matrix chart. So you see the first value of our table is true positive. So if the actual and estimated values are equal, then this true positive value appears. Now, if we have a look at our scenario, there is a thief in real life, and the parrot says there's a thief as a guess. And after all, this is a correct guess. But you see, both the actual value and the predicted value are both correct, and this is something that we want. So the parrot gets a prize, let's say. Now, in total, 1 out of 100 trials have resulted like this. So now the other value of the confusion matrix is a false positive. So let's say if it has guessed that there is something that does not exist, well, then this value will emerge. So if we have a look at our scenario, there is no thief as its actual value, but the parrot that we trained says that there is a thief. That's, of course, an undesirable result, so the owner then gets angry with the parrot and hopefully will calm down shortly. But let's say that this parrot did this once in 100 trials. So that's why you see this FP value on the screen. So here is a point that needs our attention. We call the wrong guess made like this, type 1 error. So we're going to talk about that subject in more detail shortly, type 1 error. But let's have a look at the third value of our table, which is false negative. Now this happens when we mispredict something that should happen. Going back to our parrot, well, normally there's a thief, but the parrot shouts that there is no thief. Well, that's a hazardous mistake, because by the end of the guess, the thief then will, break into the house and do whatever thieves do, okay? So we call this error the type 2 error. And this error is generally considered more important than the type 1 error, because guess why? Well, if you were sleeping in your bed when there's a thief, your parrot's not telling you, you might get a conk on the head, and all your stuff will be gone. In other words, saying something that exists does not exist is going to have some pretty serious ramifications. Now, I wonder if you've noticed something. This result has been obtained 8 times in 100 trials with parrots. And because of the parrot's wrong guesses 8 times, that means a thief was able to steal all the items in your house 8 times over. But I want to continue with this. So this is a situation that we want. As a result, the parrot made a correct guess, got a parrot reward, whatever that might be. But this result here, you see, this was obtained 90 times in 100 trials. All right, my friends, so this is the basic logic of the confusion matrix and the meanings of the values in the table in general, with a, fairly good example. So we're going to evaluate our model based on these particular values. But where do we use these values? How are we going to use it? Well, I just want to simply examine these metrics. The first classification metric that we will examine is called accuracy. Many people are obsessed with accuracy. Now, my friends, in this metric, this is the number of correct guesses divided by the number of all the guesses that were made. Okay, so the formula is right here up on the screen, but I want to show you how to apply this metric to our particular scenario. Don't kill the parrot yet. So here we have the owner of the parrot has tried 100 times in total, and a total of 91 of these trials are representative of correct guesses. So in this context, we can say the following. 91% performance, right? Just simple math, 91 out of 100. But my friends, taking into account the accuracy value might make sense if there's an equal number of observations in each class. So then how logical is it to apply this metric to our scenario? Well, my friends, the value may seem fine on the surface, but when you look at the numbers again, you realize that the thief appears 9 times and is guessed correctly only once. Well, that's not a very good result, is it? But our accuracy score reflects 91% accuracy. Right, so we can deduce the following conclusion, right? The use of metrics may differ from problem to problem. In some problems, it may be advantageous for us to look at the accuracy metric, while it might be incredibly unreasonable in others. So to summarize all of this, our accuracy value is 91%, but perhaps it's more advantageous not to use this metric for this idea of classification problems. So I want to show you with this other metric, and what's that called? Precision. Now, don't we all admire precision? My friends, precision tells us how many of those predicted as positive are correct. Okay? So in other words, if we look at the formula, it's found by dividing the true positive value by the sum of the true positive and false positive values. So this precision is a performance metric. It should be used when our goal is to limit the number of false positives, or FP, right? Now, this model should really produce many false positives. It will have a high sensitivity. But precision is a very helpful measurement when a false positive is higher than a false negative. So if we have a look at our scenario again, our true positive rate is 1. The sum of true positive and false positive is 2. So in other words, the result of 1 out of 2 is 0.50 or 50%. Now, I don't know, is that surprising to you? It surprises a lot of people. You see, the precision value of our model, for which we just got a 91% accuracy value, is only 50%. So it means that we should not make a quick decision on model accuracy just by considering a single metric. We should actually evaluate the metrics according to the type as well as the type of the problem, right? So let's have a look at this recall value. Recall measures how many of all positive classes that we have guessed correctly. So having a look at this formula, true positives are divided by the sum of true positives and false negatives. So when you plug it back into our scenario, the true positive rate was 1. So we divide this number by the sum of true positive and false negatives. That is the value of 9. See, so we get this very meager result of 11%. Now, I know I'm kind of being a little pedantic about this and trying to drill this focus in. But it's just really for now, because I need you to get this, and I want to repeat it one more time. See, the importance of these metrics varies depending on the purpose of developing the model, right? The importance of these metrics varies depending on the purpose of developing the model. So, for example, the recall value is significant in the model that we train to catch thieves to protect your home. The recall value should obviously be pretty high, perhaps in this case to you, because if we guess wrong, our house is going to be in danger of being robbed, right? But to put it another way, I'll give you another example. So in the model that can distinguish bird photos from just animal photos, the recall value can be taken into account actually less to capture more bird photos. Make sense? Yes. Now I just want to touch on just one last subject before we wrap this lesson up. I want to show you this balance, because there is a balance between precision and recall. Have you noticed that? So while precision and recall are critical metrics, it's kind of hard to compare two models just by looking at one of them. So one way to make them comparable is a particular metric that is the harmonic mean of precision and recall. Wait, what? Did I stutter? Harmonic mean of precision and recall. It's basically the F1 score. So this metric helps to measure precision and recall at the same time. You see, you can use this formula here that you see on the screen. Now, at the beginning of the definition, I said harmonic mean of precision and recall, right? So this is a harmonic mean instead of just a simple mean because we can't ignore extreme cases. If it were just a simple average calculation, a model with a precision value of 1 and a recall value of 0 would have an F1 score of 0.5. But see how that's going to mislead us. However, you will see that the result using the harmonic mean is a far more accurate decision. Therefore, the F1 score is generally used to measure the performance of classification models. So the main reason for using the F1 score value instead of accuracy is to not make an incorrect model selection in unevenly distributed data sets. Furthermore, and in addition to that, the F1 score is significant for us since we need a measurement metric that will include not only the false negative or the false positive, but also all error costs. You see that now. That means that we've come to the end of this particular lesson. I want to see you next time, though. Until then, take good care. All right, my dear friends, hello and welcome back. So, previously, we discussed the classification problems and we examined the classification metrics used to evaluate these problems. So, this course is going to cover regression problems and examine the metrics used to evaluate regression problems. And now, you know where we're going. Let's start with a definition of regression. So regression is a statistical tool. You might be familiar with it, but it's used to estimate the relationship between the dependent and independent variables. But more specifically, it focuses on how the dependent variable changes according to the changes in the independent variables. It also helps in modeling the future relationship between variables. So what are we talking about when we're talking about dependent and independent variables? Well, in the data that we are currently working on, the variable that forms the basis of the estimation is the independent variable. The variable whose value is to be estimated is known as the dependent variable. Okay? Continuing on with that, at the end of our work, we'll need to check the model's accuracy that we've created. So the model that we created is a regression problem. So this time we'll need to use regression-specific evaluation metrics. Now let's examine these metrics, in a particular order. Okay, so the first metric that we will examine is mean absolute error. So this mean absolute error, this is the difference between predicted and actual values. Now, strictly speaking, it is the mean of the absolute value of each difference between the actual value and the predicted value for that sample across the entire dataset sample. Okay. So you see the formula on the screen. Here, the first letter Y represents the actual values and the other the predicted values. Okay, so yeah, we can get the mean absolute error just by dividing all this difference by the total number of data. So for a result, this value shows us the error made by the model. Now, of course, this value being small is something that we want to keep an eye out for because that's kind of what we're looking at. It's what we want anyway. Okay, so when we look at the metrics in general, in other words, the model is actually penalized with metrics. So we prefer the model with the lowest penalty. So looking at the punishment here, you see that? However, I would like to bring your attention to one particular point. MAE penalizes the model less than other metrics. Yeah, you remember that when I examined the classification metrics, I explained that each metric differs according to the problems. Well, this is also the case in regression problems. Yeah, since the MAE value is easily interpretable. It is frequently used in regression problems. Okay, so now let's move on to our other metric. Wait, what's that? The mean squared error. So the mean squared error represents the mean of the squared difference between the actual and predicted values of the data set. So we call the difference between the actual values and the predicted values residual. So you see how MSE will measure the variance of residuals. And you'll have a look through this formula on the screen. But do you see how the MSE model punishes more? The MSE statistic gives exaggerated results in the case of significant deviations because it takes the squares of the errors. Sounds a little brutal, but that's why instead of this particular metric, the root mean squared error, which we're going to learn soon, is typically more preferred. Okay, but I do want to continue with this though, so just hang in there. If we're looking at the MSE value as a metric, see how the smallest one should be preferred for our use. But now I want to take you through another metric here. This is that RMSE that I was talking about, right? My friends, this is the root mean squared metric. So it is obtained just by taking the square root of the MSE value in the broadest sense. So here you see the formula on the screen. So you see this metric measures a standard deviation of the residuals. So the difference between the true and predicted values, that is, residuals, is how far the regression line from the data points. You see? So the RMSE measures how widespread these residuals are. So in other words, it tells us how dense the data is around the line that best fits the data. Now, the RMSE value can actually range from 0 through infinity, and the estimators with the lower values perform better. Now, a 0 RMSE value means that the model has not made any errors. RMSE has the advantage of penalizing major mistakes more, so that's why it might be better suited to certain situations. Of course, some of our friends might be scratching their head and asking, well, now, what exactly does punishing a mistake mean, and what do you mean by the advantages? Well, these are very good questions, so I want to answer these questions with a thorough example. So, my friends, you see this on the screen here? We've got two situations. Now, according to the first case, the actual values are 2, 4, 6, and 8, while the model's predictions are 4, 6, 8, and 10. Now, I wonder if you notice the differences between the actual and the estimated values are always the same, right? 2. So according to the second situation, while the actual values are 2, 4, 6, and 8, the estimated values are 4, 6, 8, and 12. There's a slight difference though this time, yeah? Have you noticed? The difference between the actual value and the estimated value of the first three numbers is 2. But when we have a look at the last values, we see that it's grown to 4. So yeah, now we're getting to the main question. We are looking at the metrics according to these values, but which metric is actually more valuable? Yeah, so according to the first case, the MAE and RMSE values become 2 when we put the mathematical formulations in place. But according to the second situation, if you pay attention, that is, the MAE value is 2.5, but the RMSE value is 2.65. So what inferences can we actually make from these results? Well, my friends, if there's not a whole lot of difference between the actual value and the estimated values, MAE can be a pretty easy metric to interpret. However, if there are too many differences between the actual and the estimated values, doesn't it seem more advantageous to use the RMSE metric instead of the MAE? Now, did you notice RMSE penalized the model more because of the difference in the final value compared to the second case? So you see, punishing the model means that we have to be more careful. Therefore, the RMSE value is more advantageous for us in this particular situation. All right, so let's just continue on quickly. I just want to show you a couple more metrics and we'll wrap up this lesson. So the following metric here is the R-squared metric. Now, my friends, this metric shows us how many percent of the dependent variable the independent variables can explain. Now, I don't want to get into the formula too much and confuse you, but your understanding of the general logic is going to be good for now. So a high R2 indicates a good regression model fit. So does a high R-squared always show us the right way? Well, my friends, as the independent variable is added, the model becomes more complex. And when the model becomes more complex, overfitting occurs. Yeah, overfitting. Therefore, the R-square increases. You see that? So adjusted R-square comes into play to solve such problems. Adjusted R-square compensates for each independent variable and increases only when given variables improve the model beyond what is possible. Yeah, so you can see the formula up here on the screen. Now, it might be a little confusing right now, but when we code and interpret these metrics with Python on concrete examples in the future lessons, well, you're going to say, why didn't I see that one coming? All right, my friends, hey, we're actually out of time. We're going to end our lesson here, and I want to see you next time. Oh, hey, how's it going, my dear friends? I'm glad you're here. Welcome back. So right now, I want to show you how to use machine learning on Python, theoretically. Now, the primary purpose of putting this course in the curriculum is to learn the subject theoretically before moving on to coding in Python, right? So we're not going to actually spend a whole lot of extra time understanding the issue while we're coding, right? So that's why we're going to just tease it out a little bit. Anyway, let's get into it. So, my friends, we're going to first start by getting acquainted with the scikit-learn library. So scikit-learn is a primary library that we will use while coding when we're doing machine learning in Python. That's true. We are now entering the machine learning territory. So let's have a look at scikit-learn library. It's pretty much the most popular Python library, but this is the one that we're going to use while making our machine learning applications. Okay, so this library actually comes ready to use on the interfaces that we're going to work on, but in some cases it may be necessary to load this library from the outside. So in fact, in the case of an external installation, just install this library by typing conda install scikit-learn right in your command line. Now, if you actually have Anaconda or any other distribution, you can run the code cell by typing the exclamation point pip install scikit-learn in the code line. In any event, the scikit-learn library will be installed in the environment where you're going to be working. So now let's get to know the scikit-learn library a little bit better. Now, at the beginning of the lesson, we said that scikit-learn is one of the most widely used Python packages for data science and machine learning. There are other features of scikit-learn, which are data manipulation, dimensional reduction, model selection, regression, classification, and cluster analysis. And it also provides several data sets that you can use to test your models. Scikit-learn is built on top of NumPy, SciPy, and Matplotlib. All right, so now that you know a little bit more about it, we can just move on to how to use it. Now, the part up to machine learning in a data science project goes like this. First, data is taken, then cleaned, then exploratory data analysis is done, and finally, the machine learning part. So the variables to be sent to the models have got to be determined. Okay, so the data is now ready for machine learning. Let's start the machine learning process together. Now, first off, my friends, we'll need to import the model that we're going to use from this scikit-learn library. Now, each algorithm in the library is presented through an estimator object. So here, this object is the machine learning model that we will work on. You see, the structure of the import process goes like this. First, we determine the family of the algorithm that we will work on from the scikit-learn library. And then we import the algorithm object. So I want to give you a concrete example straight away. So for instance, we have a regression problem and we want to use the linear regression algorithm. So we'll first say from sklearn, and that'll call the scikit-learn library. Then we determine the family in which the linear regression model is located. And you can see this family was the linear model family. So now that we found the primary location of our model, we can actually import it. So we say import and call the algorithm. See, we are writing linear regression algorithm. So when we run this code, the estimator object will be ready for us to use. So we'll continue our operations through the object. Okay, so now, since the object is ready, we can instantiate this object in the next step. For this, we'll need to assign the model to a variable. So you see there's an example variable definition on the screen here, right? See, its name is example_model. Okay, so we are equating this variable to the linear regression model object. And then when we call the variable again, as you can see, the linear regression model object is now instantiated for us. Now, I want to draw your attention to this detail here. Usually there are various parameters inside each model object. Now, we call these parameters predictive parameters. But you can use additional parameters to set the model to something a little more specific. So you can see these parameters just by going inside the model object and pressing the Shift-Tab keys. Yeah, good. So now I want to give you another example of this. So you will see a new model variation on the screen. The name is New Example Model. Now we again equate this model to the linear regression object. However, I'm going to do Shift-Tab inside the model object this time. So, do you see? There are various parameters in the linear regression model object. So what you see on the screen are the default values of these parameters. Now, if we run the code directly just like this, the parameters will be set to default. This is actually how we did it a while ago, but maybe we just need to change a few of these parameters in the future. So we will need to adjust the best parameters for our particular model. Okay, so here we're going to make some changes to the parameters. For example, let's embody this model by changing all the parameters. As you can see on the screen here, I've synchronized all the parameters with different values. And now when I call the variable again and run the code, as you can see, the model object became concrete and then printed the parameters while creating the object. Cool? Now, like I said, it's actually necessary to do a separate study to find the best of these parameters. I'm just showing you that you can change them. But this is actually called the hyperparameter tuning process. Obviously, for now, I'm just randomly determining these parameters because I just want to show you how they change, right? So after instantiating the model object, the next thing to do is give data to the model and train it. So that means it's time to do the training part. But first, we'll just give that data to the model. So how do we give data to the model? Well, my friends, before you do that, we'll need to separate the model into two, a training and a test set. While we train the model with the training data, we'll test the model with the test data. I want to show you what that looks like through a pretty good example here. Now, as you know, we will have dependent and independent variables. I will call the dependent variable the variable we will predict y, and the independent variable will be called x. Okay, so first I'll create synthetic data, and I will use NumPy library for this. So see, we first import the library and then create the independent variables, namely variable x. So we create a 10 by 3 NumPy array. And you see each column represents a variable, and each row represents a number of observations that we have. Okay, very good. So let's continue. And now we'll create the dependent variable, the variable y. So we use the range function and create a target variable from numbers up to 10. Okay, so now our data looks ready. So my friends, we're not going to insert this data directly in the machine learning model. What? Yeah, so what are we going to do then? We need to divide this data first into two, right? The test set and the training set. You remember, this is very important. Okay, so the module that we will use for this is called train test split module. It makes sense, huh? So the module is again within the scikit-learn library. So we import from the model selection family. Okay, so now you can see the code up here on the screen. So when we run it, we will have achieved our goal. Okay, so now it's time to split the data. All right, my friends, so when we use the train test split function, we will now have 4 data at the end of the process. These are the test and training data of X and the test and training data of Y. You see how 4 variables are created, and you see the variable names, xtrain, ytrain, xtest, and ytest. Right, so we equalize these variables to the train test split function, and then give the data that needs to be divided into this function. And then when we have given the dependent and the independent variables, x and y, but in general, there is one more parameter to be set. Now, what's that going to be? The test size parameter. So my friends, with the test size parameter, we determine how the data will be divided as a percentage. So if we have a lot of data, this rate can be kept low. If there's very little data, it's essential to keep this ratio as high as possible. For now, we're just going to set it to 0.4 for an example. So now at the end of the process, we call the variables separately. And you can see the values on the screen after the data gets divided. But now you see the data is ready for modeling. So in other words, we can train our data. By the way, I just want to share with you one more little point or insight. But to reiterate, this course really aims to increase general awareness before we get to coding. So you're not going to need to memorize any code written here, since we're going to be repeating the operations that we've done here a lot in the following lessons. I just want to make sure that you know this subject backwards and forwards, right? So currently, that's why we're just increasing our knowledge through theory. Okay, just wanted to make sure. So we'll continue then. Next is training the data. So yeah, the function used to train the model is the fit function. And now we'll train the model by putting the data that we have divided and called training into this function. All right, so we've applied the fit function on the first model that we created, and our model is now trained with that training data. So now we need to test the trained data so that we can double check its accuracy. And sure enough, the method that we're going to use is the predict function. So we'll put the test data inside this function. And you see we have set a variable in our example, and the name of the variable is example predict. So after we equalize our model to this variable, we apply the predict function to it. And after placing our test data in it, we will run the code cell. So yeah, in the following process, we'll now have our estimates. And we'll investigate the accuracy of these predictions, of course. So we will calculate the accuracy of the model by comparing the example predict variable with the ytest variable. And we will use the evaluation metrics that we learned previously to see these benchmarks and model accuracy. Yeah, since, of course, this lesson is about understanding the logic of machine learning in general, we're not going to really get into the evaluation part. I just want to get you practiced, right? So in this particular lesson, I gave you an example of the general machine learning process over the regression problem. So regression is a concept evaluated in supervised learning. But you have to remember that there is also the concept of unsupervised learning. So we might just actually encounter some minor differences when using machine learning algorithms included within this concept. So for example, model training is done with the same function for two learning concepts. So which function? Well, the fit function. Yeah, in supervised learning applications, the fit function takes two arguments. That is, it includes x and y variables. But in contrast, in unsupervised learning applications, it takes only one value, as there's not going to be any dependent variable, which is the variable x that we will predetermine. You follow? Just keep that in the back of your head. But we're going to continue with this one. So we've examined the functions that must be used in the machine learning process. Now we're going to examine some of the optional functions to be used in this process. So my friends, the first function to have a look at in this context, of course, optional, is predict proba. Obviously, probability. So we can use this function if we want to learn the probabilities, not labels. So you got to remember, though, predict was telling us the model's predictions using the test data. In predict proba, well, the results include the percentage that each prediction belongs to the label. See the difference? Okay, so the other function that we want to have a look at is score. We can use this function in classification and regression problems. It's a function that we will use when we want to see the model's accuracy numerically. So it'll contain a value between 0 and 1. For example, the score value is 0.89. So we can say that the success of our model is 89%. Now, another function that we might use to examine is the transform function. With this function, you can actually transform your data. Now, some machine learning algorithms require scaled data because they perform distance-dependent calculations. So there can be significant differences between variables in unscaled data. For example, values in one variable may vary between 0 and 300,000, while in another variable, they may only vary between 1 and 10. So to make these distances of all the variables similar, we're going to need to scale. So we can perform this scaling with the transform function. Okay, so now we can pass on to the other function. And what's that going to be? Fit underscore transform. So my friends, with this function, we can first scale our data and then train it. So it does two things together. So only when we apply the transform function will scaling occur. Then we need to train the data as an extra step. However, this function will provide us two of these things both together with fit transform. Okay? So that is machine learning in general, theoretically. We also understand how to use the scikit-learn library. And like I said earlier, you're not going to need to memorize this particular process since we're going to be repeating it frequently in the projects that we're going to be working on together. But I just want to make sure that you understand the logic clearly. Now, I do want to do one more thing before we wrap up this lesson. Now, it can be challenging to remember which algorithms are in the library and how they're actually used. So I just want to make the following suggestion to perhaps make that a little bit easier for you. If you go to your favorite internet browser and type in scikit-learn algorithm cheat sheet, well, you're going to see a plethora of images, and I'll just open one of them. So you can obviously reach the algorithm that you need just by following the arrows here. So all classification, regression, clustering, and size reduction algorithms get written separately. But you can also find out which algorithm to use under which conditions. So yeah, in cases where you're going to be working with machine learning, this cheat sheet will kind of actually be a treasure. I don't even know why it's called cheating. But my friends, that's to wrap up our lesson here. So I want to see you next time. All right, so here we go, my friends. Welcome back. So previously, we've talked about a couple of concepts, supervised and unsupervised learning. Obviously, we didn't get into the details. However, that presents us an opportunity because we want to get into the details now. Supervised learning. So supervised learning is a learning model that uses labeled data while training. So then wait a minute. What is labeled data? Well, my friends, if the target variable is known precisely in a machine learning problem, this variable is accepted as labeled data. So, for example, let's just consider the price forecasting project. All variables except the price variable try to predict the price. Price is the target variable here. Since price is a known fact, we call this data labeled data. Now, we call the algorithm that works with labeled data supervised learning algorithms. Okay. For example, just another way to look at it is let's have 11 variables related to mail. So the first 10 of them contain information about email. So here, the last variable is the target variable and is considered labeled data because it tells us whether mail is spam or not. You see, so if you're working on this project, it can be performed using supervised learning algorithms since there is labeled data. Now, also in supervised learning, the goal is to train models with the labeled data that we have, and then let the machine make predictions when we give data to it that it's never seen. In supervised learning, we know that our data set is, what it is, and what the desired output should be from that data. So to bring all that together, supervised learning provides a function, a match between the input data and the result data, to be extracted from this information by refeeding data and the results from that data to the machine. Thus, the machine learns the relationship between data. All right, I think you get it. We'll move on. Supervised learning problems are divided into two, regression and classification. So with a regression problem, we try to predict the results in a continuous output. We try to map the input values to some continuous functions. But then, wait a minute, what does continuous data mean? Well, these types of data are values determined by measurement and can appear either as integers or as numbers with commas. I want to show you a quick example of regression. Now, imagine that you're doing research for a real estate firm. Now, you want to find the relationship between house size and house prices and set a price for a new house that's coming up on the market to be sold. And while you're doing this, you're going to use the data that you already have, such as what size houses were sold and for how much. So then here you would insert the data into machine learning and then show the machine your data set. Okay. That way you'll be able to set a price for any size house using this data that you input into the machine. See, the computer will find you a regression equation and calculate the fair price for the new home. So you see, that is the regression problem. So I want to show you another type of supervised learning, which is classification. All right, so we talked about classification earlier. In classification, there are one or more values to classify outputs. The new value that we want to find is one of these classes. So let's just get into an example of a classification problem. Now, based on breast cancer data, we need to determine whether cancer is benign or malignant according to the tumor size of a new case. So you see how that's a classification problem. Now, since the variable that we are targeting is going to determine whether the cancer is benign or malignant, it's predetermined. So in other words, it is labeled data. Therefore, this is a subject that should be evaluated in supervised learning. You get it? Cool, because this is actually the end of this particular video. So we're going to switch to supervised learning algorithms in the following, and we'll be doing that one by one in order. So I'll see you next time. All right. Hello, my dear friends. Welcome back. And we're going to do another lesson here. We are going to be starting the machine learning algorithms in the scikit-learn library. Now, with that context in mind, we're going to first introduce the linear regression algorithm. So it's a supervised learning regression algorithm. But before we get to the coding part, I want to introduce you to some of the theory as well as some of the history involved. All right, let's get into it. So hopefully pretty quickly you'll understand why I want to give you some of this history, all right? Because linear regression first actually began with a man named Francis Galton, a very versatile British scientist who lived in the age of Queen Victoria, right? So Sir Francis Galton introduced this idea of regression to the research community in a study examining the relationship between the height of fathers and sons. His study observed that sons do not tend toward their father's height, but instead regress to the population average. Really interesting. See, so this way he formulated the idea of regression toward mediocrity. Now, of course, that's a very brief history. Go ahead and go look for that. Google to your heart's delight, but not on our time here. We're going to look for an answer to the following question: what is linear regression? So linear regression represents the relationship between two or more variables within a line. So I'll just explain with a very simple example. So in the table you see before you a banana, and on the banana axis corresponds to $2 on the price axis, yeah? So this means that a banana costs $2 at that point. So if we're going by this logic so far, 2 bananas would then cost $4, 3 bananas $6, and 4 bananas are $8. Now, of course, 0 bananas are also $0. Okay. So you can see the linear relationship between the two variables simply by looking at this example. Now, let's make our example a little bit more complex. Now, to take a closer look at what we do in real life, we'll look at the relationship between house prices and square meters. You can convert it to square feet if you really want to. But here you can read that the price of a 75 square meter house is $75,000. A 150 square meter house is $150,000. 225 square meter house is $225,000. 300 square meter house, $300,000. Right. So this is just an example for easy understanding. So when we look at these examples, we see that the bilateral relations are pretty linear, right? So can we always count on encountering this situation when we encounter actual data? Well, the answer is, of course, the distribution of the data that we examine is usually not regular. But like I say, this is theory right now. So a bit more of a real-life example is now up on the screen, so let's have a look at each red cross representing a house. However, you see it's not that easy to read the value from this table, right? Well, how do you suppose that we could create a linear relationship by looking at the square meter and the price data of these houses? May I introduce you to the algorithm that will help us at this point from now on, the linear regression algorithm? So see, we're going to draw the most appropriate regression line to show the housing data linearly. Now, hopefully you can see the linear relationship that emerges by considering the weight of square meters and price information of each house like this. So then you might be asking, what's the mathematical equivalent of this line? Well, here you see on the screen, the equation of this line goes like this. Here, y is the target value, that is, it represents the price. X is the independent variable, and that is the square meter information. Now, deeper still, have you noticed? There's one more value over here at the end, and that value is when x is at 0, it represents the required value of y. So yeah, if we just do another quick example considering this formula, for example, the price of a house of 80 meters squared is $112,370. right? So I've also put the R2 value, or R squared value in here. So do you remember this value for metrics? The independent variables could explain the dependent variable. So we could say that it's the accuracy of the model. Follow? So yeah, this formula is where we need to actually focus on. So this formula is the mathematical result of the algorithm we call linear regression. Now, considering this formula, I'll bring in a more complex linear regression formula to the screen. Okay, so you see here y is a predicted variable for us, and that is the dependent variable, okay? So the values of x1, x2, x3, and x4 on the screen, as you see, are independent variables. Now we could say all the values except the target variable. Yeah, so right in front of the independent variables, the beta values b1, b2, b3, and b4 are the coefficients assigned to the independent variables. Yeah, so the basis of this mathematical formulation is hidden in these coefficients. So in other words, when we put the independent variables into the formula at the end of the whole process, they will be multiplied by the coefficients and will provide us with the output y. Now, there's also an a value here. Now, friends, this value is the value of y when x values are 0. Okay? So now, I want you to explain to me. No, all right. Just kidding. I want to try to explain all of these formulas in one more image so that we can understand it thoroughly. So have a look at this. See the blue circle? This is where there is one house. Now, if you focus on the triangle on the graph, you'll see the slope of the blue dot to the linear regression line. This slope is the beta coefficient value for us. And at the bottom, we have the residual value a. This represents the value of y when x is 0. Yeah, so the result of this graphical operation is the linear regression formula. Whoa. Blew your mind? Okay, maybe not quite yet, but we did learn the general theory of linear regression algorithms. So if you got into logic, if you didn't, have a look at some of the history, play around with it. But we are going to practice it in the future lessons here, so don't worry about it too much. I'll see you next time. All right, hello, my dear friends. Welcome back. So in this lesson, we're going to do our first study of this linear regression algorithm. Now, in the context of what we were talking about earlier, the data set that we will work on will be the MPG data set built into the Seaborn library. Now, my friends, this data set basically estimates the British fuel consumption, measure MPG. So MPG, it's going to show how many miles a vehicle has traveled in or with 1 gallon of fuel, right? So within this context, we're going to analyze data and create an MPG forecasting model. So let's get into it before we wander off into some other topic. All right, so we're just going to write up a title on the first line. And I'm converting this line to Markdown format. And I'm writing importing the libraries as a title. So then I'll put double asterisks on both sides of it because I want it to appear in bold format, right? Okay, so now let's begin coding. So I'm saying here, import numpy as np, import pandas as pd. Let's go ahead and run the code. So now we've got the basic libraries. We'll import the visualization libraries. So I'll say import Seaborn as SNS and continue to say import matplotlib.pyplot as PLT. And import warnings library to avoid minor errors. And then I'll call the filter warnings module just by saying warnings. And I'll write ignore. All right, my friends, so these libraries are going to be enough for us to work with. for now. But guess what? If we do need to load an extra library in the future, you know how to do it. We'll do it there when we get to it, if we need it. Anyway, let's load up the data that we're going to work on. So again, I'll open up a cell in Markdown format for the title, and I'm writing loading the data set. I'll put double asterisk on both sides because I want it to appear bold. All right, so now we can continue. So I'll specify a variable. I'll say df equals and call the Seaborn library. And see how I'm bringing the load dataset function from this library, and I'm writing the dataset that we'll work on. So I'll say MPG. Let's run the code. Now I'm calling the dataset, so I'll say df.head. And you see the dataset shows, now there are 9 variables in total. Why don't we just get to know these variables in the order of presentation? So first we have our target variable, MPG. And yeah, I told you about that in the very beginning of the lesson, but I do want to explain again that MPG is short for miles per gallon. We're sticking with where the data comes from. This is the British measure of fuel consumption. Now it shows how many miles the vehicle has traveled with a gallon of gasoline or diesel, I suppose. Now, I wonder if you've noticed this variable has a continuous structure. Therefore, it is within the scope of regression of supervised learning. All right, so let's continue. The cylinders here create the energy that keeps the engine running by the back and forth movement of the pistons. Right, so let's continue. Displacement, this will be the engine size. It's the volume of all the pistons inside the cylinders of a reciprocating engine, swept from the top dead center, TDC, to bottom dead center, BDC, in a single motion. All right? So we'll continue with that. I think there's actually not a need here to explain horsepower. Everybody kind of has an idea of what horsepower is. But it is the most crucial key that gives information about the performance of a motor vehicle. So we'll keep that in mind. So continuing on, we've got weight, which is the weight of the vehicle. Acceleration is just that, the acceleration of the vehicle. And as the name here would suggest, model year is the vehicle's model year. Origin of the vehicle. And then finally, the name of the car. Okay, so those are the variables. So this MPG variable, this is our dependent variable. The other 8 variables are the independent variables that will help us estimate this MPG. So let's get into our study now. But before we move on to modeling, we do need to do some exploratory data analysis. So what I do first is look at the information of the data set with the info method. So I'll say df.info and run the code. And now we've got some information. We see that there are 398 rows, 9 columns in total. And we can see here if there are any missing values for the variables from the middle part. So see here, there is horsepower variable that kind of stands out, right? A total of 392 rows appear. So it means there's 6 missing values. Okay, so we just make a note of that and continue. And again, we can see the variable names and types in the middle. And then below is a summary of the variable types. You see there are 4 floats, 3 integers, and 2 categorical definition object type variables. So yeah, the first thing that we need to do now is analyze the data and remove the variables that we think will contribute the least to the modeling from the data set. Because you got to remember, right? What was our purpose of modeling? Guessing the MPG variable. So just by having a quick look at the data set, I really don't think the name variable is going to affect that MPG, right? That's why I'm going to remove that from the data set, right? So I'll just say df.drop and I write the variable that I want to drop. So I'll say the axis parameter to 1, as I want to reduce it on a column by column basis, you see? So by setting the axis parameter to 1, I can reduce the entire grid on a column by column basis. And because I want the change that we made to be permanent, I'll set the in-place parameter to true. Okay, so everything's ready now. Let's run the code. And now I'm calling the data frame structure again, so I'll say df.head. And look at this. Here's our request. The categorical variable is the origin variable. So why don't we continue on and look at the basic statistics of numeric variables. Again, we'll write the partition name. So I'll open up a cell in Markdown format and write summary of data set. Now, remember to put double stars on both sides and run the code. Okay, so let's continue. I'll say df.describe. And yeah, so we can see the mean, standard deviation, minimum and maximum values, and quartiles of the variables here. So this is good data for us. Now, in general, by looking at this information, we can have information about the distribution of the variables from these statistics. So now I want to make a couple of examples and ask you to comment on the distributions of all the other variables. Yes. So let's focus on the data of the MPG variable. So see the minimum value 9, maximum value 46. And the midpoint of these two values, 27.5. Yeah, so when we look at the whole average, we see that it is 23.5. So this means a left bias in the vast majority of the data. So as a result, we could say that there is a slight right skew. You follow? So why don't we just continue? I'll choose a random variable. For example, we'll examine horsepower. So its minimum value is 46, maximum value is 230. So the average of these two values is 138. When we look at the general average, it's 104. So again, the overall average remains on the left. So it means that the left side is dense. Therefore, we could say that this variable is moderately skewed to the right. And yeah, as you can see, we can get information about the distribution of the variables in the data set from basic statistics. But now, I'm going to ask you to pause me, well, pause the video anyway, and comment on the other variables, just like this, okay? I'm waiting for you. Go ahead. But now I'll continue the lesson, and we'll see what happens, see what you got. Now, those of you who actually stopped the video, great. You started it up again. Yes. If you didn't, and you're just hearing me ramble on like this, let's get back to it. So I want to move on to the data pre-processing part before moving on to modeling. So what we'll do is a detailed research on this data. Okay, so again, we're going to write the headline. So I'm writing data pre-processing. And I'm putting a double star at the beginning and the end. Okay, so now let's continue with that. We'll examine the missing values in the data set. Now, you may remember that with the info method, we saw that there were 6 missing values within the horsepower variable. So I want to prove it to you. So look here. If I say df.isNull, well, this code's going to ask if there are any null values in the data set. Present yourself, right? So now let's ask for the sum of these values. So I'll come to an end and apply this sum function to it. Now run the code. Okay, so as you can see, we can see the total number of missing values in the horsepower variable. Now, let's say you want to see the empty values in the variable. So see, I'll just say df and open square brackets. Now I want to show you how to do fancy indexing. So if I say, yeah, see how fancy, df is null again in parentheses, and this time I'll apply the any function on it, and I'll set the axis parameter equal to 1 within. See, so with this function, if there is at least one empty value in the column, it will give us an output. Right, so this code will bring us all the missing lines in horsepower, as there are no missing values in any of the other variables. Okay, so let's run the code. So looky here, it brings us all the lines with null values in the variable. Yeah, so you can see there are 6 lines in total. I did specifically call this data frame structure because now we're going to choose the method to apply to these null values. So yeah, I would like to drop all blank lines, as of course there won't be any significant data loss, right? Now, for those among us who want to, can put the mean or median value of the variable into these null values and then continue. But what I'm going to do is I'll say df.dropNA, set the in-place parameter to true, run the code, and now you can see how the null values are dropped. So we'll double check to see if there are any null values. So if I say df.isNull and apply the sum function on it, and now I will apply one more function, this code block, I'll say any. So yeah, in this code, if there is even one null value in the data frame structure, it will output true. Otherwise, it'll give us a false output. Okay, so let's run the code. And there you go, my friends. We've got the false output. So that means no more null values. So now let's have a look at a new shape of the data frame structure. So this new shape will appear when we just say df.shape. Let's run the code. Okay, so as you can see, the number of lines has decreased to 392. Okay, so that is the first part of our lesson. Good job. I want to end it here so that it doesn't go on any longer, but then we'll continue with this in the next one. All right, so see you next time. All right, well, hello, my dear friends. Welcome back. So yeah, we finished the pre-processing part of our data previously, right? So now we're going to continue just right from where we left off. So within this context, what we're going to do is start exploratory data analysis. Now, as you may know, we examined the data set in the previous lesson, so now we're going to explicitly discuss the variables in this data set. So we're going to get started with a univariate analysis. So I'll open up a cell in Markdown format and write univariate analysis. Make sure you put the double asterisk at the beginning and the end, and run the code. So what we'll do is examine the cylinders variable. Now, I want to see the unique values of this variable. So I'll say df cylinders and apply the unique function to it. And we'll run the code. All right, my friends, a variable consisting of 5 different values. Now, aren't you wondering about the numbers of these 5 observation values in the variable? So let's say df cylinders again and apply the value counts function on it and run the code. All right, so as you can see here, the total number of observation values are displayed separately. Okay, so I do want to draw your attention to one particular point. Now, as you may know, the presentation of your work is critical, right? So we can perform univariate analysis just like this directly on numerical outputs. However, I would like to present this study a little bit better by using some visualization techniques. So with that in mind, what we're going to do is visualize data here, and we'll do the analysis. So let's get started with that. First, I'm just setting the size of the image that we're going to visualize. So I'll say PLT point figure, and I'll set the fig size parameter to 15 by 8. So now let's start creating the graphic. I'll say SNS.countPlot. Variables with low observation values can be visualized with a count plot. Okay, so now I'm placing the variable in the count plot. I'll say df cylinders. I'll continue with setting the data parameter as df. For the colors of the bars in the image, I'll just equate the palette parameter to cube helix. Okay, my friends, you can change this parameter with any argument that you want to. I just set it like that because, well, cube helix kind of makes sense for this graphic, but I've got that in my mind. You don't yet. And then finally, I can say plt.show. See, so now everything's ready, and we'll run the code. All right, so here's the graphic. Now, the data looks better. But from this graph, we can see that vehicles with 4 cylinders have the highest observation value. And you can also see the order of the other values on the screen. The vehicles with the smallest percentage are those with 3 and 5 cylinders. But to conclude this idea, 98% of the cars in the dataset belong to vehicles with 4, 6, and 8 cylinders. Yeah, so I'll just make a note of that, about this particular variable. And we're going to call the data frame structure again, so I'll say df.head. Yeah, so now I want to examine the variable model year from the variables. Now, have you noticed the model underscore year variable used the last 2 days of the year that it was in? So 70 instead of 1970 is written in the dataset. Now, for clear understandability, I need to fix that before I do the visualization. So what I'll do is first call the variable. So I'll say df model year equals. Now I will add the number 1900 to all the values in the variable. So the year variable will take the shape that we want. See, so I'll open up parentheses and say 1900 plus. Call the model year variable again. And let's run the code. Okay, so call the data frame again. And as you can see, the year variable is in the format that is more acceptable. It's certainly the format that I want anyway. So we're going to visualize now and analyze it. So I'm taking the above code, copying it below. That makes efficient coding. So here I am changing the name of the variable. I'm going to make another small change as well. So this time I'm going to set the palette parameter to be rainbow. As you know, this parameter changes the colors of the bars. Okay, so now that that's ready, we'll run the code. All right, so have a look at this. The model years of the vehicles are now up on the screen. We can analyze it. The majority of the vehicles in the data set are from the model year 1973. And the year with the most negligible value happens to be 1973. So yeah, so the rates of the other years are more or less similar. So make a note of that and continue. We'll examine the origin variable. So this variable determines the origin of the vehicles. Okay, so I'll use the count plot again. Now, so as to not waste any time, I want to just grab that code from above, copy and paste. Right, so I'm just changing the name of the variable, and let's run the code. Now, here's the chart. So according to the graph, considering the origin of the vehicles, well, it's seen that the United States is the most common. It's actually, according to the graph, wow, almost 3 times the size of the other 2 origins. So the other 2 groups seem to be very close to each other, right? One is Japan and the other one's Europe. Okay, my friends? So just make a note of that in this variable and we'll continue. I want to examine the horsepower variable. Now, you do remember this variable had an important place in terms of engine performance. So as we continue, when we examine the basic statistics, we made the comment, there is a right skew in the horsepower variable. So I want to just check together whether this interpretation is actually correct. So this time I'm going to use a dist plot chart. So what I'll say here is SNS point dist plot, and I'm writing the variable into it. I said df horsepower, and I'll say plt.show to get a decent view. All right, so let's run the code. Okay, so what you're looking at here is we see a graph that fits our analysis. Now there is a tail to the right, and most of the data is over here on the left, so there is a left skew. So if we examine the values, most vehicles have 70 to 110 horsepower. Now there's a sudden increase in the region where there are vehicles with 150 horsepower. The reason for this can be investigated in binary analysis. But for now, we'll continue. Especially after 200 horsepower, there's a decrease in vehicles. So now let's have a look at the displacement variable. Now, you know, this variable was about the engine displacement. And I want to use a dist plot graphics again. Now I'll just grab the code from above to avoid having to, well, just take up too much time here. So I want to paste it in, and I will change the name of the variable. And I'm going to run the code now. All right, so have a look. We can now say that it has a left skewed variable. So if we examine our values, we see that the volume of the motor is generally between 100 and 110. But after 200, there's a decrease, even if it's partial. Okay, so make a note of this variable, and that wraps up our univariate analysis. But yeah, you see, in univariate analysis, the characteristics of the variables individually are examined, right? So the observed changes on the graph are sometimes not fully explained because, well, these changes may be related to another variable. So we typically would do bivariate and multivariate data analysis while performing exploratory data analysis. But that's all part of what we're explaining and learning, okay? So right now, let's do some bivariate analysis with that in mind. And what we'll do is examine the issues that we had some questions about, right? So we'll first write up a title, open up a cell in Markdown format, and write bivariate analysis. And I'll put that, of course, in double asterisks, both sides, and run the code. Okay, cool. So now we can start the binary variable analysis. Now, for the target variable, MPG, I will examine the relationship between MPG and other variables. So in this context, I will use the box plot graphic. So as we get started, we'll make our first graph to be this relationship between the cylinder and MPG. So I'll just, first off, adjust the size of the graph. So I want to say plt.figure and set the fig size parameter to 15 by 8. Okay, so we'll start coding the graph now. I'll say sns.boxplot, and I'll write in the variable that will take place on the x-axis, and x equals cylinders. And then I'll determine the y-axis. I'll say y equals MPG. Okay, so now to set the data parameter df and the palette parameter to spectral. I wonder if you notice, see, I'm trying to use different palettes in the graphics so that you can see the difference in the palette without having to do a whole, thing on them. Figure you can pick it up as we go along. Anyway, just finally write in plt.show. All right, so everything's ready. We'll run the code. And let's have a look at the graphic. Now, what immediately catches my eye is that the 4-cylinder vehicles have the highest MPG values. So yeah, the MPG value decreases as the number of cylinders increase, right? So the number of cylinders with the lowest MPG value is 8. So sure enough, the lower the MPG value, the more fuel the vehicle will consume. So then it follows that cars with a lower MPG value would be more fuel efficient. All right? So let's have a look at something different now. For example, does the model year affect the MPG value? So we'll use the box plot again. And what I'll do, in order to save on some time, I'll just take the box plot code from above and paste it down here below. Now here I'll change the variable x. So I'm doing model year. Okay, so that's the code. Let's run it. Yeah, so as you can see, we've come across some pretty exciting data here. So as the years increase, the MPG values of the vehicle increase with the newer models. So yeah, I'm going to make some notes of that. So see, that's how we do this binary variable analysis. And those of you who wish to examine the relations of different variables with each other can do it like that on your own. I want to show you, though, how to do a multivariate analysis. So we'll continue forward. So what I want to do is specify more than 2 variables and see their relationships with each other. So let's just write in a title in Markdown format. And I'm just writing multivariate analysis. And I'll put in a double star, of course, at the beginning and the end. So we'll run the code. And now we can move on. So yeah, by looking at the effective horsepower on MPG, I want to see the differences in this effect by country. So if I were to use the type of graph called IMplot for this purpose, I'll call IMplot from the Seaborn library. Now I'll enter the parameters inside, so I'll type x equals horsepower to see horsepower variable on the x-axis. And I'm writing y equals MPG for the y-axis. Now, remember I said that there would be a 3-variable analysis, so I'll add a 3rd dimension to the chart, and I'll set the hue parameter to origin. Okay, so now we've defined our variables. I want to set the data. So I'll say data equals df. And finally, I'll set the palette parameter to be rainbow. And finally, I'm writing plt.show to make the output look nice, right? So let's run the code. All right, my friends, there it is. However, I think, looking at it, there are some minor problems. Can you see? Well, some values may be outside the x and y axis because some values appear halfway. So what do you suppose we're going to do about that? Yeah, we can define the boundaries of these axes. So let's actually do a little more work with this graph. See, I'm going to assign all this visualization code to one variable. For example, let's call it a graph, okay? Yeah, so now we can perform operations on the variable that we have determined. So first up, I will determine the boundaries of the x-axis. So you see I'm writing graph and applying the set function. And I'll write in here xlim parameter, and that'll be able to set the limits between 0 and 250. Yeah, so that way I think the values will stay in the range. Okay, so we'll determine the y-axis now. So I'll say graph and apply the set function on it. And I'll write the ylim parameter, setting that limit between 0 and 50. All right, so now let's see what that looks like running the code. Okay, So that's a better shape that we might want. So yeah, let's focus on the graph now. We can see the countries represented by the colors on the right. In cars produced by all countries, the MPG value decreases with the increase in horsepower in general. But the softest reduction occurs in countries originating in the United States. The number of vehicles based in the USA was much higher than the other two groups. Therefore, if we evaluate the other two groups among themselves, we might reach a more accurate result. Yeah, so when we interpret it like that, we can say that the decrease in the MPG value of Japanese and European cars is pretty much the same. All right, so make a note of that, and let's continue. So I want to now examine the relationship between acceleration and MPG by country. And again, to, save a little bit of time here, I'm going to just grab that code from above and paste it on in. I'm only going to change the values from here. So I'm going to set the X variable to be acceleration. I'm also deleting the border code on the X-axis below, because this interval might be just a bit much. Okay, so now everything is ready. Let's just run the code. All right, so let's have a look at this graph. Yeah, so the y-axis comes to this format that we want. However, we do need to correct that x-axis, huh? So for this, I want to say graph and apply the set function. I'll write the xlim parameter, and we'll set it to be between 5 and 28. Now, of course, you can change these values as often as you want to, according to whatever your convenience is. It's not going to be very scientific, right? You just do what you need to do. You can always play around with these values until you get the most suitable image, whatever you're looking for. Okay. That's for you to decide. I want to run the code now. See, now look at this. That's a much more doable shape, right? That's what I was looking for. So I want to perform the analysis. So according to all the different origins, as the acceleration of the vehicle increases, the MPG value increases. So we could say that there is a correct ratio. So the increase in MPG due to acceleration occurs in cars of European origin at the lowest. So you see the acceleration angle of the line is a little lower. However, when you look at it in general, the MPG values for acceleration in vehicles of the US origin are lower than those of other origins. Therefore, the US-based cars seem a bit more advantageous when the MPG relationship is examined according to the acceleration. All right, so make a note of that, and we'll move on. So having a look at the relationship of weight to MPG, and we'll analyze that by country. And again, to save a little time, I'll just grab the code from above and paste it in below. And here I'll just change the X variable. Now, since I don't know the axis limits, I'll just delete this part. And we'll run the code. So having a look at the graphic, yeah, I'd say some minor adjustments are required. So I'll go again and get this code and paste it here. Okay, so y-axis is going to stay the same. And I'm going to make changes to the x-axis. For example, let's say between 1500 and 5500. All right, so we'll run the code. All right, so the visual is a little better now. That'll give us a chance to start our analysis, yes? So you see here, my friends, after the value of 3500, there is no increase in the weight of cars of Japanese or European origin. Now, the vehicles originating in the US can weigh up to 5200. So as the weight increases, the MPG value decreases according to these three groups. Okay, so we'll make a note of that. And now we can carry out our final study within the scope of multiple analyses. And what we'll do is examine the relationship between engine volume and MPG and evaluate it according to country. So within this context, I can just take that code from above and paste it in here, and I'll change the X parameter. And again, I'm just going to delete the code that we wrote for the x-axis below. All right, so let's run the code, see what it looks like. There's your graphic. Yeah, we're going to need to make a slight adjustment again. So I'll just write in the graph below and applying the set function. And I'm going to set the xlim parameter to, let's say, from 0 to 475. Of course, why don't you go ahead and play around with whatever parameter that you want to put in there. But whatever it is, just rerun the code. And here's my graph. That's a much more doable shape. Sure, so when you look at it, the MPG value decreases when the engine volume increases, and that's compared to all countries. So in general, after the value of 180, there's no increase in the engine volume of European and Japanese cars. According to the increase in engine volume, the MPG decrease occurs in the most complex European origin vehicles. So you see the very steep slope in the line, don't you? Yeah, so just make a note of that as well. All right, so that wraps up our analysis. What I'll do is I'll go ahead and add all the conclusions that we have made right into the notebook after the lesson. But I want to see you in the next one. All right, so see you then. All right, well, hello, my dear friends. Welcome back. We've performed an exploratory data analysis considering our previous lesson data set. All right, so right now I want to perform, well, the last part of the modeling prep. By determining the variables that we will enter into the model, we will convert all the variables to the format that we will enter into the model. Make sense? Well, let's get started without wasting any more time, and you'll see how we go. So I do want to use the heat map graph, and this will be able to visualize the relationship between the variables. I want to examine the correlations between the graph and the variables. So first, we'll write up a title. I'll open up a cell in Markdown format and write heat map of correlation matrix in it. I'm putting a double star at the beginning and the end. Run the code. Very good. So first of all, I want to determine the size of the image. So I'll say plt.configure. Set the fig size parameter 15 by 9. Okay, so let's code the graph. I'll say sns.heatmap. Now I'll need to enter the value that I'm curious about. It was the correlations of the variables, yeah? Yeah, so I'm typing in df.core. Okay, so now I want to adjust some parameters just to make it look a little bit better. So I am setting the anot parameter to true. This will print the correlation coefficients on the graph. Now I'm setting the line width parameter to 0.5. You see, this parameter will open the distance between the frames in the graph. Finally, I'll set the CMAP parameter to spectral. And this is what allows us to adjust the color of our graph. So now I'll go down to print the graph correctly and say plt.show and run the code. All right, so that comes out. See, the correlation values between the variables are apparent. So now let's perform our analysis. So let's focus on the MPG variable. All the other variables except acceleration and model year variable are inversely proportional to the MPG variable. So in other words, while one side decreases, the other side increases, or vice versa. The variable with the lowest correlation with MPG is the variable acceleration with a value of 0.42. Now you see, since the correlation is low, I don't really think that this variable is going to affect our MPG variable in this model. So maybe after the analysis, I'll just remove that variable from the data set. Now you see why. Okay, let's continue. Now the strongest correlation with MPG is the weight variable with a value of negative 0.83. Yeah, so this variable will be instrumental for us when estimating the MPG variable. And we can see the relationships between the other variables on the graph. Now, the subject that we're going to focus on here looks like this. If there are variables that have too many correlations with each other than MPG, we will remove one of them from the data set. See, because if there are two highly correlated variables with each other, it means both have the same power to predict the MPG variable. So there's really no need to complicate the model by unnecessarily putting both of them into the model. So if we focus on the displacement variable in this context, there's a correlation of over 90% with three variables in general. So in other words, these three variables provide the same benefit in explaining the MPG variable. So I could also remove the displacement variable from the data set. So you see how it works. Now, of course, you might be wondering in the back of your mind, or maybe you might shout it out loudly, hey, wait a minute, couldn't that actually harm the model if we remove the variables? Well, my friends, good question, and it might be harmful in minuscule proportions. However, our primary goal, remember, is to make the highest estimation with the least variable. So that means we don't give too many variables to the model, and that way we prevent overfitting. Remember the overfitting situation? So yeah, in this context, I'm going to end our analysis, and you'll see what I mean later. But I will now apply the conclusions that we've now drawn from this analysis. So, what was I saying before you interrupted me with that brilliant question? We need to remove acceleration and displacement from the data set, right? See, so if I say df.drop and write the variables that I want to reduce in order, to say acceleration and displacement, then I'll set the axis parameter equal to 1 because I want to reduce it on a column by column basis. And then, of course, to make the changes permanent in the data set, I'll set the in-place parameter to true. Now let's see what happens when you run the code. So now we'll call the data frame structure again. I'll say df.head. And look at this, exactly what we wanted. So now, what exactly are we doing now? We are trying to make the variables in the data set suitable for modeling. Yeah. So for now, I want you to focus on the model year variable within this context. Now, I wonder if you notice this variable is the year variable. And if we want to include this variable directly in our model, we can try the model because the concept of size in years. So what does that mean we should do? Well, I want to do feature engineering. So I wonder if I can create a different variable using the model year variable. And something like this could come to mind. Let's create a new variable. We'll make the name be age. And if I subtract the model year variable from today's date, I can actually find the age of the vehicles. Okay, so I want to apply this now. So first I will find today's date. For this, I will import the datetime library. So I'll say from datetime library, import datetime. So by using this model, we will reach today's date. Now I'm going to go down and create a new variable, and we'll call it today. And I'll equate this variable to datetime.today. I'll use the today module from the datetime library. Okay, so let's run the code. So now we can call the variable, and I'll say today. And there you get the info. So this info is up to date, right? The very first element that matters to us is the year. As you can see, it's 2022. And I'm going to use this year now. And I'll be creating a new variable. I'll say this underscore year equals, and I'll equate this variable to the expression today.year. So this expression will take the year from today variable above, and let's run the code. Yeah, my friends, so we didn't write the number 2022 directly, right? Because we have to rerun the code after the years have passed. So I want the year value to be up to date. Yeah, so we can create a new variable since we have reached the year value. So I'll say df age equals, then I subtract the df model year, which is the variable, right, from this year variable. Now let's run the code. And now we can drop the model year variable from the data set. Yeah, so I can say df.drop, right, the variable that I want to drop. So I'll say model year. And I'm setting the axis parameter to 1 and in-place parameter to true. Let's run the code. Now we can call the data frame structure again. And there you go. That's what I wanted. So what are we going to do now? Well, we'll work on one last variable. Which one? The origin variable. Yeah, so let's get the unique values of this variable. So first, I'll call the variable. I'll say df.origin and apply the unique function on it. Let's run the code. Okay, so as you know, we've got 3 values. I wonder if you've noticed these values are categorical. So that means that we'll need to convert these values into a language the model will understand. Now, what? Yeah, we can just apply the getDummies method to the origin variable. And that way, the values in the categorical variable will turn into 0 and 1s. So you see, I'll call the data frame and say equals. Now we'll create a new data frame structure. So I'll say pd.getDummies and place the data frame inside. Yeah, I almost said get gummies, but that's on my shopping list. Anyway, the categorical variable in the data frame structure will be exposed to the getDummies method, and the transformation will occur. So yeah, as a result of this method, one column will be extra. So I'll reduce this extra column. I can just change the drop first parameter to be true. Cool. So now everything's ready. Let's run the code. We can call the data frame structure again. And look at that. Looks pretty good, huh? Data frame turned into the shape that we want. So we can now move on to modeling with these variables. So I'm going to write up a title first. I'll open a cell in Markdown format, writing modeling in it, putting, of course, double asterisk before and after. Run it. Cool. So now we can move on to our coding. But what do we actually do now? Well, first we'll define 2 variables. One of these variables will consist of independent variables. The other one will consist of our dependent variable. That's the prediction variable. Okay, so let's let the name of this first variable be x. I'll say equals. Now I will bring the independent variables into this code, and I can achieve my goal if I remove the MPG variable from the entire data frame structure. You see, if I say here df.drop and write MPG into it, then I'm setting the axis parameter equal to 1. All right, so now the x variable is ready, and the order is in the other variable. So, of course, we'll let this be y. I'll say it is equal, and here I'll call the predicted variable by saying df mpg. Okay, so the variables are ready. Let's run the code. Yeah, so now we got to divide these variables into test and train sets. Now, while we train the model with train, we'll test the model with the test. You remember that from before. So how do we do this division? with the train test split function. So what I'll do is I'll call this function from sklearn. I'll say model selection, call the function by saying import train test split. All right, my friends, so we've got 4 data groups that come out of our train test split function. And I will create a separate variable for each of these. So you see I'll use the most common variable name, so I'll say x_train, x_test, y_train, y_test, and I'll say equals. Now I'll call the function. You see, so I'm writing the variables that I want to split inside the function. So I'll say x and y. Then I'll need to specify the size that I want to divide as a percentage. So that's why I'm setting the test size parameter to 0.2. So this code will divide 20% by 80%. All right, so we'll continue. And what I'll do is set the random state parameter to 42 to see the same split. Now, of course, you can play around with that parameter value as you wish, but I just made the most frequently used one. All right, so now that everything's ready, let's go ahead and run the code. All right, so you see the split took place. Let's have a look and see how the split happened. For example, I'll call xtrain. See, so it randomly split the x data. So I'm calling up ytrain. And as you can see, it's also been divided randomly in the same way. Now, of course, you can go in there and control other variables if you want to. But you see, now that you know this, that wraps up the 3rd lesson of our series. So next time, what we'll do is linear regression modeling to complete our linear regression lessons with Python. So go back, have a look, maybe make clear something that is still a little fuzzy, but I want to see in the next one because we're going to have some fun. All right, see you then. Well, hello, my friends. Welcome back. So in this lesson, we're going to end our linear regression lessons with Python. But right now, I want you to make sure that you understand we have now made the data ready for modeling, right? So in this lesson, we're going to create our machine learning model. So we're going to get started here without taking any more time. I want to import the library. So I'll say from sklearn.linearModel, import linear regression. So let's run the code. Yeah, so as you can see, the linear regression module has been imported. And now we can start building our model. So first, I want to create the model object. So I'm specifying a variable name. For example, let's say model. I'll say equals and equate this variable to the linear regression function. Now let's run the code. As you can see, a linear regression object has now been created, so we can work with this object. First, we'll train our data. Now for that, I'll just call the model object and apply the fit function on it. So I'm putting the training set data into it, and I'll say xtrain and ytrain. And now run the code. And as you can see, the model is now trained. Now, I wonder if you remember when we talked about the theory of linear regression, we studied a particular mathematical formulation. Now, the formulation contained coefficients and residual values, namely the intercept value. Yeah, so now that we've created the model, we have the linear regression formula. So now let's see the coefficients and the residual value together. So first, we'll have a look at the residual value, the intercept value. So we're going to use the intercept underscore function for this. Yeah, so I'll call up the model and apply the intercept underscore function. And run the code. All right, so here you see the value 78.24 has appeared. Okay. Now, it means that while all the variables are 0, the y value is 78.24. Now, let's have a look at the coefficients of all the other variables. So if we use the coef underscore function, we can now use the data frame structure because I want the output after applying this function to, well, look presentable. So first I'll create a variable. Let coef param, and I'll say equals, I'll say pd.dataframe to create a data frame. Okay. Now let's write the function suitable for this purpose, and I'm calling the model and applying the coef function on it. So all the values in the data frame structure will be the coefficients of our arguments. Yeah? Yes. So let's continue. I'll equate the index parameter to the variable x column names, and I'll say x.columns. And moving on, I'm setting the column parameter as coefficient. All right, so now that we've created the data frame structure, let's call up the data frame again. So I'm running the ready-made code. And as you can see, the coefficients of the independent variables in the model came from the data frame structure. Okay, so what are we understanding from this data frame structure? Let's have a look one by one. So my friends, what we're looking at here is the coefficient of the cylinders variable is 0.20. So it means that a 1 unit increase in the cylinders variable creates an increase of 0.20 in the MPG estimation variable. You got it? So we'll continue. The horsepower variable, look at this coefficient. An increase of 1 unit in the horsepower variable affects the formula negatively. Minus 0.015 is a decrease, right? Yeah, so you can see how to analyze other variables like this, right? The point that draws attention here to us, though, is the coefficient of origin USA. That's this variable right here. This affects the formula the most. So an increase of 1 unit in this variable causes the MPG variable to decrease by minus 2.38. That's the negative direction. So yeah, this gives us the opportunity to see in practicality the coefficients that we were talking about theoretically. Now you might be wondering about the accuracy. Really, I mean, how accurate is this model that emerges according to these coefficients? Well, I want to show you how to check it. So first, we will test the model using the test data. Now, I'm creating a variable for the prediction. I'll let it be ypred. I'll say equals, and I'll call the model. I'll use the predict function to make predictions and insert the test data into this function. So I'll say xtest and run the code. All right, my friends, you see our model has now made the prediction. So we can see the success of our model just by looking at the evaluation metrics. What do you think? Now, I would like to do one more study before this evaluation. So I want to see the actual and test data that we have side by side. And that way we'll be able to see how much difference our model made in the predictions. Okay, so to do that, I just want to set up a data frame structure again. This time I will create a data frame using a dictionary structure. So that means I'm creating a dictionary. I'll let it be called myDict. And I'll say equals, and I'll open up the square brackets, and now I'm going to create a key and value pair. So first I'll say actual for the actual values, put a colon, and then I'm setting the corresponding value for this to be ytest. And we'll continue. So I'll generate a key named pred, set the corresponding value to be ypred. Okay, so now the dictionary's ready. I need to create a data frame from this dictionary. So I'll set a new variable. I'll let it be called compare. I'll say equals, and for the data frame structure, I'll say pd.dataframe. I'm putting the dictionary in it, and let's run the code. All right, so you see the data frame has been created. So now I'll call the variable. I'll say compare.sample and write 10 into it. And the code will return 10 random values from the data frame structure. Okay, so run that code. Okay, so there you go. It's great. Actual and prediction data are shown here. Actual values in the first column data set. The second column is the values predicted by the model. So now by looking at this table, we can see the performance of the prediction outputs of the model concretely. Yes. So let's evaluate this performance that we see now through metrics. We can't just, take your word for it. The metrics that we need to use for this are mean squared error, mean absolute error, and R2 score. That might be ringing a bell from the very beginning. So now we'll need to import them, of course. So in this context, I am pasting the import code here to save a little bit more time. And as you can see here, my friends, we'll just import these metrics from the metrics module of the sklearn library. Now, isn't the function of each metric according to its name? Yes. All right, so see that. We've imported the metrics. Now we can apply them to the model. Okay, so all of these metrics usually take the actual data as the first value and the forecast data to be the second value. But now instead of writing them separately, I'll just create one function. See, that way we'll be able to correctly output all the metrics at once. So now we can start creating the functions. Okay, so I'll say def and give the function a name. We'll call it evaluation metrics. So I'll now enter an argument for this function. And of course, I'm going to want it to take two arguments. So I'll write actual and pred. And we're going to use these arguments in a moment. I'm just going to go down to the body here. Now I'll write the metrics one after the other. All right, so first of all, I'm creating a variable for the mean absolute error. So I'll say MAE equals, and I'll call the function. And I'm putting the arguments we wrote above it. I'll say actual and pred. Yeah, so you see, that's our first metric, and now it's ready. We'll move on to the other. So I'm creating a new variable. I'll say MSE equals, and I'll equate that to the mean squared error function. And I'll write the arguments in order. So I'll say actual and pred. And we'll move on to the root mean squared error metric. So we'll let the variable name for this metric be RMSE. I'll say equals. And do you remember this metric was the square root of the mean squared error, right? So in this context, we'll just call the square root function, sqrt, for the square root from the NumPy library. So that means I'll write mean squared error function inside this function. Now, you see how I'm taking it from here and then pasting it in below. Okay, so we've got our three metrics. I do want to create the final metric, though. You see here, I'm creating a new variable, and we'll let the variable be named score. I'll say equals. Then I'm calling the R2 score function. I'll write the arguments in it. I'll say actual and pred. And now we've got all of our metrics prepared. So I need to finish out the function. So I'll say return. And of course, to make the output look nice, I'll be adding in this statement to the function. Okay, so my friends, all the metrics will be written under this statement. And now we can run the code. All right, so now our function's ready. We can call on our function and put the arguments in. So I'll say ytest for actual. For pred, I'll say ypred. And let's run this code. Okay, all of our metrics are here. The R2 score value of our model is 0.78. And what was the R2 score? It was the power of the independent variables to explain the dependent variables. Isn't that right? The ability of the independent variables to explain the dependent variables. You remember that. So 0.78 is a pretty good value. Yeah, so we also see that the MAE value is 2.51. Now, low MAE is something that we want. Okay, so a value of 2.51 can be considered a good value. So yeah, the MSE and the RMSE values are also here. Now this metric interests me the most. Between these two is the RMSE. You know why? Well, if you remember, this metric was punishing the model a little bit more. Therefore, I can prefer this metric to MAE and MSE. Right? So we said that the R2 score value is also essential for us. It gives us an accuracy of about 0.78. And we saw this numerically. So now, don't you want to know the model predictions visually? So for this, I want to use the yellow brick library. What? You haven't used that before? Oh my gosh. My friends, this library is a beautiful library that allows for wonderful visualization on a variety of subjects. So I've included this section in the curriculum for awareness and innovation. You don't have to be as enraptured as I am with it, but it's all right. I want to take you through it pretty quickly, though. So if you are working with this library for the first time, just, install it in the environment that you're working in. Or you could just sit back, relax, and watch me do it. But anyway, the installation code on the computer is as follows. You have to say, !pip install yellow brick. Yeah, so I'm not going to do this again because I've already got it installed. But that's why I'll just come up here to the beginning and put the comment mark. So hopefully you've installed it in your environment if you choose to, and we'll continue from here. So first I want to import the library that we want to work on. So see here, I'll say from yellow brick.regressor. And this way I can import the function that is our aim by saying import prediction error from there. So let's quickly realize our purpose. First, I will create the visualization object. So I'm specifying a variable, let it be called visualizer. I'll say equals, and I'll call the prediction error function. I'll place our model in it. Okay, so now we'll work on this object. First, I'll train the visualization object. So you see, I'll say visualizer.fit and place the training sets within it, respectively. And I'll continue, and right now I'll call the metric. I'll say visualizer.score. This time I'll put the test data in it. And then finally for the image to output, I'll say visualizer.show. And that makes everything ready. So let's run the code. So you see, my friends, that looks great. Now, if you look at the graph's title, it says linear regression prediction error. So below there are two lines. The black one is the best line to be, and the other is the line of our model. Okay, we'll continue. The x-axis is the actual value. The y-axis is the estimated value. So yeah, you can see the score result on the graph, and you can see the predicted points here. So you see why the visualization is quite significant, very helpful. Now, if you do want to learn the details of this kind of visualization, just go back and review the Yellow Brick Library's documents. We're not going to get into that here. But like I said, I included this image in the curriculum just for your awareness and your innovation. And those of you who want to go into the details, yeah, go for it. Just not on my time. Joke. Okay, so I want to show you how to make another visualization like this, and then we can wrap up the lesson. So this time I want to provide a visualization of residual values. So again, in order to not spend too much time, let's just grab all this above code and below here, paste and just change the function name I will use in the visualization. So you see how I've made residuals plot. Now I'm also going to correct the function name from the bottom. Now my friends, everything else is going to be the same, so I can just run the code directly. Hey, look at that. That's pretty good visual here, right? So the green ones are the test data points. The blue ones are the training data points. And then if you look at our model, especially after the value 23, well, a scatter occurs in our estimates. So you can see the distribution of estimates and actual values on the far right. Now, there is another point that I want you to pay attention to when you're training and testing accuracy values. If the difference between these two values is too great, obviously that's not something that we're going to want, right? If the difference between these two values is too big, this is definitely something we don't want. So there's an overfitting situation if the test data is too low, is lower than the training data. You see that? So yeah, for this example, there's very little overfitting here. I'm just telling you about speculation. It might not be considered very important in this case. But that's all for now. We are wrapping up our linear regression lesson. So I'll see you next time. Well, wouldn't you know, it's already next time? So hello, my dear friends, and welcome back. So in this lesson, we're going to examine the concept of bias-variance trade-off, which is really one of the most frequently encountered concepts in machine learning. You might have already heard of it, but let's just get started without taking any more time, because I want to show you this on the screen here. We are going to work this lesson through this picture. However, before we move on to our main topics and analyze a graphic in the picture, I just want to start by explaining some of the terms that you may be looking at right now on the graph. So first of all, just want to remind the training and test data set concepts, right? So as you know, the section studied for the model in the data set is called the train, and the data reserved for observing how the model works, this is called test. So remember, I've talked about the concept of overfitting before. So we can understand overfitting in a model by the difference in accuracy between train and test. So because the model we trained on the training data set memorizes the data, the result may be irrelevant when there's new input from the test data set. So in that case, there is excessive memorization, and that's why the situation is called overfitting. Okay, so yeah, there's an opposite situation. We can examine now the concept of underfitting. So underfitting, you might imagine, would be the insufficient or incomplete learning, the state of not being able to learn. So in other words, if the accuracy of the results is low when measuring the model's power in the trained data set, we can say that there is an underfitting situation. So with all that in mind, we'll consider now the concept of bias. So bias is the value that reflects the distance between the estimated data due to modeling and the actual data. Yeah? So finally, we'll examine the concept of variance, and we'll put it all together, don't worry. So variance is the variability of the model estimate for a given data point or the value that shows us how the data is spread. All right? So the relationship between bias and variance is going to give us some clues about the validity of the machine learning algorithm created. Yeah, so that's all the concept for now. Let's interpret the graph. So once you have a look, and you can see the x-axis variance and the y-axis bias represent the error value. So this upper line represents the test error. The lower line represents the training error. Now, as you may have noticed, the test and training data set errors are very high at first. So in that case, an underfitting situation could be observed. But as the variance increases and the number of variables entering the model increases, the errors in the training and test data set decrease, and thus the bias value decreases. Now, there is an optimal point for training and test error. This is the optimal point for our model. Okay, so training and testing errors are in balance at this point. So the model starts to memorize as the variance in the data increases and the complexity of the model increases due to the rise in the number of variables entering the model. Okay, so in this case, naturally, the training error decreases because the model has started to memorize the training data. However, if you've been paying attention, the model will make a lot of errors while testing. And this is where overfitting occurs. Now, like we said earlier, the most appropriate point is when the concepts of bias and variance are in balance. And that is a place that we call the best model in the chart. All right, my friends, that's the general logic anyway. Okay. So I do want to give you a new example so that we could perhaps understand the subject a bit better. So you see a new picture on the screen. Now here, the left side represents low variance, the right side represents high variance. And again, the upside represents high bias, the downside, low bias. And accuracy increases as it gets closer to the center of the circles. So you see the innermost circle represents the accuracy point. Each nested circle represents the degree of dispersion. So yeah, starting from here, we can actually examine underfitting and overfitting situations for supervised learning. Now for model, we can say that there is underfitting when the bias value is high and the variance value is low. The underfitting situation arises because the algorithm to be trained cannot model the underlying pattern in the data set, right? Now, this situation may occur either because there's insufficient data to be trained, or a linear model is trying to be established using nonlinear data. So yeah, you might want to prevent that. So how can you prevent that situation from cropping up? Well, the correct algorithm has got to be built with the right data to solve this. I mean, end of story. But yeah, the other case is, though, if the bias value is low but the variance is high, that's when we can talk about overfitting. So here, the model learns all the differences in the data pattern and memorizes the values corresponding to the observations in the target variable. And in this situation, it'll indicate that there is no clean data in the training set. See, the differences in accuracy rates between the train and test data set indicate overfitting. So overfitting may be encountered for complex models such as decision trees, k-nearest neighbors, and support vector machines. So yeah, when we look at the picture, the way that I would want it to be is the figure over here on the bottom left. Estimates accumulated precisely at the point of accuracy. There's low variance, low bias. See, variance and bias are a trade-off. So then doesn't that just conjure the question, how to set up a bias-variance trade-off? Yes, great minds think alike. So if the number of variables we include in our model is few, well, we probably have a high bias and low variance value. So in this case, it's necessary to increase the variables in the model to an appropriate extent. Now, on the other hand, our model will have low bias and high variance value when we have many variables. So in that case, we should actually resort to methods that will reduce the number of variables as much as possible. Because, yeah, there's a high risk of overfitting in just about any study that I can think of off the top of my head, just generally speaking. Okay. The danger of underfitting is actually less common than overfitting. Well, then, certainly the question arises, if we do encounter this overfitting problem a lot, what are some of the methods to prevent the problem? Well, I'm glad you asked, because there's a few things that I want to talk about, and we'll take this in order of solution. Okay, so the first method would be cross-validation. Now, my friends, in this method, the model must be trained by taking different sections from the trained data set. So see, that way the model will be trained by seeing not just a single trained set, but different data sets. And then, yeah, the other method would be data insertion. So in the data insertion method, more observations, that is, rows, can be added to the data when the model starts to lean towards memorization from the data set, you see? Okay, so another method is feature selection. Now, my friends, with the feature selection method, noise and bias in the data set can be reduced just by reducing the number of variables. See, so actually the feature selection includes quite a few sub-methods, huh? Now, there's another method that's called trimming or stopping. So with this method, the model working as an iteration can be prevented from being trained too much on the data. So, for example, for decision tree algorithms, for instance, overfitting can be prevented just by pruning without branching too much. Cool, so let's continue to another method, would be regularization. So this method refers to various techniques that artificially force your model to be more straightforward. And then the last one that I want to tell you about is ensembling. So with the ensembling method, we can combine predictions from more than one model. Yeah, so as a result, when building a machine learning model, we'll always need to consider overfitting as well as underfitting situations at pretty much every stage of the algorithm. Right, so hey, guess what? We've come to the end of yet another wonderful lesson. I want to see you next time, though. We've got more to learn, more to do, more to explore. See you next time. Well, hello, my dear friends, and welcome back. So we've got an action-packed lesson for now. We're going to continue with supervised learning algorithms. This time, we're going to hit up logistic regression algorithms. So yeah, in this context, we're going to first talk about the theory of the algorithm before moving on to coding with our Python. So my friends, logistic regression is kind of like a regression problem where the dependent variable is categorical. It's actually widely used in linear classification problems. Although it is called regression, there is a classification here. So logistic regression is a statistical method used to analyze a dataset with one or more independent variables that determine an outcome. Now, the outcome is measured with a binary variable. There are only two possible outcomes, in other words. Now, in logistic regression, the dependent variable contains binary encoded data. So, for example, the target variable can only be 1 or 0. Now, if we detail the example a little bit more, 1 could be true, successful, pregnant, this kind of thing. So a value of 0 may also be false, failing, or non-pregnant in our examples. The most significant difference between logistic regression and linear regression is how it applies the line that separates the two classes. Yeah, so let's examine the situation with a technical visual. Okay, look at this image. It's basically explaining the logic of linear and logistic regression algorithms quite well. So we examine linear regression. It uses the least squares method to draw the optimum line. Predicted values can be below 0 or above 1. Logistic regression uses maximum likelihood. So in other words, the estimated value according to the state of the line on the graph is between 0 and 1. So then, what is a line on the logistic regression graph? What is that going to mean? Well, my friends, I'll tell you. The line on the graph is the sigmoid function. The sigmoid function is simply the function used to compress our data between 0 and 1. So it's thanks to this function we can classify it. Then you might be asking or thinking, how does this logic of the function work? Well, you can see here a threshold value drawn from the middle of the function on the screen. This threshold value corresponds to 0.5. If the prediction is above 0.5, a logistic regression model will predict 1. If the prediction is below 0.5, the logistic regression model will predict 0. Okay, you probably could have guessed that. But now I want to talk about some of the advantages and disadvantages of logistic regression algorithms. So, what are some of the advantages? Well, my friends, logistic regression is easy to implement and interpret. It performs pretty well if the dataset can be linearly separated. It's going to be less prone to overfitting, but may overfit in large datasets. So then what could a possible disadvantage be? I've got a few. Logistic regression should not be used if the number of observations is less than the number of features. Otherwise, you might actually be guaranteeing an overfit. For example, it's kind of unreasonable to use this algorithm if we have 100 observations but 150 variables. You know what I mean? All right. Anyway, that's enough. We'll just leave it at that. So, that's the algorithm's logic. How about we move on to coding with Python? Because that's what you're here for, right? Now, previously, I've explained the metrics that we use to evaluate the model we built with this algorithm. And those of you who just are a little bit fuzzy, you can go back and watch those lessons again. Not a problem. We'll catch up with you in a minute. Because in the next lesson, we're going to start our coding. So I want to see you then. All right. Hello, dear friends. So here we are, and welcome back. As you know, we have talked about and hopefully learned the theory of this logistic regression algorithm. So now we are going to perform our application with Python. So we'll get started without taking any more time. Unless you think you need it. I don't think so. You are ready. So we're going to perform the application on the Titanic dataset, which is one of the built-in libraries in the Seaborn library. Now, my friends, this dataset happens to be very famous in data science, if you didn't know that. In general, people interested in data science often encounter the Titanic dataset. It is a classic. So in this lesson, we're going to analyze this dataset and do some machine learning. So right now, let's get to know the dataset a little bit better before we move on to the algorithms themselves. So you might recall, if you haven't seen the movie, the Titanic was this great ship that was supposed to be invincible, unsinkable, and it sank on its maiden voyage on April 15th, 1912, after colliding with an iceberg. Now, 2,224 passengers and 1,502 crew members actually lost their lives. This tragic disaster shocked the international community and led to better safety arrangements for ships. But one of the reasons the accident caused such loss of life was the lack of lifeboats for passengers and crew. Now, you might imagine it was pretty difficult to survive. It was either luck, divine providence, or sheer grit. Who knows? But the point here is, some of the classifications of humans were actually more likely to survive than others. Now, without guessing, we're going to talk about where is this dataset used in the field of data science, right? That's what we're here for. So this dataset estimates what kind of people would survive the ship's accident and which passengers actually survived the wreck. Now, this will be our aim in our Python coding lessons. So let's get to work. So first, we'll load up the libraries. And I'll write in a title. So I'm writing importing the libraries in Markdown format. And I'm, of course, putting a double asterisk around it. And let's run the code. Very good, very good. So now we can start importing. First, I'll import pandas and numpy. I'll say import pandas as PD and import numpy as NP. And let's run that code. Very good. So now let's import the visualization libraries. So I can say here, import matplotlib.pyplot as PLT. And I'll say import Seaborn as SNS. Okay, so I will import the warnings library so that we can avoid seeing some of those simple warnings. Now, from the bottom line, I'll call the filter warnings module from this library and write the ignore argument here. So let's run the code. Okay, so the libraries are now ready. Let's load up the data set. Now again, I'll open up a cell in Markdown format and write loading the data set within. And I'm putting a double asterisk around it so we can run the code. Very good. So now we can actually load the data set. So I need to specify a variable. Let it be df. And I'll say equal and call the load dataset function from Seaborn library. Now I'm writing the data set that I will load into it. I'll say Titanic. Okay. Now let's run this code and call the data set. So I'll say df.head. Okay, my friends, so as you can see, we've got our data set. Now, let's get to know some of the variables within this data set. It's actually essential to recognize variables here in the data set because it's always, well, you are going to be at a huge disadvantage, right, to be able to work on data if you don't know anything about it while you're doing your work. But I digress. But if you've noticed, we actually always recognize the variables in the data set before we start our work, so I'm training you. You are my training set. Okay, so let's get started here. So the first variable we see is survived. This variable is a variable that tells us whether the passengers on the ship survived. So those are the value of 1 are survivors. Those are the value of 0 are people who lost their lives. So yeah, the variable P class is next to it. Now, this is a variable that represents a class of tickets. So it shows that there's first, second, and third class tickets. Moving on, next is the sex variable. And this variable refers to the gender of the passengers. And we'll continue with the variable age that shows the age of the passengers. Now here, there's a variable sib_sp right next to it. So this variable is a number of spouses or siblings on the ship of the passenger. Now, we're not going to comment about 18th or 19th century mores or anything. We're just going to share and review this data. Okay, so continuing on, you see the parch variable? This variable shows the number of parents on the ship. And then right next to it, of course, this variable shows us the ticket price. And again, there is the embarked variable over here on the side, and it basically shows us from which port the passengers boarded the ship. Now, curiously, this variable has 3 values. These are values C, Q, and S. Do you know what they are? Well, I'll give you a little history lesson. C stands for the port of Cherbourg. Q stands for Queenstown Port, and S stands for the port of Southampton. And we'll continue. There's a class variable. Now we can also say the categorical state of the P-class variable for this particular variable. So it has 3 values, first, second, and third. All right, we'll continue. Now there is a who variable. This variable is a variable that indicates whether the passengers are male, female, or child. And you see adult male is the variable right next to it. And this variable, of course, shows whether the passengers are adult males or not. Continuing on with the deck variable, and this variable is the one that shows which deck the passengers are on the ship. And it starts with the letter A, shows the decks up to the letter G. And we'll continue. On the side is the embark town variable. Now, we know this variable, right? You may remember that when we were defining the embarked variable, we said that the initials of the port where the passengers boarded the ship, right? So this variable will consist of the names of the port cities directly where the passengers boarded. And here is the alive variable over here on the side, and this variable can be called the categorical version of the survived variable. So the value of no represents a deceased. The variable yes represents the survivors. And continuing on, right next to it is the variable alone. It tells us whether the passengers were alone on the ship. And this variable is actually a mixture of SIB-SP and PARCH variables. So in other words, if the SIB-SP and PARCH variables are both 0, right, they are expressed as true in the alone variable. Now, I know some of you may be wondering, well, why do some of these variables look alike? Or couldn't they be condensed? Or, well, hold on. Why keep both numeric and categorical states of some of these variables as data might be the deeper question. But for those of you who might just have awakened with that, the variables survived and alive appear as a reason for asking these questions, right? What's the difference? Is there a difference? Why have it here? So here's the answer. These variables provide some flexibility with which type of data that we want to work with for our research. For example, if our purpose is to analyze categorical variables, well, we can use the variable alive. If we want to operate with numeric variables, we could always use the variable survived. Okay? So my friends, we're finished with the variables in the data set. Now you understand why we do that. There are a few more details I want to draw your attention to. So we'll open up this section as a new topic. Now here, you see I'm opening a cell in Markdown format, and I'm typing in the title. For example, let's just let it be initial analysis on this data set, say. And I'm putting a double asterisk before and after, run the code. So now I can examine the data set in detail using the info method. So if I say df.info, as you can see, the information on the data set has appeared, and my friends, you can look and see there are 891 rows, 15 columns in this data set. There we can see the missing data and the variables in the middle part. Now, according to our initial analysis, the most missing values are found in the deck variable. So just think about discarding this variable from the data set. We probably will. And yeah, so here we can see a nearly moderate missing value in the age variable. There's actually more than 170 missing values. And here the variable embark and embark town. Well, this, of course, would have the most negligible missing values, got 2 missing values. So yeah, we can now see the types of variables on the right again. Now you've got a summary below. See, so there are 2 Boolean, 2 categorical, 2 float, 4 integer, and 5 object type variables. Yeah, so before we move on to the primary analysis, I do want to make one of our general inferences, okay? You remember what we were saying when we recognized variables at first? There were variables in the data set that kind of meant the same thing, right? For example, embark or embark town and the class with P class. So now I want to show you how to remove one of the similar variables from the data set. So this way our work can be a little easier before we move on to our modeling and analysis. So with that in mind, I'll just say df.drop, and now I can write in the variables that I want to discard from the data set. So let's say that I want to remove the embarked variable from the data set because we've already got the embarked town variable with the very same features. All right, and I will want to remove the class variable because if you remember, it means exactly the same thing as the p-class variable. Let's do that. And then finally, let's say that I want to discard the alive variable because we've also got the survived variable with the very same properties, right? Okay, so see, that'll be enough to remove this many variables for now. If there is a variable that we need to drop in the next step, we can always remove it from the data set. All right, so for now, we'll continue. And I'm setting the axis parameter to 1 because I want to reduce it on a column-by-column basis. And because I want my changes to be permanent, I'm just setting the in-place parameter to true. All right, so now we can run the code. And we'll call up the data set again. And look at that, my friends. Our request has come to 4. You see it in front of you. Okay, my friends. So, hey, we are going to call it for this particular part of the lesson, right? We're going to wrap it up here and continue where we left off in the next video. All right. Well, hello, my dear friends. Welcome back. So we're going to pick it up right where we left off from. So we have removed the 3 variables that we don't want to see from the last lesson data set. And now we'll proceed with our analysis. So now I want to perform a missing value analysis. So therefore, I can evaluate the actions that I will take from now on in exploratory data analysis. Okay. So I'm just going to set up a new title and I'll write exploratory data analysis, EDA, in Markdown format. So run that code. Now we're going to analyze the missing values. So first, I want to see the number of missing values. So I'll show the presentation as a data frame structure to make the presentation even better. So we'll start with that. Creating a variable. And we'll let it be an abbreviation for null number. So I'm typing null num. And I can equate this variable to the empty list. See? So soon the empty list will be filled with the total missing value number of the variables. And I'll keep going and start a loop. So I'll say for I, and then pretty soon all the variables in the data set will come into this I respectively. And I'll continue with df.columns. Yeah, so now we can get down into the body. And here I'm creating a new variable. I'll say x. So now I want this x value to be the null value of the variables. So in the scope, I'll say dfi. You see, because since the variables are going to be within the variable I, the value of I here will be filled with the variables in order. Right, so then I can apply the isNull function to this expression because I want to learn about the missing values. Okay, so yeah, now we'll get all of the missing values right in here. However, since I want the number of missing values, I end this whole expression and insert the sum function. That'll give us a total number. Okay, so now the variable x is created. So I'm going to add the values in this variable to the empty list that we created above in order. For this, I'll apply the append function. So you see, I'm calling the list and applying the append function. I'm writing x inside the function. Okay, my friends, so here, I think I've reached the goal here. So let's run the code. And now we can have a look at this null num list. All right, so here we've got our values. Now we'll show these values in the data frame structure. You get me? So see, I'll go here to the bottom and say pd.dataframe. Now first I'll insert the values into it. Then I sync the index parameter to df.columns because I want the index to consist of variable names, right? All those named variables. So what I'm doing is I'm setting the columns parameter to total missing values. Awesome. the data frame structure is now ready so we can run the code. All right, my friends, look at that. It's pretty good. So the number of missing values comes up with a lovely looking table. Yeah, see, so only 3 variables have missing values. It's pretty good. These are age, deck, embark 1 variables. Okay, so let's deal with the missing values in these variables first. So I'll want to start with a variable with the most missing values. That happens to be the deck variable. So my friends, the missing value in this variable is just too much, right? We can fill them with appropriate values. That's one way to go. However, this time the structure of the data may actually change. So therefore, we will remove this variable directly from the data set. Right. So before I do this drop, I just want to examine this variable a little bit deeper like this. So first, we'll examine the observation values according to their numbers in the data set. So for this process, I want to use the countPlot graph function in the Seaborn library. So we'll create a graph. First, I want to set the background of the graphic. So I'll say sns.setStyle and put the dark grid argument into it. Yeah, see, so you can change this argument. You can see some of the other arguments if you Shift-Tab inside the function. But we're going to continue. I'm just writing sns.countPlot. Very good. So I'm now going to write the parameters, right? So first I'm going to write the variable that I'm curious about. So that's why I'm setting the x parameter as the deck. Then I'm setting the data parameter to df. And finally, I'll set the palette parameter to viridis. All right, so let's run the code. And here you go. As you can see, that's what it looks like. Now, according to this image, most of the passengers are on the C deck. The deck with the majority of minors is G. And you can see the results of some of these other decks on the screen as well. But for right now, let's quickly determine who's going to survive after sinking according to this deck variable. So you see, I'll take this code, I'll copy and paste it below, just writing the hue parameter into it and setting this parameter to the survived variable. See, this way we'll be able to operate this suitable to our purpose. Let's just run the code. Okay, so there's a great graph. And when you look at the upper right-hand corner, we see the green bars belong to the survivors, the blue bars belong to the deceased. All right, so the decks are on the x-axis again. So let's just interpret this together. So yeah, the first thing that stands out is that the passengers on decks B and C have more survivors than the others. You see that? But if we evaluate these two, the B deck actually seems to be more reliable. What would be the reason for this? Well, when we evaluate the survivor versus non-survivor, the B deck seems to be more advantageous, right? So this is what we're thinking about for our future. Perhaps the least safe decks are A and G. Now, if you've noticed here, the rate of death's very high. So yeah, we can evaluate the other values just like that as well. But you see, now that we've examined this variable, we've learned a few things, we can actually remove it from the data set. So I want to remind you, why would we remove this variable from the data set? Well, for one thing, yeah, there were way too many missing values in it. So why don't we just do it right now? I'll say df.drop, write the variable that I want to drop into it. And then I'm just setting the axis parameter to 1 and the in-place parameter to true. So run the code, and let's call the data frame structure again. And look at that, the variable fell. So yeah, so now I'm back to the missing value table. Now here, let's focus on the age variable. And if you notice, there are 177 missing values here. So how do you want to deal with these missing values? Well, to be honest with you, this actually might be a necessary variable. So I don't want to drop it from the dataset completely. So there's got to be another way, right? We could fill it with appropriate values. So let's say that I want to find appropriate values. First, I want to analyze the p-class variable according to the age variable. You, of course, remember what the p-class was? It was the ticket classes of the passengers on the Titanic, right? Okay, so we'll take the average of the age variable according to the ticket classes and place it in the missing values from the age variable. See how that works? So now we've set up an algorithm, we can start the application. Yeah, so you're going to get that when you see it in practice. So I want to create a graph, and we'll use the box plot graphic, and I'll determine the size of the image. I'll just say plt.figure and set the fig size parameter to 10 by 6. So I'll go down here and say sns.boxplot. And first I'll put the variable p-class for the x-axis and age for the y-axis. And I'll set the data parameter to df. Very good. Let's run the code. And there you see a great graph. Look at this. We can now see the age distribution by class here. So I want you to notice something. The quality of the ticket class increases as the age increases. So in other words, those who are older seem to have bought first-class tickets. So yeah, when we look at the general average, though, passengers with P-class variable 1 have an average age of 38. Passengers with 2 have an average age of 29. Passengers with 3 have an average age of 23. So you see how in this context we can fill in the missing values from the age variable, taking into account the P-class variable, that is, the ticket classes of the passengers. So that means I can create a function to make our work a little bit easier. And then I want to apply this function to the entire age variable with the apply function. All right, so let's continue. I will say def and find a name for the function. Let's let it be fill in age. And now I'm going to put parameters. So I'll call it columns because we will work with 2 variables. And we'll go down to the body now. So we're going to have 2 variables, right? So I'm setting the first one to be age and equating it to the 0th index of the columns parameter. And I'll create another variable, which will be p-class. I'll equate this variable to the first index of the columns parameter. So now we'll move on to filling in the missing values. So I'll use the if, else structure. So I'll say if, write the condition. I'll say pd.isNullAge. Yeah, see, so this condition will cause the if structure to work, as it will return the empty values in the age variable true. Okay, so we can go down to the body of the if structure, and I'll create an if structure again and fill in the missing values according to the p-class variable. As you know, this variable has 3 values, 1, 2, and 3. So I'll write the code to fill these values in order. So I'm writing if p-class equals 1, go down to the body. And yeah, if this condition is met, we want to fill the missing value with 38, right? So I'm returning 38, and we created the first structure, okay? So now I'll just go down and continue to write the other conditions. This time I'll say if p-class equals 2, and go down to the body. Now, if the p-class value is 2, what are we going to do? We're going to fill it with the value of 29. That's why you make notes. So I'm writing return 29. Yeah, so now I want to create the final structure, And that is our absolute value, I believe, of 3. Yeah, because it's the last structure, I can say else and go down to the body and write return, what was the youngest? 23, right? So that's going to fill it with 23 for the very last value. All right, my friends, so there you go. If else structure is going to be valid if there were missing values in that age variable, right? So then, what do you suppose happens if the values in the variable are not missing? Well, you see, for this, I come to the first level of the structure. I go down to the body by saying else. If the variable age is not empty, it does not need to be filled with anything. So let it output directly as it is. So that's why I'm just going to write return age. I know that was kind of a dramatic buildup, but I wanted you to get the point. So now you see that we've completed the function in general. Let's run the code and see what it looks like. And we'll apply this function to the age variable. So I'll say df age equals, because we will create the age variable again. And now I call the variable age and p class from the entire data frame structure. And I will apply the function that we created above to these variables. Now, hopefully you remember, right? There was a column parameter in the function. This parameter will take 2 values here. Then we create 2 variables, right? Age and p class are going to be our variables. The first value of the parameter will be create the age variable, while the other will make that p class variable. And yeah, you know what's going to happen next. After a summary, we're going to go back to coding. Now, the last thing that we did was get 2 variables from the data frame structure, right? Right. So now I'm applying the apply function to these variables. So this function will apply the function that we will write to the entire age variable. Okay, so now we're writing the variable that we created above. Yeah, so I'm setting the access parameter to 1, and it's going to be applied on a column-by-column basis, right? So let's run that. Okay, so you see the code works. All the missing values of the age variable get filled. But we got to make sure that's correct, so let's recheck, and we'll see if we can find any other missing values. So I'll just go up here, get the code, copy it below, paste it. And I'll go up again and get the data frame rendering code. Copy and paste it. Okay, so now that's set. Let's run the code. See, so look at this. There are now only 2 missing values, and those are not what we just did, so that's good. They are in the EmbarkTown variable. Now we're also going to deal with the missing values of this variable and then finalize this stage. So what do you think we ought to do? Well, my friend, since there are only 2 missing values, why don't we just remove the values from the data frame structure? So what do you think? So I'll use the drop_NA function for this, and this function will drop the missing values directly. See, so it'll just drop 2. So for this, I'll say df drop_NA, and I'm setting the in-place parameter to true, and that'll make those changes permanent. Let's go ahead and run the code. Cool. So now let's have a look for some missing values again. So I'll take the code above, copy and paste. We'll run it again. Okay, so now we've got no missing values. So the variables turned out just the way we wanted. So in fact, I think that's a very good time to wrap it up. We'll indeed wrap it up here, and we'll continue next time with our exploratory data analysis. I'll see you then. Bye for now. All right. Hello, my dear friends. Welcome back. So we kind of struggled with some of those missing values in the previous lesson. Hope you don't feel too guilty about dropping anything, but you see how that works now, right? So in fact, we're going to analyze the variables through some visuals. All right, so let's get into it here. I want to first examine the target variable survived. Now for this, I don't want to use any different visuals just to save a little time. I want to make some changes to the code of the visual work a little bit differently than we did earlier. So with that in mind, I'm going up here and I'm going to take the whole code that we wrote for the variable dec. And copy and then paste it. And now I'm just going to change the variable name from here, right? So I'm changing the X variable to survived. Let's run the code. Okay, so here's the graph. Now, as you can see, most of the passengers on board died. In fact, it looks like there were almost twice as many deaths than survivors. Okay, so let's say that I want to see the variable's exact number of observed values. So if I write df survived below, and then apply the value counts function to it. Let's run the code and see here, 549 people lost their lives after the accident, while 342 people seem to have survived. Well, now let's dig into a little more detail. Are there any factors that affect the survival of the passengers? So I would wonder if the passengers survived by chance, or did some of the opportunities that passengers might have obtained on board actually enable them to survive, or at least up their chances of survival? So for that, we'll need to do a binary analysis using the target variable to answer these questions. Why don't we just get right in? So first, I would like to explore the impact on survival of being alone on the ship. So which variable would we want to look at then? Would it be alone? In fact, the alone variable is a mixture of SIB, SP, and parch variables. So in other words, if the SIB, SP, and parch variables are both 0, they are expressed as true in the alone variable. So yeah, I'll just take the above code and copy, paste it below, and that saves a little time. Now, since we are wondering about this variable survived, I'm not going to change the X parameter. I will add the hue parameter, and I'm setting this parameter to be alone. So let's run that code. Okay, so now we're looking at the image that we want. Let's interpret it. All right, so the first thing that you see, or that I see anyway, is that most of those who lost their lives were alone on the ship. In fact, almost twice as many of the deceased were alone. So maybe they weren't in a very safe place on the ship. Maybe the accommodation on the Titanic wasn't suitable for being alone. I don't know, it's too early to say. But again, when we look at the percentage of survivors, the number of those who are not alone does seem to be higher. So that would support some of those comments. But now let's investigate the effect of being an adult male on board. How does that impact survival? Now, to save a little more time, I'm just going to take this code above and paste it below. I'll change the hue parameter. So you see here, I made it adult male. And we'll run the code. Okay, so that's a pretty incredible visual here. See, so the vast majority of adult males seem to have died. And when we look at the survivors, we see that the blue bar is kind of high. So in other words, there is a success of non-adult males. What does that mean? Well, perhaps little boys are given better chances to be rescued. Well, what would be the general opinion then? Wouldn't it be that, you know, the old expression, right? Women and children first and that sort of thing. The captain goes down with the ship. So wouldn't it follow then that women and children should be given that priority. Well, we saw in this analysis that children were given the priority. Can we say the same for women? Well, for that, we would need to investigate the effect of the gender variable on survival. So I'm just going to be taking the code from above and paste it down below. And I'll select the hue parameter here for sex, and we'll run the code. Okay, so there you go. There's another hypothesis confirmed. The majority of those who lost their lives are men, in fact, almost 5 times more than women. See, so when we look at the survivors again, the increase in the number of women is quite apparent. So it means that women and children were given the chance to be rescued. So now let's have a look and investigate the impact of port cities. So where the passengers embarked, well, how did that impact any survival? So in this context, I'm going to take that code from above and paste it down here. And I'll just change the hue variable and run the code. Okay, so check it out. As you can see here, most of those who lost their lives boarded the ship from Southampton. And you can see the others in order on the screen. But I do want to draw your attention to one thing here. The number of passengers joining in Southampton is probably much higher than in the other 2 cities. In fact, let's just double check that. So if I say df embarktown, and I'll apply the value counts function to it, let's run the code. And as you can see, that analysis would be correct. So the number of passengers joining the ship from the city of Southampton is 2 to 3 times higher than the sum of the other 2 cities. So we're going to finish up our analysis, but I want you to stop the video for a second after I tell you what's going to happen next. But give it a try. Analyze the relationship of the remaining variables in this way to survived. So, for example, interpret the relationship between the variable sib_sp and survived. Okay, and then let me know how you did. All right, so I just want to end the lesson here because I think that we've done a lot of binary variable analysis, and that's enough for now, but I do want to make sure that you understand how to do it. Okay, so we're going to continue with developing your analysis skills next time. I'll see you then. Well, hello, my dear friends. Welcome back. So in this lesson, we're going to continue our variable analysis from where we left off and examine the structure of numeric variables. So for this particular study, we will use the dist plot graphic. Yeah, so let's focus on the age variable first, and we'll code the graph. Okay, so I am determining the size of the image, and I'll just say plt.figure, and within it I'm setting the fig size parameter to be 10 by 6. And continuing on, I'll just type in dfAge. To determine the color of the graphic, I'm setting the color parameter to be dark red. You can make that a different value if you want. But let's run the code. All right, so as you can see, we've got a nice graphic here. There's a general average age of passengers between 25 and 35. Now, I wonder if you noticed, there is a breakdown here. So here we see that there are children between 0 and 4 years old. Yeah, so there are no very old passengers in general. There seems to be a severe decrease, especially after age 35. Okay, so we'll continue by taking our notes, write them down. Now, don't you wonder about the distribution of ticket prices, though? Now, again, to save some time here, I'll just take the code from above and paste it down here. And I'll just change the name of the variable. And I'm looking at changing it to fare, F-A-R-E. And let's run the code. Okay, so as you can see, ticket prices for passengers generally vary between 0 and 50. And after 50, there is a decrease. So because we've got these endpoints, the data has a tail to the right. That's why we say that the data is skewed to the left. See the difference? So we can end this analysis here, now that we've seen this general distribution. But then finally, I want to examine the correlation between all the variables. So I will use the heat map graph for this. So here we'll get started, and we'll set the size of the chart first. So I want to say plt.figure. I'm setting the fig size parameter to 10 by 6. And I'm going down the line saying sns.heatmap. Writing the data that I want to see in the graph, I'll say df core, C-O-R-R. And finally, I am setting the anot parameter to true. All right, so this parameter will print the correlation coefficients on this image. Let's run the code. Okay, so now we see all the correlation coefficients appearing. Now, I do want you to focus on the survived variable here. So the variables with the lowest correlation are age, SIB, SP, and parch. So you could say that these have a deficient level of correlation. Therefore, I will remove these variables from the data set before moving on to machine learning. You see? We also see their relationships with other variables on the screen. Now, since the variables are not significantly correlated, I will put all the remaining variables into the machine learning model. You get it? Okay, so let's apply the analysis that we extracted from this chart now. Now, what did we say? We will remove 3 variables, right? So that means I'll say here df.drop, and I'll write the variables that I will extract into it, respectively. Yeah, so I'm setting the axis parameter to 1 because I want to reduce it column by column. And finally, I'll set the in-place parameter to true. Good, so let's run the code. So now we can call the data frame structure again. And look at this, the data set comes right into the shape that we're looking for. So yeah, but we do have one thing left before we go inserting these variables of the data into the logistic regression algorithm. You know what that would be? We'll need to transform the categorical variables into a form that the machine learning model can understand. So remember how to use the getDummies function? That's what we're going to use right here in this context. So we'll apply the getDummies function to the categorical variables within the scope of the one-hot encoding method. One-hot encoding. You know it? Yeah. So here you see that there are 5 different categorical variables. So I will implement 5 other getDummies functions. So first I want to say pd.getDummies. Insert the first variable inside. Then I'm setting the drop first parameter to true, and that'll drop the extra column that'll be formed by getting dummies. Yeah, so I can equate all this code to a variable named sex again. Now, when that operation finishes, I just want to add these newly created variables into the data frame structure. So continuing on, the second variable is this who variable. So I'm creating a variable with the same name within this variable. So I'll say who equals. And of course, to avoid spending too much time here, I just want to take the code from above, paste it down here, and I'm just changing the variable inside. So moving on, I'll say adult male equals for the third variable and paste the above code again. So here I'm just changing the name of the variable inside, right? So I'm just doing adult male. And moving on, for the fourth variable, I'll say embark town equals and paste that code again. So now I'm setting the variable name to embark town. All right? So for the last variable, I'll say alone equals, and again, I'm pasting that code, and I'm changing the variable name to alone. All right? So now let's run all that code. All right, my friends, look at this. So we've created the variables with a getDummies. there is a data frame structure inside each variable. The next step is adding these variables to our main data frame structure. For that, I want to use the concat function. So we'll do it right now. So if I say df equals, and then call the concat function from the pandas library, you see where we're going? I'm writing the data frame structure I will add to a list. I'll say df. Then I'll write the variables that we created above, respectively. Yeah, so because I want to concatenate on a column basis, I'm setting the axis parameter to 1. See, pretty soon you'll be able to just see it in your head, but right now, let's run the code. Yeah, so now let's call the data frame structure again. So I'll say df.head and run that code. Very good. So see, that looks great. Our categorical variables appear in binary format next to the primary data frame structure. Now, have you noticed the state before getDummies is still in the data frame structure? So therefore, I want to discard the initial state of the variables that we transform from the data frame structure. Got it? So I'll say df.drop. I'm writing the variables that I want to reduce in a list. Okay, so I am setting the axis parameter to 1 and the in-place parameter to true. And now let's run the code. Call up the data frame structure again. And as you can see, our request has been granted. See, now the structure is ready for machine learning. Pretty cool, huh? Yes, my friends. So we're going to start the next lesson with our logistic regression algorithm. Okay, so I want to see you then. Bye for now. All right. Hello, my dear friends. Welcome back. So I want to create a model in this lesson using our logistic regression algorithm. So let's dive right in. So first of all, I'll open up a cell in Markdown format, write the subject title in it, call it modeling. And of course, put a double star at the beginning and the end. Let's run that. Okay, so now I'll first divide the data set into 2, right? Test and train. So in this context, I will import the relevant library. So I'll say from sklearn.model_selection, import train test split. We'll run that code, and you see how that imports the library. Now I'll create 2 variables. We'll let the first be just the classic x. I'll say equals. Yeah, so variable x will consist of independent variables. And in that context, if we remove the survived variable from the entire data set, we're going to achieve our goal. Yeah, so I'm going to say df.drop, write the variable survived in it. I'm setting the axis parameter to 1 because I want to reduce it column by column. I'm going down here and creating variable y. Then I'll say equals. This variable will be the target variable, the predicted variable. So I'll write df survived. Now everything's ready. Let's run the code. Yeah, so see the variables are ready. Now we're going to divide these 2 variables into 2, right? Test and train. And for that, I'll use the train test split function. Now, my friends, this function yields 4 variables, right? So I'm creating variables within that scope. I'll say xtrain, xtest, ytrain, ytest. And let's now call the function. I'll write x and y variables into it. So now I want to determine the ratio at which I will divide the data set. So with that in mind, I'm setting the test size parameter as 0.25. I'm going to set the random state parameter to 42 to get the same output every time. So let's run that code. Yeah, so now we have our test and train data sets. Right, so now we can create our logistic regression model. First, we'll import the relevant library. So in this context, I'll say from sklearn.linearModel, import logistic regression. Run that code. I'll create the model object first, and I'm creating a new variable within this scope. Let's let it be LR model. So I'll say equals and equate it to the logistic regression function. Let's run the code. Yeah, so the model object's now been created. Let's train the model. Okay, so I'm calling the model object and applying the fit function on it. I'm writing the training data inside the function. I'll say xtrain, ytrain. Now let's run the code. Awesome. So the model's been trained. Now is the time to guess. So we're going to do this with a test data set, right? Let's do it. So I'm creating a new variable. Let's let it be ypred. And I'll say equals. I'm calling model object and applying the predict function. And I'm writing the test data set. And we'll run the code. Yeah, so we have the guesses now. Guesses are just another word for prediction, right? So we can actually test the accuracy of our model, which is the point. So I will use the classification report and the confusion matrix for my metrics. So you know how to do that, right? I'll just import the library into two metrics. I'll say from sklearn.metrics import classification report. Go down and say from sklearn.metrics import confusion matrix. Let's run the code. So now we've got to find the accuracy of the model using these metrics. So I'll say here, print classification report, and I'll put actual test data in it first. Then I'll put the estimated values next to it. I'll say ypred. Okay, so now that everything's ready, we can just run the code. All right, so here is our report. Now, the important metric for us is the F1 score metric, remember? And this is actually a good result. However, this value can be increased by returning to a new model structure. Yeah, we see the precision and recall values here. But let's use the other function, confusion matrix, to analyze them a little bit better and see what that gives us. So I'm creating a new variable. Well, let it be called the CNF matrix. I say equals and call the confusion matrix function. And I'm putting the actual data into it first. Then I'm putting the predicted data. Now let's run the code. And we'll call the variable again. And look at that, my friends. We've got some data here. Yeah, so we see type 1 and type 2 errors. So the type 1 error is the value in the upper right corner. False represents a positive value. So if we look at the Titanic data set, a false positive is a situation in which those who do not survive are predicted to survive. 30 predictions were made like that. So let's have a look at the type 2 error. So this value is the one that you see at the bottom left. It's a negative value of false. So again, if we evaluate it over the data set, it's a situation where those who were not able to survive were actually predicted to be alive. So a total of 17 values were estimated like that. Yeah, so see, a type 2 error is far more critical than a type 1 error. So therefore, it would be advantageous for us to have the value of this type 2 error much lower than the value of type 1. So with that, let's wrap up our lesson. So in the logistic regression part, we've actually learned this Titanic dataset, and it happens to be a built-in library from the Seaborn library. We certainly conducted extensive exploratory data analysis before we moved on to modeling, so you should know it backwards and forwards. All right? Finally, we created our model using the logistic regression algorithm. Real good job. Excellent. So I want to see you next time. Bye for now. All right. Well, hello, my dear friends. Welcome to our lesson, because now we're going to talk about a new term. It's called cross-validation. So far we've worked on two machine learning algorithms, and these were linear regression and logistic regression. Both of them algorithms, just like you know. Now, hopefully you understand the logic of machine learning because of these algorithms. So now it's time to go a little bit deeper. I know you're ready. Now, as you know, we built models using these algorithms and divided the data into two, one to train and one to test, using the train-test split method. For example, we split 75% to be trained data, 25% will then be test data. And according to this distinction, the models were giving predictive accuracy. However, I wonder if you noticed, while we were doing this study, we only achieved accuracy once. Maybe information could have been better for our model was within the 25% that we set aside for testing, or perhaps the data that we needed to use for the actual test was in the data that we reserved for training. We used the k-fold cross-validation method to overcome just this situation. So I want to start showing you the logic of this process. So we've got k-fold cross-validation. It's only one of the methods of splitting the data set for evaluating classification models and training the model. So for example, we've got a data set with 2,000 rows. So we want to train our model with part of this data set and evaluate the success of our model with just part of it. All right? So it's a pretty simple approach. You set aside 75% of that for training and 25% will be for testing. However, just like we have discovered before, while the data is fragmented here, some deviations, biases, and perhaps even outright errors may occur in the training and testing of the model. It depends on the distribution of the data. So in this way, k-fold cross-validation divides the data into equal parts according to a determined k number, ensuring that each part is used for training and testing, thus minimizing deviations and errors caused by dispersion and fragmentation. Sounds good, huh? However, an additional process such as training and testing the model for k requires some overhead and time. Although this is not necessarily a problem for small and medium volume data with short training and testing periods, it's going to be costing computation and time in much larger volume data sets. You follow? Yeah, so you're looking at a picture on the screen, and here we can see the k-fold cross-validation logic. The leftmost rectangle represents the 2,000-row data set. Now, we divide this data set into 5 equal parts. The k value here is 5. And we run the algorithm 5 times on the training and test sets. So in the first round, we divide the first 1 through 400 pieces of data for testing, and the 401st all the way through 2,000 will be for training. But then you see in the second round, we're allocating 401 through 800 of these records for testing, and the rest will be for training. So you see, this way we'll complete 5 rounds. So when we take the average of the accuracies, the result will give our model performance score. So after trying this on many different classification algorithms, we can say that the algorithm with the highest score has classified it the most successfully. All right, my dear friends, so we're going to wrap it up here with that theory. And next time, we're going to apply the k-fold cross-validation method via Python. I'll see you next time. Bye for now. All right. Hello, my dear friends. Welcome back. So, you know what we're going to do, right? We're going to apply the k-fold cross-validation method with Python. So we'll proceed through our previous studies to fully understand this subject. And as you can tell, we're on our notebooks where we do linear regression work. So let's do a quick recap. We imported the MPG dataset and looked at its contents. Then we dropped the unnecessary columns, examined the basic statistics of the dataset, and started data preprocessing. Here we struggled with nulls, right? So finally, we looked at the evaluation metrics and evaluated the model's accuracy right here. The R2 score was 78%. Now, I wonder if you noticed, these values came with only one training and one test data set. So now, why don't we run the model with the training and test data that has not been seen with the k-fold cross-validation technique? See, so in this way, we'll be able to obtain more reliable results and compare the two. Okay, so if you've reopened this notebook that we worked with before, remember to run all the cells from the beginning. Okay, so now I'm adding in a blank code cell to the lower part here. So first, we'll need to import the cross-validation. I'll do this with the model selection module from the sklearn library. So see here, I'll say from sklearn.model-selection. Then I'll import the cross-validation score by saying import cross-val score. All right, so now we can get to work. First, I'll create a variable from which the average scores will come. So I'll say accuracy is equal and call the cross-val score function. Okay, so I'll go inside, do Shift-Tab. Now, see here, my friends, there are different parameters here, right? We'll work with some of them. But first, you'll see here, this is the estimator parameter. So in this parameter, we will need to enter the name of our model. And then next come the X and Y values. These will be train and test data. Okay, let's continue. Now here we've got a scoring parameter. So you should actually change this here if you're curious about the different evaluation metrics. We're going to do that at a later stage if you're patient enough. Anyway, finally, we've got the CV parameter. This is the most critical parameter. So we determine how often we want the model to be created with this parameter. If we're not going to change it, it's just going to set up the model by determining 5 training sets and 5 test sets, respectively, and then get a score. So for the result, we'll look at the average. So yeah, it's going to be enough to work with this many parameters. It looks like so. Why don't we just place our values in order? Now first, I'm going to want to call the estimator parameter and equate it to the model. Now, what was the name of the model? See here, IM model, isn't it? Okay, so I write it in and I'll continue by saying X equals X train, Y equals Y train. And yeah, I'm not going to change the scoring parameter. It is the R2 score by default, so that's good enough for me. And finally, I'll set the CV parameter 10. All right, so now everything's ready. We can go ahead and run that code. Now check it out. You see what happens? Since we determined the CV to be 10, the model was created with 10 different training and test data sets 10 times. See? So this way, the model works with a training and test data set that it hadn't actually ever seen before. So now what do we call the accuracies variable? Let's run the code. All right, check it out. 10 different scores come up, and these are the score values of 10 different pieces of training. Now, if we were to take the average of these, we will see the score of the variable IM model as more reliable. Okay, so I'm just writing the variable and applying the mean function to it in the scope. And check it out, my friends. We got it as high as 81%. Now, you do remember, right? It was 78% when we first found it. Now, yeah, if we focus directly on 78%, we could determine the performance of the IM model in that way. However, we have seen the actual performance of the score value by cross-validation. So now I just want to change the scoring parameter, and we can wrap it up here. So remember, I said that we could make changes to this parameter. So yeah, I'm just going to take the whole code here and paste it. And now I'm writing scoring here and equating it to a different metric. And let's just let it be neg mean squared error. Now this will give the negative value of the mean squared error. So let's run that code. All right. Now a new accuracies variable has been created. All right, let's have a look at the average. So I've copied and pasted it below. Let's run that. And check it out, my friends. A negative value came up because it was negative. Now, I'm doing this positively, so I'll say minus, take the above code, move it down here, and let's rerun it. All right, my friends, our output is 11.79. But the first score that we found was 11.23, right? So I was hoping you could do a cross-validation on the logistic regression study in this context. Go ahead, try it out. Then you can compare the results that you find with the previous results we got here, okay? So we're going to wrap it up here, yeah? See you next time. Bye for now. All right, hello, my dear friends. Welcome back. I want to show you a new algorithm this time around. So what's it going to be? Well, how about k nearest neighbors? So yeah, this algorithm is known as KNN, and that is short for k nearest neighbors, if you've come across that before. Now, if we define this algorithm, we can say the following. Calculated as a result of performing a distance measurement by comparing data of an unknown class with other data in the training set. See, so it's actually expressed as the data classification that is yet to be assigned to a class according to the distance by setting it to the most ideal or optimal class. Okay, so in short, when the model sees any data for the very first time, it will look at the values around it and then classify the new value according to the greatest value. So the KNN algorithm, it's usually preferred in terms of being used in both classification and regression studies. General classification models create a classifier within their algorithm and use this classifier on each data value in the system. You see, so the KNN algorithm classifies the values for each value by creating a classifier over the set of nearest neighbors to the corresponding value. So for example, what do we have here? You're currently seeing an image on the screen. Are you not? Raise your hands. Never mind. Okay, so we've got two classes here, right? Yellow class A and in purple, class B. Now, you see the red star in the middle of the image. This is data coming from outside the KNN algorithm. Yes, indeed, the purpose of this algorithm is to predict the class of the red dot by looking at its neighbors around it. So you see, my friends, the essential thing that we're going to do here is determine the number of neighbors. I wonder if you noticed, we've got two circles around the red star with dashed lines. If you focus in on the first circle, the number of neighbors is shown with a K here, right? So first, the K value is 3. Now, do you notice this? There are 2 purple and 1 yellow datas here. So that's why the red star data is classified as purple, right? It's classified as class B. Now the circle gets bigger. The K value is 6. And there are 2 purple and 4 yellow data points in this circle. That's why we now see the red star is classified as yellow. Okay, glad we cleared that up. So right now, we've actually talked about determining the number of neighbors. What do you suppose is the distance calculated when determining the neighbors? Well, this is kind of fun because this is where different calculations will come into play, my friends. Now you can see the types of distance calculations for the algorithm on the screen, right? We've got Euclidean, Manhattan, Chebyshev, Hamming, Minkowski, Mahalanobis, Haversine, Levenstein, Sorensen-Dice, Jacquard, right? These are all distance calculations. So each of these has emerged with a different mathematical calculation, right? Now, those of you who want to learn the mathematical details can go ahead and research because there's plenty of it out there on the World Wide Web. Because I want to interrupt any possibility of confusion, I'm not going to actually entertain any of it. I just wanted to point it out. Because here we can just choose one of these distance calculations in addition to the k value while specifying the parameter. Now, this one here is optimal, and the default value is Minkowski. So you can see the parameters of the k nearest neighbors algorithm right here on the screen. We're going to use n neighbors, and this will determine the number of neighbors and the distance parameters to determine the distance from them, right? So the places where this algorithm is most used in everyday life are, generally speaking, the banking sector. Credit and risk analysis is very useful in business bankruptcy forecasts, as well as stock market analysis for buying and selling transactions. They're all included here. But it can also be used on very specific problems. For example, the KNN algorithm is frequently used in ecological action analysis, biological analysis, complex text mining analysis, differentiated disease analysis, that's for advanced cancer and tumors, and similarity-based missing data analysis, complex level. So why don't we just quickly have a look at some of the advantages and some of the disadvantages of this KNN algorithm before we just wrap up our lesson here. So my friends, I'll just list them out. The advantages of the KNN algorithm are: data training operations are more accessible than any other algorithm. Processes and analyses can be followed analytically, numerically. Effective against complex or complex noisy training data. It's easy to implement. And the training can be performed using small number of parameters. So yeah, there's going to be some disadvantages though. Because of the transaction volume and steps are fairly high, it needs some pretty high performing hardware. So the cost of the model that we'll create is also pretty high. Although it is resistant to high volume data, it takes a lot of time because the number of steps in the transactions is obviously high. Now, finding the algorithm takes a long time in certain periods, but if you can live with all that, you're good to go. So, my dear friends, that is the KNN algorithm pretty quickly, but we're going to build the KNN model process in the next lesson with Python programming because you know how to do it. All right. I'll see you then. It's going to be fun. All right. Hello, dear friends, and welcome, welcome, welcome. So in this lesson, we're going to practice the KNN algorithm with Python. So let's dig right in. So let's check it out. Obviously, we're in Jupyter Notebook. Now, my friends, imports are all ready to save you time, right? So you don't have to buy me coffee or anything. Just run the code directly, and we've saved some time. Now we can load the data set. So I want to first write a title. Now I've converted the following code cell to Markdown format and wrote the following data set in it. So let's run the code. Okay, my friends. So we're going to work with a data set that we will load from the outside in this algorithm. And now we can import the data set. And I will create a data frame. I'll say df equals and call the read CSV function from the pandas library. Now I'm writing that data set into it. I'll say telecust.csv. And let's call it the data frame. So I'll say df.head. Okay, so you see, my friends, here's the data set. Now let's go ahead and get to know this data set a little bit more intimately. So check it out. This data set belongs to a telecommunication provider. So here, customer data is segmented according to service usage patterns. So we're going to consider customers as 4 different groups. So the company offers these 4 different customer types based on the available data. So for example, we will use demographic data such as region, age, and marital status to predict usage patterns. And then based on this data, we will present proposals to customers. Now, a classification problem was actually requested from us. Given the data set with predefined labels, we need to construct a model that will be used to predict the class of a new or unknown case. You with me? Let's do it. We're going to create this model with our KNN algorithm now that you know everything about it. So we know the data set. We can examine the variables in the data set now. So I'll open up a new markdown cell and write getting to know the data set in it. Okay, so now I want to create a for loop to analyze the variables and their contents. So I'll start the loop just by saying for, and now I'm writing the value that the variables are going to come in order, and I'll say I. So I'll continue with in df.columns. We will reach the values in the data frame in order. All right, so we can now switch over to the body. First, let's output the variable. I'll say print I. Now we want to see the values and the numbers in the variables. We'll use the value counts function for this. I'll say print, and I'll write dfi.valueCounts. See, this way, the value information of all variables will come up to us in order. So now I'm writing the value consisting of hyphens and print so that the variables do not mix. Okay, cool. So now everything's ready. Let's run the code. Now check it out. We got a really good result, the one that we were predicting, right? Let's get to know the variables. So in the data set, the region first welcomes us. The region represents your customer's region. And customer data consists of a total of 3 regions. So here you see the count of the values on the screen. All right, so let's continue. There is a tenure variable. So this variable represents how long the customer has been with the telecommunications company. And check it out, it has a lot of value. Okay, so age is the age of the customer. Marital will, of course, represent the marital status of the customers, and this will be a value of 0 if single and 1 if married. But check it out. When we look at the total number of values, we see a situation close to each other. So let's continue a little further. And there's an address variable. This variable is a numerically encoded form of the addresses of the customers. An income variable expresses the income of the customers. And next up, we have the variable ed. Now, to be honest, I couldn't actually find what that means anywhere. It wasn't actually written in the data source either. Just another side note to always make a comment. So I'm just going to drop this variable from the data set. If you want to, you can go ahead and insert it into the model and examine what you come up with. But for now, we're going to continue. And next is the employee variable. So this variable is numerically encoded according to the companies the customers work for. This does not affect the target variable, though, and I want to remove it from the data set. And we'll continue. There is a retire variable. So this is a variable that represents whether the customer is actually retired or not. So a value of 1 here indicates that the customer is retired. 0 indicates not retired, right? And then right next to it is the gender variable. And this, of course, represents the gender of the customer. Okay, now, the residence variable represents the numerically encoded form of the customer's residence. Now, check it out. We have a custcat variable. And this variable is the target variable. It represents the categories of customers. So this variable has 4 possible values corresponding to 4 customer groups. It classifies customers under 1, basic service, 2, e-service, 3, plus service, and 4, total service. All right, so we're asked to create a model that makes predictions according to these 4 classes. So now I'll do the necessary action on the variables that we want to reduce. So I can say here df.drop, open the square brackets, and now I'm going to write values that I want to drop here. So I'm just writing ed and employee for the variables that I want to drop. And I'll continue and set the axis parameter to 1 and the in place parameter to true. Now let's run that code and check the data frame. I'll say df.head. And now let's get some more detailed information with the info method. I'll say df.info. And see here, my friends, we now have a data set of 10 columns and 1,000 rows. Variables have no null values. Therefore, we will not deal with operations such as filling in any blank values, okay? Now, 2 variables have a float, and 8 have an integer type structure. All right, so my friends, I want to leave you with that because this is our first part of this particular lesson. I'll see you on the other side. All right, so here we are, my dear friends. Welcome back. We've got a great lesson in store for you, but you know I say that every time because it's true. This lesson, we're going to continue right where we left off, actually, on this KNN algorithm. So we're going to do a bit of exploratory data analysis now. Won't you join me? So my friends, I will not keep the EDA part too long since our primary goal is to understand the logic of this KNN algorithm. So basically, I will have completed this section only with heat map visualization. So I'm going to open a cell in Markdown format and write EDA in it, and we'll run that code. Now let's determine the correlation between the heat map and the variables. So first I'll just adjust the size of the image here. I'll say plt.figure. And I'm setting the fig size parameter 15 to 9. And I'll go down to the bottom line and call the heat map graph from the Seaborn library. So I place a correlation of the variables with each other in it because I want to visualize it, right? Okay, so I'm going to say df.corr. Now, let's set some of the parameters. I'm going to put anote, a NNOT. So this parameter is going to be true, and this will parent the correlation coefficients on the images. So I'm going to continue here and set the line width parameter to 0.5. What this does is open and break up the boxes in the image. So finally, I'm going to determine the color of the image. I'll set the CMAP parameter to be spectral. And here I'll say plt.show. Now I can run the code. Nice. See, the correlation coefficients are right in front of us. And of course, you can examine the relationships between the variables. But right now, I just want to examine the relationship between the target variable, cust_cat, and the other variables. So see here, the variables retire and gender have little correlation with the target variable. The correlation between them is almost non-existent. So we can actually exclude these 2 variables from the data set. And yeah, there's a small relationship with the other variables. Okay, though, the significant relationship, of course, seems to be with this tenure variable. So from here, we can basically conclude, right? After creating the model, we may not get a very high score because the variables don't have a great relationship with the target variable. Follow? So what do we do about that? We can produce new variables by doing feature engineering, or we may request different data from the company. However, since our main topic here is to learn the algorithm's logic, let's just skip over this part. Okay, so what we'll do is drop the 2 variables with the lowest correlation from the data set. You understand now why? Cool. Then we'll set the axis parameter to 1 and the in-place parameter to true. Now let's run the code and call the data frame structure again. Now look at this, we get the result that we were talking about, right? I want to try something new though with you. Look at this. I'm going up, and here the region and reside variables are actually in a categorical structure. So that means that we can convert these 2 variables into a binary structure by applying the getDummies method to these variables. You remember that, so let's do it. So yeah, right here I'm specifying the new variable. I'll say region equals and call the getDummies function from the pandas library. Now I'm writing the variable in which I want to apply the getDummies method. So I'll say df region, and since I want to reduce the redundant column, I'm setting the drop first parameter to true. Okay, so now let's do the same for the other variable. And to save a little bit of time, I just am taking the code here and pasting it below. And I'll change the variable name, of course, and you can see the rest. All right, so now everything is ready. We can run the code. And now I can drop the old version of the variables from the main data frame structure. If I say df drop and write the variables in a list, then I can set the access parameter to 1 and the in-place parameter to true. Let's run that, see what it looks like. Cool. So now let's add the new version of the variables that we created with getDummies to the new data frame structure. I'll perform this operation with a concat function. So I'll say df equals and write df region reside. Cool. So now we want to add them side by side. So I'll set the access parameter equal to 1. Let's run the code. And I'm calling the data frame again. And look at that. Turns out exactly how we want it. All right, so we can continue on from here. We want to do one last thing before moving on to modeling. And what's that? Standardization process. All right, so yeah, we might just have to learn something new here, but that's all right. I'll take you through it. See, some machine learning algorithms are distance sensitive. And in algorithms that are distance sensitive, it's necessary to standardize the variables. I wonder if you noticed, some of the variables in the data set consist of 0 and 1, right? These values here. Some consist of, well, values in different intervals. So in this case, the distance-based algorithms don't actually give good results. So therefore, it's necessary to carry out some standardization work. Now, what do we actually mean by standardization work? Well, my friends, the process of standardizing the data is called standardization to change the values, put them in a specific format, and it allows them to be processed in this format without destroying the information and the variant structure within the variable itself. Yeah, so we're going to do this with a standard scalar right here, right now. Stick with me. The standard scalar makes the mean of the variable 0 and the standard deviation 1. You see where we're going? So it brings a distribution closer to normal. So let's see about working it into our example. First, I want to open up a cell in Markdown format, and I'll write standardization of variables within it. And now let's run the code. Okay, so first of all, I want to import the standard scalar. And I'll say from sklearn, call the preprocessing module from the sklearn library. Then I'll perform the import by saying import standard scalar. Let's run the code. All right, my dear friends, look at this. We'll determine now which variables that we will standardize. So I'm specifying a new variable. Okay, so I'm going to say scaled variable is equal, then write df, open up a couple of square brackets because I'll be slicing. Now let's go up here and check it out, my friends. Here, tenure, age, address, and income variables are different from the others, so we need to standardize these variables. So yeah, here I'm just writing these variables in the square brackets in order. And let's run the code. All right, so after that, I'll just call the data frame. I say scaled variable, and there you go. As you can see, we've got the variables that we wanted. So that means that we're ready to start the standardization process. So first I'll need to create a standardization object, okay? So I'll say scalar equals and set it to be equal to the standard scalar function. And now let's run that code. Okay, so now we'll be able to fit this object with the above variables. So what I do here is say scalar.fit and write a scaled variable in parentheses. Okay, so let's run that code. And there, you can see that standardization has taken place. So now we can transform the data with the transform method. So I'm creating a new scaled variable, and I'll say equals. I'm calling the scalar object. And this object has now learned standardization. So now it's time for transformation. So I can apply the transform method right here. And now I write the scaled variable again in it, and let's run the code. And there you go, my friends. We're going to call the new variable. I'll say scaled variable.head. Boom, there's an error. What? Yes. Did you notice the newly created variable is an array? So what are we going to do about that? Well, we'll just need to convert this variable to a data frame structure, and you know how to do it, right? So let's do it together. I'll say df scaled equals, call the data frame function from the pandas library, and I'll write the variable that I want to convert into it. And I'll equate the columns parameter to the list that I created above. So the data frame columns will be made with these variable names. Yeah, so now let's run the code. And now we can call the data frame structure. I'll say dfScaled.head. And look at that. The variables have changed into the format that we want. All right, so let's go ahead and call the main data frame structure. I'll say df.head. And yeah, we'll drop the old version of the variables from this data frame and add a new version. So for that, I'll say df.drop and write the variables that I want to drop in a list. I'm setting the axis parameter to 1 and the in-place parameter to true. And let's run the code. So now let's go ahead and add the standardized version of the variables to the data frame. I'll say df equals and call the concat method from the pandas library. I'll write the data frames that I want to merge into a list. And finally, I can set the axis parameter to 1 and run the code. All right, so let's call the data frame structure once more. I'll say df.head. And there it is in front of you. The data frame structure is now in the format that we want. Okay, so we're now ready to move on to modeling. But guess what? We're not going to do it here. We're going to do it in the next video. So let's wrap it up here. I'll see you next time. Bye for now. Yes, indeed, my friends. Welcome back. Because we're going to create a machine learning model using the KNN algorithm right now, right in front of your very eyes. So let's get started without talking about it. So first of all, I want to set a title in Markdown format, and I'm writing KNN modeling. And now I can split the data set X and Y, and I'll say X equals. Now, my friends, this variable will be all the variables except the target. You follow? So I can achieve my goal if I just drop the target variable from the data frame. All right, so I'll say here df.drop and write the target variable that I want to drop in square brackets. Now, since I want to reduce on a column basis, I'll set the axis parameter equal to 1. And yeah, the X variable has now been created. Now let's make the Y variable. So I'll say Y equals and call the target variable from the data frame. And yeah, let's go ahead and run the code. All right, so now it's time to split these two variables into two different sets, right? One for test and one for train, because we're going to use the train test split method. So first, I want to import. I'll say from sklearn dot and call the model selection module. Then I'll import the train test split function by saying import train test split. And now we can create 4 variables. Now we know these, right? So we'll just jam through it. I'll say xtrain xtest, ytrain ytest equals, and call the train test split function. And I'm putting X and Y variables in it. And I'll continue with setting the test size parameter to be 0.2. Now to get the same values every time, I'll just set the random state parameter to 42. Let's go ahead and run the code. Yeah, so let's write code to see how it performs a division. So I'll say print train set, and after that I'll call the xtrain variable and apply the shape method. I'll call the variable ytrain and apply the shape method to that. And to avoid taking up too much time, I'm just going to copy all that code, paste it in here, And I'm changing the train parts to test because I want to see the test data dimensions, right? So let's run that code. So check it out, my friends. It divided the train and test data set into 800 by 200. Now, it's time to create the model with a KNN algorithm. So I'll perform the import operation. So I'll say from sklearn and call the neighbors module. Then I perform the import by saying import kneighbors classifier because it will classify it. All right, so that's the way we import the KNN algorithm. Now, I said it could be used for classification and regression when we were talking about the KNN algorithm earlier. If you do use it for regression, you should call the kneighbors regressor function after typing import. Okay, so we can create the algorithm now. Let's first determine the k-value. For example, we'll say k is equal to 4. Then we'll keep the distance value default. Okay, so we'll continue with KNN model equals, and I'll call the kneighbors classifier function. Now I'll equalize the parameter nneighbors to the k value because I previously set that. The value of k was 4. Yeah, so now it's time to fit the model. Cool, so I'll say KNN model.fit and insert the train data into it. I'll say xtrain and ytrain. All right, let's call the model. Now look at this, guys. The model's created, so we got to be able to test the model, right? So I'm making a variable, and I'll say ypred equals, and call the model, and apply the predict method. So I'll put test data inside this method because I want to, well, test it, right? So I'll say xtest. Let's run the code. Yeah, so there you go. We can have a look at the model's success. Now I need to import the metrics model to look at the metrics. Let's go ahead with that by saying from sklearn import metrics. Yeah, okay, so now let's print the score. So I'll call the print accuracy score. And continuing on with the accuracy score function from the metrics module. So this function first takes the actual values into it. That's why I say ytest. Then I put the forecast data here. So I say ypred. Let's run the code. Okay, so we get a result of 32%. Now, the score is kind of low, right? However, do you remember when we looked at the correlation between the heat map and the variables? We found a very weak correlation between the target variable and the other variables. But didn't we deduce that the model would give us a low score? And this is what you're looking at. However, despite this low correlation, it does show the success of the KNN algorithm. Okay, let's do a study by changing the k-value. Is it going to make any difference? Will it shift the score? So I'll take the code here, paste it below just to save a little time, and I'm changing the k-value this time to 6. And I'm making a model name and a model number 2. Okay. So I'll just grab that code again and paste it in. And here I'm changing the model name, of course, and now we can see the score. So I'm just going to take this part of the above code here, copy and paste, and let's run the code. So what do you see, my friends? The score has increased. See, increasing the number of neighbors affected the success of the model. Now, did you notice? I increased the k parameter myself, and I wanted to reach a better score just by experimenting. So you can do that too, just by changing other parameters. But can we find the best values of these parameters in a more specific or scientific way? I mean, not just arbitrarily, according to whatever the heck we feel like at the moment. Of course we can, my friends. That's the answer, of course. In fact, the best thing to do is to find it that way. In other words, to determine the parameters and the results based on scientific and mathematical foundations that you know and love. So, how do we go about performing the determination based on scientific and mathematical foundations? Well, I want to introduce to you another concept, hyperparameter optimization. Okay, so while you go off and learn how to spell that, I just want to wrap it up here, and we'll do all that in another video. I'll see you next time. Bye for now. All right. Hello, my dear friends. Thanks for coming back. Welcome. Now, we have learned all about cross-validation. Previously, we talked about using the cross-validation method to evaluate model performance. So we have now come to the point where we need desperately to examine hyperparameter optimization, which is a second usage area of cross-validation. Okay, let's get started. So first, we need to start by defining what the heck hyperparameter optimization is. Well, you know what a hyperparameter is, right? Machine learning models are based on mathematical functions representing the relationship between dependent and independent variables, target features. So for a quick example, in linear regression, there is a linear relationship between dependent and independent variables that can be expressed with a function y equals mx plus b. Yeah? Okay. So during the training of that linear regression model, the most appropriate m and b values are determined using various optimization techniques. So these values are the model parameters. Unlike the parameters, the hyperparameters are not learned during the model's training. See, the data scientist comes in and has to determine them before the modeling phase. So for example, this KNN algorithm, one of the non-parametric classification algorithms we learned previously, classifies by looking at the k-neighbors closest to the value to be estimated. So here, the number k and the distance metric to be used are among the hyperparameters that the data scientist in you should specify before modeling, and that increases the performance of the model. So in other words, we will indeed choose hyperparameters to improve the model's performance. But see, that's why we're data scientists, because we know what we're doing. Okay, well, maybe not quite yet, because how do we choose? Well, my friends, the selection process is actually what's called hyperparameter optimization. All right, hyperparameter optimization is a process of finding the most appropriate hyperparameter combination according to the success metric determined for the particular machine learning algorithm that you're using. So with this thing called hyperparameter optimization, the model complexity can be balanced and a balance of overfitting and underfitting can be achieved. So again, the overlearning problem caused by the model's flexibility can be solved with the constraints imposed by hyperparameters. All right, so now that you know the responsibility lays on you, let's talk about hyperparameter optimization methods. Now, considering, of course, that there are tens of hyperparameters and tens of values that these hyperparameters can take for any given machine learning algorithm, it's clear how difficult it would be to try all the different combinations one by one and then choose the best one. So for this reason, different methods have been developed for hyperparameter optimization that you are more than welcome to use. That's right. So a couple of these methods are grid search CV and randomized search CV. Now, by the way, cross-validation is a hyperparameter optimization technique within its own, right? However, since these are the ones that get used the most, well, derived from cross-validation, that's why we're bringing them up here. Let's have a look at the working principle, the pros and cons of grid search CV and randomized search CV as distinctly different methods. So we'll first start with grid search CV. So here a separate model is created with all combinations for the hyperparameters and their values to be tested. The most successful hyperparameter set is determined according to the specified metric. So the main advantage of grid search is that it guarantees to identify the best performing hyperparameter set as all combinations are tried. In fact, it works really well in small data sets and when only a few hyperparameters need to be tested. But if you have a look at the disadvantages, you could say that when working with an extensive data set or when the number and value of the hyperparameters to be tried increases, well, the number of combinations will increase exponentially, and that's a lot to sort through. So considering that each established model is tested with cross-validation, the cost will increase tremendously as well. So that's why, and therefore, the random search CV method may be preferred as a unique alternative. So let's just go through that a little bit. So we've got a set of hyperparameters that is randomly selected and tested by cross-validation. Now, these steps continue until the specified calculation time limit, or the number of iterations, is reached. Right, so that brings with it a number of advantages. Among them, it can identify hyperparameter sets that will perform close to the best score obtained by the grid search CV method with less cost in large data sets. It can scan a wider hyperparameter area. But there's a disadvantage. Although it approaches the optimum hyperparameter set, it cannot guarantee finding the best performing one, since it only tries some of the possible combinations, one by one. So you get it. We can wrap it up here. And in the next lesson, we're going to continue with working on optimizing hyperparameters in Python. I'll see you then. Bye for now. All right. Hello, my dear friends. Welcome back. So right here, right now, we're going to perform hyperparameter optimization using Python. Okay. So we're going to conduct our investigations through this KNN algorithm established in the previous lesson model. So you should know where we're going. Let's do it. You remember there was a telecust data set. And in the last stage of this data set, we created a model by determining the K value. And we made two different trials for the K value, the values 4 and 6. So we're going to do it with grid search CV. So now we'll perform these values not with trial and error, but by using grid search CV, which is a more scientific parameter selection, of course, which is what you were jonesing for to begin with. So let's first write a title in Markdown format here. And I'm just going to write hyperparameter optimization with Python and run the code. All right, so now I need to import the grid search CV method. And I do that by saying from sklearn dot, I'm calling the model selection module from the sklearn library. So I can now import the method, and I'll say import grid search CV. And here, my friends, everything looks ready, so let's just try to find the best parameters. So first I want to create a new model object. I'm specifying a new variable. I'll say knn model3 equals and call the kneighbors classifier function. So let's run the code. And check it out, my friends. The model object has now been created. So now I need to create a dictionary. Inside this dictionary will be parameters and values that the grid search CV method will try to find the best. So I'm specifying a variable for the dictionary, and I'll say knn params equals. Okay, so now we can create a dictionary. The dictionary's keys will be the parameters. Yeah. And the values will be the values that we want to see in the parameter. So the first parameter that I want to try is a number of neighbors. I'll say n neighbors and use the arrange function in the NumPy library to set a number range. So for example, I'll say np.arrange and write 1 to 50. And okay, so our first item is now ready. Grid search CV will try these values from 1 to 50 for the number of neighbors, and it's going to tell us the best result that it finds. Okay, so we'll move on. For example, we left the metric and weights parameters as default values previous models that we demonstrated. So let's just now set the values in these here and try to find the best one. So I'll write metrics and open the list parentheses. In this context, I'll write different metrics within the list. So I'm writing Minkowski, Euclidean, and Manhattan. So these three values were the values of the metric parameter. Yeah. The default value was Minkowski. You do remember that. So now we wanted to find the best of these three. Okay, continuing on. I'll write the weights parameter and open the list parenthesis. And I will write two different values within it. I'll write uniform as the first value and distance as the second value, right? Because the default value was uniform. All right, so that's enough parameters and values for now. But you noticed I only tried to find the best of three different parameters. However, you can increase the number of parameters and the number of values in them. So in other words, you can write all the other parameters and values in the algorithm here if you want. And actually, that's something for you to remember, because the more parameters and values that you enter, the more costly the model will be for you. Okay, so now I am creating a new variable. Say KNN-CV model equals and call the grid search CV method. And I can do a shift tab in it. And check it out. There are the various parameters. So we're going to use 3 of these. And we will determine the name of the model with the estimator parameter. We'll place the dictionary containing the parameter value pairs defined above in the param grid parameter. And finally, we will determine the amount of cross-validation with this CV parameter. Yeah, so let's just get to it. All right. Writing an estimator and setting this parameter to KNN model 3. Now, my friends, 10 is an optimal number for a CV. You can increase it or decrease it if you want to. But now you see how everything is ready, so let's run the code. All right, so the grid search CV model has now run. Let's finish it up. So I'll write the variable and apply the fit method to it. And I'm putting the train data in it. I'll say X train and Y train, and we'll run the code. Now, my friends, I'm sure you've noticed that this process takes some time, and we're just working with very small data sets here. The reason why that is it tries each parameter with the other parameters one by one, and it repeats each operation 10 times because of this CV parameter, right? That's why the process takes a long time. It's okay. But like I was saying, we have a very low capacity data set. Now, if you were timing it, though, how long did it actually take? Well, just imagine, though, working with hundreds of thousands of data at once. It can take a while, okay? Just as a warning, I'm going to continue now. The model is trained, and we can find the best of these parameters. So let's check it out, my friends. We'll find the best parameter with the best params method. And here I'm writing the variable and applying the best params method. So let's run the code. And there are the values that come up, as you can see. So according to the grid search CV method, the best parameters to be used in the KNN algorithm are as follows. It specified Minkowski for the metric parameter, 15 for the neighbors parameter, and uniform values for the weights parameter. Now, I know you were paying attention right, because it's already showed the default values in the KNN algorithm as the best for the metric and weights parameters. So that means, yeah, there's no need to change those two values. But you see how it specifies the number of neighbors? 15? So yeah, we can actually reconstruct the model since we get the values that can be the best parameters. So I'm specifying a new variable. I'll say KNN tuned equals and call the KNeighbors classifier algorithm. I'll set the nNeighbors parameter to 15. I'll leave the other parameters as default. And now let's run the code. All right, so now the model object has been created. It's time to fit this object. So I write the variable in the cell and apply the fit operation. I'm writing the training data set in it. I'll say X train and then Y train. Let's run the code. Okay, my friends, the model has now been trained. Now it's the estimate time. So I'm creating a new variable, and I'll say ypred equals, and after calling the model, I apply the predict function. Then I can put the test data in it. I'll say X test, and we can run the code. All right, so now let's print the score. Now, to avoid taking up too much time, I've just copied all this from above and pasted it below. So let's just run that code. Okay, so you see that the score has increased, so it's going up. And as you can see, our final score was 32%. Now, after doing a grid search, this score increased to 35%. Now, by the way, I do want to mention one more thing. Grid search aims to find the best parameters. So, in other words, you can't think of it like it's going to just automatically increase your model's success. Because I wonder if you noticed, we're not trying all the parameters. For example, we tried to find the best values of only 3 parameters for this model. Now, perhaps it was the other parameters that we should have wondered about. However, when we did such a study, we're doing the most important ones first. So, to summarize all of that, grid search increased the score in this model. So therefore, we can use the model as it is. However, when we're working with other models, grid search may not be enough. It might not work. It's kind of rare, I'll tell you, to be honest. But just when you get the result, be prepared that you might have to adjust. Okay, my friends, there we are. Let's wrap it up here. I want to see you next time, though. All right, hello, my friends. Welcome back. I'm glad that you're here because I want to introduce you to a new machine learning algorithm. Say hello to decision tree. Yeah, you might have heard of decision trees in an analog form, perhaps, because a decision tree is a structure used to divide a set of large numbers of data into smaller groups by applying a set of decision rules. So in other words, it's a structure. It divides large amounts of data into smaller groups of records and applies simple decision-making steps. That's how you break it down. But you're going to come across decision trees everywhere because they can be used in classification and regression problems. But to be honest, it's generally used more often in classification because it's genius, all right? So we'll examine the structure of this particular algorithm. The first cells of decision trees are called roots or root node. So each observation is classified as yes or no according to the root condition. So these root cells contain nodes or interval nodes. Each observation is classified with the help of nodes. So as the number of nodes increases, so does the complexity of the model. So the bottom of the decision tree are these leaves or leaf nodes. But it's the leaves that gives us the results. All right, my friends, I want to take these definitions in more detail as we work through an example. Okay, so check it out. Here is a representative tree. Now, our main question is written on the tree, right? Should I accept this job? So yeah, we're going to prepare some questions to answer this central question. Now, I wonder if you've noticed here, there's a question at the top of the tree. And what's it asking? Is the salary more than $100,000? Well, see, this is the root node of our question tree. If we answer yes to this question, well, the tree will produce branches downwards. If we say no, hey, it's easy to reject the offer. Okay, so you're paying attention, right? The tree structure is shaped according to the answers to the questions that we're asking. So let's continue through this and let's just pretend to say, yeah, okay, $100,000 is fine. And if we say yes, interval nodes begin to form. Now, you can also see them in the figure. So yeah, we're asking a new question to finish it up. Is the business type home office? So if we say no to this question, we reject the job offer. However, if we say yes, other interval nodes are formed. You see? So let's just say that we say yes, and we'll examine the last question here. And what is that to be? Is the annual leave 20 days? So we will reject the job offer if we're saying no to this question. However, if we say yes, we will accept the job offer. Okay, that's it in general. So what are we doing here, my friends? We got closer to our goal each time by asking the main question. Now, in the end, our goal is in its purest form. So we call leaf nodes to reach a result according to the decisions made in the decision tree. So yeah, that's the general structure. That's kind of the logic of how this algorithm is understood. So I do want to continue. But first, how do we choose the first question in a decision tree? Well, sure enough, my friends, we want the root that we will choose here to explain our data set as thoroughly as possible. So, for example, if we look at the decision tree in the previous model, the most critical factor in the job offer for this person was the salary. All right. So yeah, various factors in the algorithm decide this first question. So we usually call these factors parameters. Well, which parameter is most helpful in this algorithm? Well, my friends, the parameter used in this algorithm is criterion. Now, this takes two values, all right? One of them is Gini, and the other is entropy. So I want to first start with a Gini parameter. Gini can be called the purity value of the subset. This parameter is calculated for each class, and the sum of the squares of the results is subtracted from 1. So the Gini value returns a result between 0 and 1. And the closer the effect is to 0, the better the discrimination. Now, I really don't want to go into the mathematical aspect of this operation because it's just not what we're doing. If you really do want to understand all that, go ahead, research it. Internet is your friend. But I'll continue on here with the other criterion that we need to examine, and that's entropy. So entropy is a measure of the uncertainty about our data. Now, intuitively, a data set has lower entropy if only one label exists, yeah? For example, while working on Python and the KNN algorithm, there were 4 tags in the target variable of the telecust data set that we worked on. Therefore, entropy is high in this data set. So that means we need to divide our data to minimize entropy. The better the divisions, the better our estimate. So again, I'm not going to get into the explanation of how that's calculated mathematically. Go ahead and do that research on your own time, because I want to take this talk a little bit deeper into some of the other important parameters. So check it out. There's a parameter called max depth, my friends, and it represents maximum depth of the decision tree. Now here, if no value is entered, it will be unlimited. If the model is overfitting, it should be downgraded. Another parameter would be min sample split. And this, my friends, refers to the minimum number of samples a node should have before splitting. Okay? But here we have another parameter. That's min samples leaf. So this would refer to the minimum number of samples a leaf should have. Okay, so we'll move along to the parameter max leaf nodes. And this, of course, would be the maximum number of leaves. So you see, my friends, how this works? Cool. Well, the last parameter that I want to take you through is max features. So this is the number of features to consider when looking for the best split. Now, I would like to bring your attention to an important issue here. You can consider these parameters to be hyperparameters. Yeah, so when you're facing problems such as overfitting or underfitting, you might just need to play around with the hyperparameter values, right? So as we generally understand the logic of decision trees and examine their parameters, I want to bring you through some of the advantages and disadvantages, and then we'll wrap it up here, okay? So some of the advantages are definitely easy to understand and interpret, right? The tree structures used can be visualized. And it actually requires very little data preparation. However, I do want to make a note that this model does not support missing values. So we must fill in any missing values in the data set. The cost of the tree is logarithmic to the number of data points used to train the tree. So in other words, the cost increases as a number of data points increase. It can process both numerical and categorical data. It can also handle problems with multiple outputs. So in other words, data sets with more than one label number of the target variable can be studied within this algorithm. It is also very possible to verify a model using statistical sets. But as always, with some advantages, there are certain disadvantages. Yeah, sometimes you can get some overly complex trees that, well, they just need to explain the data better. So in this case, tree pruning may not actually be followed. And then, of course, the pruning refers to removing leaf nodes containing few objects from the decision graph. So let's just wrap it up there. And next time, we're going to practice using Python. All right? See you next time. Bye for now. Well, hello, my dear friends. Welcome back. We've got a great lesson here. We've talked about the decision tree algorithm previously. So now we're going to work on this algorithm with Python. Let's get into it. All right, so you can see here the imports are ready, and I'm running the code directly. Now let's load the data set. So I'm converting the following code to Markdown format. I'll write loading the data set inside. All right, so my friends, we're going to work on the iris data set built into Python. Now, we will perform the loading process as loading from an external source, not with a load dataset function. So there is a file named iris CSV in the file where I'm working on in the notebook, right? You can, well, in fact, I'll just upload it right now. So first of all, I'll need to set a variable. I'll say df equals and call the read CSV function from the pandas library. I'll write iris.csv in it. And yeah, let's take a look at the head of the data frame. I'll say df.head. All right, so check it out, my friends. There's our data set. And this data set is a data set that includes different flower types and their sizes. So here we're going to attempt to classify the type of flower by examining the characteristics of different flower types. All right, so now let's get to know the variables in the data set. The first variable is the ID variable. So this is the index of the data set, right? Now, if you've noticed, it starts from 1 and continues increasing. So there's actually no need for this variable because Pandas already assigns an index number when creating data frames. So after examining those variables, we can just drop this variable from the data set. Okay, so let's continue. And the following variable is sepal length in centimeters. All right, so this variable expresses the value of the sepal leaf length in centimeters. Cool. Right, the sepal is the part of the flower that is the outermost ring. It's usually consisting of green leaves. Okay, you're not a botanist? Well, neither am I. But that's okay. We need to learn everything, don't we? Anyway, the sepal width, cm, well, this is the variable that's right next to it. The variable represents the width of the sepals. So now we've got these other two variables, length and width of the petal features of the flower. So the petal is a part of the leaf inside the flower. And we'll continue on to the last variable, this species variable, and this variable refers to the type of the flower. All right, so now that we've learned what the variables that we're working with mean, we can now move on to the analysis part. So I can open up a cell in Markdown format here and write getting to know the data set. Okay. Now, my friends, let's first see the type of flowers and their numbers, okay? So see here, I'm calling the data frame and applying its value counts function. And let's run that code. Now, there we have 3 types of flowers, and forgive my pronunciation, any Latin scholars, but we've got Virginica, Setosa, and Versicolor. So I wonder, do you notice the flower types have the name of the data set at the beginning? So I can just remove this from the data set in a minute. But you see, though, that there are 50 of each of these flowers in total. Okay, so now I'm going to want to do a few things to organize a data set. So first of all, we can just lower the ID parameter in the data set. So I'll say df.drop and write the ID variable. And I'll set the axis parameter equal to 1 because I want to reduce it on a column-by-column basis. And to make permanent changes, I'll just put the in-place parameter to be true, okay? So now let's run that. Yes, indeed. Now let's edit the names of the values of the species variable. So we'll remove the iris expression at the beginning of the values. Okay, so now we can make a reassignment to this variable. So check it out. I'll write df species equals, and again, I'll call the species variable from the data frame and apply the str replace function, right? So that's string replace. Now, my friends, this function is for changing characters in string values. I mean, I just all of a sudden thought, oh, wait, maybe you don't remember. So the string expression at the beginning of the data set provides the application to all rows. Yeah. Okay, so now we need to enter the string expression to be changed first and then the new value second, right here into this function. So I'll write iris hyphen and set the value that I want to be replaced as a blank string expression. Now let's run the code. And let's check the data frame from the head. So I'll say df.head. Check it out. The data set is turned into the format that we want. Booyah! So now I want to put 2 photos showing these flowers and their features to, visually represent them better, but we'll be able to understand them better too. So look here. We can actually see the types of flowers in the picture right here. So that way we can actually see what these other features mean. See, a picture, what do they say? A picture says 1,000 words or something like that. But you know what we're talking about. So what have we got? Now, we will request information from the data frame with the info method. So I'll say df.info. And now we can see all the variables and how many values are in them. Now, do you notice something? Are there any null values? No. So this is actually something that we want. So it means that we're not going to struggle with nulls later on. But you probably did notice 4 of the variables are float. 1 of them is an object. But my friends, we know our data set pretty well. We've examined all the values. So why don't we just wrap it up here and we'll continue where we left off next time. All right? I'll see you in the next video. And we're back. Here's the next video, my friends. Welcome. So we're going to continue with our Python practice, learning this decision tree algorithm and playing around to see what we can do. Now, let's just get into it. We're going to do EDA to learn the properties of the variables in the data set and their relationships with each other in a lot more detail. So I'm going to convert the following code to Markdown format, and I'm just writing EDA into it. So my friends, I want to first work on the data set with a pair plot. Now, a pair plot is going to allow us to see the distribution of single variables and the relationships between 2 variables. So I want to call the pair plot function directly from the Seaborn library, and then I'll write the data frame inside. Now, I want to show you how to add a 3rd dimension to the chart. I want to do this with a hue parameter. So I'll set the hue parameter to the species variable. And this way the graphics are going to be colored according to the species variable, right? Okay. Now, finally, I'm going to set the height parameter to 2.75. And this is going to help to enlarge the visible part of the graph. All right, my friends, everything looks ready. Let's go ahead and run the code. All right, so that's a pretty neat looking graph. Axes have variable names. And you can see what the colors mean by looking over here on the right. All right, so when we look at the diagonal, we see the distribution graphs of the variables with the target variable. And here the variable that has the most relationship with the target variable is the petal width CM variable. right? And I know you're paying attention, so the separation of flower types is very clearly delineated. All right, so moving on, you can also see that it has a high correlation with the petal length variable. However, the setosa flower is more prominent in this variant. So let's move along here. The variable with the slightest relationship with the target variable is the sepal properties. Now, if you notice, the distinction cannot actually be made very well in the sepal width CM variable. The colors kind of seem so intertwined, don't they? But when we look at the correlation between the variables, you can actually see that there is a perfect correlation between the petal properties. So if there is too much correlation between two variables, one can be dropped from the data set. But I want to decide on something other than this current analysis. So I'm going to keep that in mind, and I might consider that at a later stage. So I wonder if you wonder, what other inferences can we make from this chart? Well, I think it's enough for now. I'm going to just make note of what I told you before and continue along. So we're going to call the data set again. And now I will use the heat map graph to see the correlation between the variables in a different way. All right, I do want to mention one thing, though. The heat map graph only shows a relationship between numerical values, remember? So what are we going to do about it? Well, you notice that the species variable here, it's a categorical structure. So could we convert the target variable to a numeric one? I think so. So I'm going to create a new column. I want to create a new variable for this as well. I'll call the data frame and write species num equals for the new column. I'll equate this variable to df species. Let's go ahead and run the code. Now let's call the variable again and check it out. Two columns are melded into one. So now I want to convert the last variable to numeric format. So I'll do that in a little different way. We can actually replace the characters using the replace method. Okay, so I'll say df species num equals and call the variable again. I'll write str on it and apply the replace function. And I'll write setosa1 in it. All right, so now the setosa flower will appear as 1. I do want to do the same for the others. So I'll take the code and just paste it below twice to save any time. And I'll change the values within. I'll write 2 for versicolor and 3 for virginica. Okay, so everything looks ready. Let's run that code. And now let's run the data frame again. So see here, my friends, we had a thought, we had a question, we said, hey, let's see if we can do it, and we did it. So I want to get some information from the data set with the info method. So I'll say df.info, and look at this. I want to make another point here. We have edited the variable just as we wish, but the type is still an object, okay? So we'll need to convert this variable to an integer. And I can do that very easily with the toNumeric function. So here I want to say df species num equals, from the pandas library, I'm calling the toNumeric function. And within it, I'll write df species num again. And then I can set the downcast parameter as an integer. So let's run the code. Now we can have a look at the info method again, and my friends, we certainly get what we wanted, yeah? So that means that we can now create a graph. So first up, I'll want to adjust the size of the graph. So I'll say plt dot figure, and in it, I'll set the parameter fig size to 15 by 9. And I'll call the heat map graphic from the Seaborn library. And just by saying df core, C-O-R-R, I get the correlation information of the variables. So I set the CMAP parameter to spectral and the ANNOT, annote parameter to true. All right, let's run that code. Well, my friends, correlation coefficients, what do you say? So here we can see that the analysis that we were making earlier with the pair plot are correct. Now, I wonder, did you notice the variable that the target variable has the most relationship to is pedal with CM? The variable with which it has the most diminutive or slightest relationship would be sepal with CM. Okay, so now I want to draw your attention to another point here. I wonder if you notice the correlation between pedal features is 96%. Now, actually, we saw this in our previous analysis. So what are we going to do? We can impose a lower cost on the model by removing one of these variables from the dataset. Now you remember. So in this context, I just want to drop the one with the least correlation with the target variable from the dataset. And by that, I mean the pedal length CM variable. Let's just do that. So I'll say here df drop and write the variable. Now, by the way, we're done with a numeric target variable, so we can drop that too. And here I'm typing species num, and I'll set the axis parameter to 1 and the in-place parameter to true. All right, so let's go ahead and run the code and call the data frame again. Wow, check it out. That's how you do it, my friends. So now we're ready to move on to the modeling phase. But guess what? We're going to do it in the next video. I think this one's long enough, don't you? All right, so take that and, well, do whatever you want with it. Or you can just march right on to the next video. You know I will. If you're here and I'm here, it means we're in the next video. And everything's right with the world, yes? Well, let's just continue with the modeling lesson, right? So we're going to dive right in. Now, you know, a decision tree is not an algorithm that requires standardization. Therefore, we can just proceed right to modeling. So yeah, first up, we're going to divide the data set into two, X and Y. Now, we'll create the first variable X. So I'll say X equals, and this will be all variables except the target variable. So therefore, I can do something like this. I'll say df drop, write the target variable. Then I can set the axis parameter to 1. Yeah, so variable X is ready. Now, let's hit up variable Y. So I'll say Y equals and make it equal to the target variable. That's how that works. We've divided the data set into X and Y. Now we want to divide our data into two as test and training sets with train test split. Now for this, I want to perform the import operation first. So I'll say from sklearn.model selection. Then I'll import the train test split method. So this is how we will create four variables. Now we know these things. We're going to do them quickly. So keep up. I know you can. I'll say xtrain, xtest, ytrain, ytest equals, and call the train test split method. So then I'm putting the x and the y variables in it. I'll set the test size parameter to 0.25 and the random state parameter to 42. Let's run that code. Cool. Let's import the decision tree algorithm now. My friends, the algorithm is in the tree module, so I'll say from sklearn.tree. I'll continue and write import decision tree classifier. Now let's run the code. Yeah, there we go. So now we can build a model, and I'm setting a variable for the model object. I'll say dt model equals and call the decision tree classifier function. Now let's run the code. So we've got our object ready. Now we can train it. So I'll say dtModel.fit and insert the training data into it. I'll say xtrain and ytrain. Now let's run that code. Okay, so are you ready to make a little bit of a guess? I mean, it's a prediction, right? I just want to create a variable, so I'll say ypred equals and call the model. I'm applying the predict function to it, and I'm writing the test data set in it. Let's run that code. All right, so there you go. The prediction was right. Now, of course, if you want to, you can go ahead and check the accuracy of the model. But if you want to just wait and do it along with me, I'm going to do that in the next lesson. All right, so let's wrap it up here and see you next time. All right. Hello, my dear friends. Welcome back. So we've created a model, right? We've carried out the test process. So right now we're ready to see the score of the model. So I want to get right to it. I want to import evaluation metrics. So I'll say from sklearn metrics, and I'll import the classification report, confusion matrix, and accuracy score metrics from this model. All right, so let's run the code. So let's have a look at the accuracy score first. So I'll say print accuracy score and call the function. And first I want to just put my y-test in it. And I'm inserting the y-pred. And let's run the code. All right, so check it out, my friends. We have a high accuracy value. That's 97%. But I kind of doubt the accuracy. So I want to do some cross-validation. You with me? So I want to perform import again. I'll say from sklearn.model selection and import the class-val score function. All right, so let's run the code. Now I can say CV scores are equal and write cross-val score variable. See, so in it, I'll equate the estimator parameter to the model name. So I'll set the X parameter to be Xtrain and the Y parameter to be Ytrain. So finally, I'll put the CV parameter to 10. Okay, so as you can see, the accuracy value has decreased. So its meaning is that the data set in different splits can establish a low accuracy model. You see? So now let's have a look at all the accuracy. So I want to say here, CV scores, and check it out, my friends. All the accuracy values are in front of us. Now, while we can see 100% success in some models, we can also see rates as low as 63% in others. But we're not done yet. Yes, let's evaluate the confusion matrix metric now. So I'll say print confusion matrix and write the variables y-test and y-pred in order. And let's run the code. All right, so here we've got our confusion matrix. Now, in this metric, rows represent actual labels and columns represent predicted labels. Yeah, so class names that will interpret the metric are actually not specified. So we can learn how to rank with metrics like classification report. So let's just have a go at interpret. So the machine has correctly guessed the 15 real values for the first class, right? There are no incorrect predictions. There's actually only one incorrect prediction in the other class. A perfect guess was made in the next row, and all were guessed correctly. Now, did you notice it actually isn't very easy to interpret the metric this way? If you want to, we can actually graph this metric and analyze it from there. I like that a whole lot better. I'm sure you will too. Of course you will, because I said so. All right, let's move on. I'm going to put this metric in a variable in this context. I'm going to say CNF matrix equals. And I'll take the code from above and paste it below. So now let's create a graph. I want to use a heat map. I'll say sns.heatmap. Put the CNF matrix variable in it. Then I'll set the anote parameter to true and CMap parameter to this value. Now you can go ahead and change the parameters, but we'll name the axes. I'll say plt.ylabel for the y-axis and write the actual label inside. Then I'll say plt.xlabel for x-axis. I'll write predicted label in it. All right, let's run the code. Wow, okay, so I love a good graph. Many people do. It's a whole lot easier to understand, and Here we can see the number of actual and predicted values within the three classes. All right, so let's examine the classification report metric. So I'll say print classification report and write y test and y pred. Let's run the code. All right, my friends, our model's F1 score value is 97%. 0 value is Setosa. 1 value, Versicolor, and 2 is Virginica. All right, so what do you think about working with a decision tree algorithm? So I want to draw the graph of the tree structure. Remember that. I mean, that's what you came here for, so that we can understand the working logic of the model that we have built, and you'll see why. So for this, I want to use the tree library, and I'll say from sklearn import tree, and then here, my friends, I'll use the plot tree function in this library. Cool. So we're going to give this function the names of the independent variable and the values of the target variable. Right? So within this context, we'll assign these values to the variables first. So I want to reach the independent variable names, yeah? So for that, I'll say df columns in the list function. So now, since we're going to get all but the last value, I can do indexing like this. I'll put a colon and say -1. All right, let's run that. Now, my friends, you see, it brings us the values that we're looking for. Now let's put this in a variable. So say features equals, and copy and paste the above statement just right in here below. And now I want to create the values of the target variable. I'll say targets equals, and write the 3 values into the list. Now let's print those 2 variables. I'll say print features. Then I'll scroll down and say print targets. Let's run the code. Now check it out, my friends. We've obtained the values that we're going to be using in the function. So now we can draw the graph. So first off, I want to determine the size of the chart. So I'll say plt.figure. I'll set the fig size parameter to be 20 by 20, okay? Next, I'm specifying a new variable in the line below. So I'll say tree2 equals. Now I call the plot tree function from the tree library. So I'll write the model name in it. Then I set the filled parameter to true, and this parameter will allow the information to be written on the graph. You see that, so let's continue. I set the feature names parameter to features and the class name parameter to targets. Now let's run that code. Well, check it out. Isn't that a magnificent tree? So we can see the whole tree system of the model that we built, right? So first, the question is going to be asked according to the value of the petal width CM variable less than 0.8. And the Gini value is a parameter. So yes, indeed, there are 112 samples, and they are divided into 3, 35, 39, and 38. Okay, so it classifies 35 as Setosa and classifies the other 2 as Versicolor. But doesn't it start asking new questions then? I wonder, did you notice the sample and Gini value decrease according to the questions? So when the Gini is 0, that's when we have or achieved purity, and the model answers the classification. So there you go, my friends. The decision tree algorithm logic is pretty simple to follow. I'm hoping you find it simple as well. But now we can do the hyperparameter optimization and see how the result changes. But guess what? I've saved that for another time. I'll see you in the next video. Bye for now. All right. Hello, my friends and everyone else, because this time you might be going, oh, man. But hey, we're here together. We're going to work through this step by step. We're going to make hyperparameter optimization with the model that we created with our decision tree algorithm. So we'll jump right in. And I've prepared, of course, the header and the imports. So I'll import these libraries just directly like this. So now I want to create a new model. Okay, so I want to say DT model 2 equals and call the decision tree classifier function. So we can run the code. And yeah, we've now got a model object. So now I want to create a dictionary to determine the parameters that we're going to try. I'll say DT params equals and open curly brackets. Now, I'm sure you remember from our theory that there are many parameters, but we're only going to really work with the three most common. So the first parameter is the criterion parameter. So we'll equate this to the Gini and entropy values in the list. So let's just see which of these two will be better for the model. Okay, so let's continue. I'll equate the max depth parameter to a range of numbers. I'll say np.range and write the values in it. All right, so I want to start from 2 and progress in 2 steps up to 14. Now, what was the max depth? It was the depth of the tree, right? So we'll continue, and I'll equate the max features parameter to 3 values inside the list. So these will be auto, squirt, and log2, right? Square root. Okay, anyway, this parameter answers the question of how to calculate the properties. All right, let's run the code. Ooh, so everything looks ready. We can now start the grid search CV. Yeah, that's why we learned it, right? So I'm setting a variable here. I'm saying DT CV model equals, and I'll call the grid search CV function. Now that I'm in it, I'll set the estimator parameter to be DT model 2. I'll equate the param grid parameter to the DT params dictionary that we created above. And finally, I can set the CV parameter to 10. All right, let's run the code. Okay, I'm fitting this model object. I'm writing the model's name and applying the fit function. Then I'm writing the training data in it. I'll say X-train and Y-train, and let's run that code. All right, my friends, now it's time to find the best parameter values. To do this, I'll call the model and apply the best params function. So we can run that code. Okay, so here we have the values that the grid search CV function chooses as the best parameter. So why don't we create a new model according to these values and see the result? And then we can compare and see how it changed. So I'm creating a new variable. I'll say DT tuned equals and call the decision tree classifier function. In order, I write the parameters determined by the grid search CV above. All right. So now that that's ready, we can run the code. And now it's time to fit the model object. So I'm calling the model and applying the fit function. I'm actually entering the train data into it. And we'll run the code. All right. So now, my friends, it's time to test. So I'm setting a new variable, and I'll say ypred equals and call the model and apply the predict function. Now I put test data inside the function and run the code. So now let's see if we can examine the accuracy values of the model just by looking at its metrics. So we'll first check the accuracy score. So as to not take a whole lot of time, I'm just going to copy and paste the above code below and run the code. So as you can see, it has changed positively. The model performance has increased. Let's have a look with cross-validation. So I'm going to go up here again and take this and I'll paste it down here. And I'm changing the model name. And now we can run the code and all right, so now we see that this is a more reliable score. I do want you to have a look at the confusion metrics and the classification report metrics, however. And you can also review the changes from the previous model from there. All right, so let's draw the tree graph again just to see the tree structure in the final model for the, well, final time. And I want to take the code from above and paste it below. And I'm just changing the model name from here. Let's run the code. All right, so check it out. That's a beautiful graph, don't you think? Of course. Okay, so we're going to wrap it up here, and I want to see you in the next lesson because it's time to learn a new algorithm. I'll see you on the other side. All right, my friends, welcome back. Now, I promised you a new algorithm, and here we go. We are going to first run the theory of the random forest algorithm, keeping with our tree themes. Anyway, we've examined the decision tree algorithm, and we actually learned the general structure, but I wonder if you noticed we've processed through a single tree. Of course you did. So now that means that we want to work with a random forest algorithm. So the random forest algorithm is one of the supervised classification algorithms. So it's used in both regression and classification problems. The algorithm aims to increase the classification value by generating more than one decision tree. Aha! Random forest algorithm is the process of choosing the highest score among many decision trees working independently. So have a look at this image. It clearly illustrates what's going on, right? As the number of trees increases, our rate of obtaining a precise result increases as well. Now, the main difference between the decision trees algorithm and the random forest algorithm is that, well, finding the root node and splitting the nodes is random. Yeah, so just as the name would suggest, right? Random forest, it creates a forest and does it randomly. All right, well, here we go. We're going to do some examples so that we can get better understanding what's going on. So let's take something from the medical sector this time. Let's say when we get sick, we go to the doctor, all right? We tell the doctor the symptoms that is maybe caused by a disease so that they can better detect our disease, right? So the doctor makes various tests according to the symptoms and asks for opinions maybe from other doctors to diagnose what's going on. And then, according to the opinions of those doctors, the results of the tests, their own experience, the disease gets diagnosed, and then, hey, you get something and you recover from the illness, whatever the recommended treatment is, right? So here, not to pass the analogy, but each doctor represents a decision tree, right? You see that? So the sick person, whether it's you or me or anybody else, learns what type of disease they have in line with a decision made by the most doctors. And then according to the result, treatment is recommended and carried out. So the random forest algorithm actually has a structure that works with this logic. Now, I want to tell you about some of the most used parameters of this model. The first would be the estimator parameter. So this is going to be the number of trees that the algorithm creates before averaging the predictions. And it probably is the most important hyperparameter because overall, a higher number of trees improves performance. It makes predictions more stable and actually slows down the computation. But another important hyperparameter is max features, which random forest can try on a single tree. And this would be the maximum number of features, right? Now, the last crucial hyperparameter here that I want to discuss here in terms of speed would be min sample leaf. And just like the name would suggest, it determines the minimum number of leaves needed to split an internal node. All right. Advantages and disadvantages? Sure. Let's talk about that, and then we can wrap it up. So a few of the advantages would be, like I mentioned before, random forests can be used for both regression and classification tasks. Random forest is also considered a handy and very easy to use algorithm because default hyperparameters usually produce a really good prediction result. Now, the number of hyperparameters is low and easy to understand. Are there any disadvantages? Well, maybe. In a random forest, many trees can make the algorithm slow way down and kind of ineffective for real-time prediction. But in general, these algorithms can be trained quickly, but they're extremely slow to generate predictions once trained. The random forest algorithm is, well, it's fast enough for most real-world applications. But there may be cases where runtime performance is crucial, essential, and other approaches might be preferred. All right? So that's a few of things to think about. But random forest algorithms get used in many, many fields like banking and stock exchange, medicine, like I said, and in e-commerce as well. For example, when used in banking, it can identify customers who will use the bank services more often than others. And this is also used to detect fraud customers who want to defraud the bank. In finance, it gets used to determine the future behavior of a stock. In healthcare, it's used to analyze a patient's medical history to identify the right combination of, well, treatments or medicines, whatever, and identifying diseases. And then in e-commerce, well, random forest gets used a lot to determine whether a customer actually likes a product or not. Okay, my friends, so that's random forest. We're going to get to practicing in Python next time. So I'll see ya on the other side. All right, my friends, hello there. Welcome back. So guess what? We're going to examine the random forest algorithm together using Python. So let's dig right in. Now, my friends, since we aim to understand the logic of creating and using the algorithm, we're going to continue with the notebook that we worked on previously. Yeah, okay, good. But what did we do? Well, by using the decision tree algorithm, we did a classification study on the iris data set. And now we're going to work on the same data set here with a random forest algorithm. All right? So as you can see, I'm here in the latest part of this notebook, and I'll open a cell in Markdown format. And here I just write random forest modeling. Now, first of all, we'll do the import process. So I'll say from sklearnensemble, and I'll import the random forest classifier function right from this module. Okay, so this is how the random forest algorithm gets imported. And since all the import operations required in modeling are done above the notebook, I don't need to import them in here again. Okay, we'll continue on creating the model object. So let's set the variable name first. I'll say rf model equals and equate it to the random forest classifier function. All right, so now, my friends, I will create the first model without setting parameters. So I want to run the code directly. And now it's time to fit the model. I'll call the model and apply the fit operation on it. And I'm writing train data in it. I'll say xtrain and ytrain. All right, let's run the code. All right, my friends, we can venture a guess now. So I'm setting a variable. I'll say ypred equals. I'll call the model and apply the predict function to it. I'll enter the test data into the function. I'll say xtest, and we can run the code. All right, so there's the guess. Let's check out the model accuracy. So I'm just going to go up here to save some time. I'm taking these two codes and paste them down here below. So I do want to change the model name. And the first code will give us the accuracy score. The other will give us cross-validation and present the accuracy to us. Yeah. So I'm going to run both codes. And there we have the scores. Now, look at this cross-validation. So it's actually been the best score that we've received so far. Ooh, you're getting an inkling of the power of the random forest algorithm. Cool. So let's get the confusion matrix codes. So I'll go up here and take these two codes and paste them down below. Let's run the codes. All right, so my friends, the first one is the pure state of the confusion matrix, and the other is its visualized version. And yeah, sure enough, the model only guessed two values incorrectly in the first tag. So let's have a look at the classification report. I'll write print classification report and enter ytest ypred. And now let's run the code. Yeah, we see the F1 score has 95% again here. So my friends, now I want to show the graph that will show how the trees look in this random forest algorithm, and then maybe we can wrap it up. All right, so I'll just take the tree graph code from above here and I'll paste it down below. I will change the model name here and just making a small change. So I'm putting a period at the end of the model and calling the estimators method. And from the values that come from here, I'll get the first value that I want to be an example. So I'll do indexing. All right, so I open square brackets and write a 0 in them. You know what that means? Well, we'll find out in a minute. See, so I'll open a cell. I'll write the model here and apply the estimators method. So now let's run the code. Okay, so we've got a total of estimators, and each of these is a tree model, my friends. They combine and form a random forest. Trees have been formed, and that's certainly a forest. Okay, so let's say if we want the first of the trees here to be visualized by taking the 0th index in the graph below. Cool. Now, anybody out there can index this a little differently and see how the other trees get formed. But I'm going to run the graphics code here and check it out. We've come across a tree structure of the first estimator. Now, sure enough, there are 50 other tree structures just like this one, and the estimates are made by taking the average of all of them. Pretty powerful though, right? All right, my friends, we're going to wrap it up here, but go ahead, go back in there and examine all the details of the different trees. You got 50 of them, or make more. Okay, we're wrapping it up. I'll see you in the next video. All right. So welcome back. Now we need to perform hyperparameter optimization on our random forest algorithm. So we're going to dive right in. I'll create a new model object. I'm specifying a variable name here. I'll say rf model2 equals and call the random forest classifier function again. Now let's run the code. And yeah, we've now got a model object. So now I want to create a dictionary to determine the parameters that we're going to try. I'll say rf params equals and open curly brackets. So with this parameter, we can actually determine the number of estimators. Okay, so I'll open the list parentheses and enter values 50, 100, and 300. All right, and we'll continue by making the max features parameter an item with 2, 4, 6, and 8 for the values. And then finally, I'll try the min sample split parameter with the values of 2, 4, and 6. All right, so these are the most used parameters in the random forest algorithm. So we're going to search for the best of these parameters with a grid search. Okay, so our dictionary's ready. Let's run the code. Now we can do our hyperparameter optimization. So first, I'll define a variable. I'll say rf CV model equals and call the grid search CV function. All right, the model name in it. Then I add the parameter dictionary. After that, I'm setting 5 CV and put the n jobs parameter 2 minus 1. Okay, so this parameter will allow the computer to focus on this process. Okay, so let's run the code. Now it's time to fit. So I'll call the variable and apply the fit function to it. I'll write the training data in it. I'll say xtrain and ytrain. Let's run the code. All right, my friends, this process may take a little while because we're actually trying 4 parameters and each has different values. And of course, we're going to try them 5 times because the CV value is 5, right? So yeah, my computer might just take a little bit to respond. I don't want you to be alarmed if yours is choking, but there you go. You can see that my process is now complete. Now let's have a look for the best parameter. So I'll call the variable and apply the best params method. And we'll run the code. All right, so as you can see, the best parameters are in front of us. But now let's create a model according to these parameters and see the result. So first I'm creating a variable, namely rftuned equals, and call the random forest classifier function. Then I'm going to write the values given by the grid search CV above into the algorithm. Now everything looks ready, so we can run the code. All right, so check it out. Now the model object's been created. It's time to fit. So I'll call the model and apply the fit function to it. And I'm writing train data in it, so I'll say xtrain and ytrain. And we can run this code now. All right, my friends, we can now test the model. So I'll say rftuned and apply the predict function to it. And I'm writing test data in it. And I'll say xtest. Let's run the code. Okay, my friends, let's have a look at the accuracy value and the other metrics. So I'll write print accuracy score and call the function. I'll write ytest and ypred in it. All right, let's run the code. Well, would you look at that, 100% accuracy? Well, we better have a look at the confusion matrix and classification report. So I'm just going to copy the codes from above and paste them down in here below. Let's rerun it. Well, check it out. That looks great. There is 100% accuracy. And boy, you really do see the power of the random forest algorithm once more, huh? I do want to mention one thing before we wrap up this lesson, though. My friends, we can identify the essential features in the data set with random forest. So the method that we need to use for this is the feature importances method. So check it out. I'm calling the model and applying the feature importances method. Okay, so let's run the code. All right, so now you can see the weights of the features appear on the screen. And what are those features? Well, I'm applying the columns method on the xtrain variable. And look, the names of the features are right here. Now, perhaps we want to strengthen this process by doing some visualization. So I'll create a variable. I'll say best feature equals and call the series function from the pandas library. I'll convert the properties and coefficients to series. After that, I will visualize this series. So I'll say rftuned.feature importances for the series values. I'll say index equals xtrain.columns for index. And finally, I'll call the sort values function to sort the values from largest to smallest. And then in it, I'll set the ascending parameter to false. All right, let's run it. And sure enough, the pandas series has been created. So let's have a look at the series now. So I'll say best features. Look at this. The features are now displayed according to their importance. I do want to visualize this output, though. So the best features variable is for the x-axis. For the y variable, I'll determine the indexes of the best features variable. So I'll go down the line and say plt.title for the title. I'll write feature importance in it. And then I can make this visualization just by saying plt.show. Let's run the code. Hey, look at this. The order of importance of the features are now displayed in a very easy to understand way. Now, my friends, we've worked obviously on a very small data set just to understand the algorithm, right? But of course, you've noticed that the number of variables in the data set is actually quite small. It's minimal. But you can see the importance of our operations in larger and multivariate data sets, yes? So feature ordering becomes more critical because we can remove the less important variables from the data set and make the model, well, just that much easier to work with, okay? So yes, indeed, my friends, we have now come to the end of yet another machine learning algorithm. Next time, we're going to learn a completely different algorithm. I'll see you then. Bye for now. All right, hello, my friends. Welcome back. Check it out. We're going to say hello to a new algorithm. Which one, though? Which one? Support vector machine. Now, my friends, it might not sound very exotic, but this algorithm is actually one of the most effective and simplest methods used in classification. So it's going to help you out. Now, for classification, it's possible to separate the two groups by drawing a boundary between two groups on a plane. So the place to remove this limit should be the farthest from the members of both groups. See, so here, SVM determines how to draw this boundary. Now, it can get complex, but it is suitable for small and medium-sized data sets. So let's have a look at this image again. You see there are two different classes in the graph. We've got blacks and we've got whites. And the primary purpose in this classification is to decide in which class the future data will take place. So to make this classification, a line separating the two classes is drawn, and the green region between +1 and -1 of this line is called margin, all right? So the wider the margin, the better the separation of the two or more classes. Naturally, this image has mathematical formula, but please, we don't need to go there. I just want you to get this as we stick to it. So the margin, okay, is drawn, and classification is made according to these mathematical formulas. You can go look them up if you want, but on your own time. So we're going to learn a couple of new concepts. These are hard margin and soft margin. Okay, so the margin may only sometimes be, well, the way we want. Sometimes observations in the data set can fall into the margin region. That's why it would be called a soft margin. But the hard margin works if our data is linearly separable and is very sensitive to outliers. So therefore, in some cases, we might actually prefer soft margins. We can control the balance between the two with a C hyperparameter in the support vector machine algorithm. The larger the C, the narrower the margin. Also, if the model overfits, we need to reduce the C. So my friends, nominal dimensions may not be sufficient to explain complex data sets. That might seem logical to you. If we increase the size, it'll take a longer time because the transactions will increase. But this is where the kernel trick statement comes into play. So we can actually make it much more meaningful by multiplying our coordinates with specific kernel functions. Yeah, so now it's time to examine the two most used methods in detail. The first one is polynomial kernel. So to solve our problem using polynomial kernel, we just move out of 2 dimensions and act like we're operating in 3 or more dimensions. We cannot classify the distribution on the left, 2 dimensions, with a straight line, right? So for this, we can use the polynomial kernel. So using this kernel, dimensions are transferred to a 3-dimensional plane. Now, when we're operating in this 3rd dimension, we use a plane instead of a straight line to classify, and we can organize it much more appropriately. So yeah, if our model is overfitting for the dimension, you're going to need to lower its rating. And if it's underfitting, you'll need to increase its degree. All right. Now, another kernel is Gaussian RBF, which stands for radial basis function. This one might be a little tricky to understand, but it definitely finds infinitely sized support vector machines calculating how similar each point is to a particular topic using a normal distribution, and then we'll classify them accordingly. Now we can control the width of the scatter with the gamma hyperparameter. The smaller the gamma, the wider the distribution. Now, just like using the C hyperparameter, if the model is overfitting, we need to decrease the gamma value. If the model is underfitting, well, we'll need to increase the gamma value. Now, my friends, this RBF kernel is generally preferred if your data set is manageable. All right? So my friends, other than these two kernels, available in kernels, you are now seeing the names of the others right here on the screen. But anybody who wants to do any more research, go ahead, go do it. For our purpose, we are going to be touching on two of the most used, okay? That's why I introduce them to you, but that's the theory. So next time we're going to practice with Python. It's going to be a lot more fun for some of you. All right? I'll see you on the other side. All right, my friends, welcome back. So I know that you want to practice the support vector machine algorithm with Python. So let's just dig right in. So most of the imports that I'm using in the notebook are already here. So I'll just run the code directly. Now let's import the data set, and we'll work with a data set that classifies red wines according to their quality. Okay, so in this context, we'll be given different characteristics of wines, and we'll evaluate the quality of the wines according to these features. Okay, so we're going to import the data set. So I'll say df equals and call the readCSV function from the pandas library. And I'm writing the data set in it. Yeah, so I'll go down here and call the head of the data set by saying df head, and let's run the code. All right, so see here, my friends, the data set is now in front of us. Let's quickly recognize the variables in the data set. So the first variable here is fixed acidity. So this property is determined by the sum of the acids contained in a sample. Volatile acidity refers to the group of low volatility organic acids, such as malic, lactic, tartaric, or citric acids, and it's actually specific to the properties of the sample. And then here we have volatile acidity right next door. The amount of acetic acid in wine can cause very high levels of an unpleasant or vinegary taste. Volatile acidity refers to the group of short-chain organic acids that can be distinguished from the sample by distillation. Formic acid, acetic acid, propionic acid, butyric acid. These are just some of them. This is not a chemistry class after all. But anyway, the following variable is citric acid. Citric acid, present in small quantities, can add freshness and flavor to wines. Citric acid is a colorless, weak organic acid. It occurs naturally in citrus fruits. In biochemistry, it's an intermediate in the citric acid cycle that occurs in the metabolism of all aerobic organisms. And we'll continue with the next up, residual sugar, which happens to be the amount of sugar remaining after fermentation has stopped, and it's measured in grams of sugar per liter, G/L. All right, so the amount of residual sugar affects the sweetness of a wine. That makes sense. Now, the next variable is chlorides. This is the amount of salt in the wine. The higher the chloride extraction during red wine making is due to ions separated from the rinds during fermentation. Okay, so now we've got free sulfur dioxide right next to it. So free sulfides are those that can react and thus exhibit both germicidal and antioxidant properties. Bound sulfides have reacted both reversibly and irreversibly with other molecules in the wine medium. So the sum of the free and bound sulfides defines the total sulfite concentration. Now, by the way, these are some very technical terms. I'm just trying to give you a sense in detail here in some, for some awareness. Like if you're working for a wine business, you need to know this stuff, right? But it's enough to know right now just what they mean. So there you go. Like I said, it's not a chemistry class. We'll continue, though, because we do have total sulfur dioxide next. And this is the amount of free and bound forms of sulfur. So at low concentrations, sulfur is primarily undetectable in wine. Simply put, total sulfur dioxide, TSO2, is the part of the sulfur that is free in wine, and the sum of these aldehydes, pigments, or sugars in the wine. So here we have the density variable next. It's the density of the wine. Okay, so we'll continue with the pH variable, and that defines how acidic or basic wine is on a scale, and most wines are typically between 3 and 4. Yeah, so next we have sulfates, and these will act as an antimicrobial in a wine additive. And now we've got alcohol right next to it. So this is the percentage of alcohol content of a wine. All right, now finally we've got our target variable. And what's that? Quality. So my friends, this output variable is based on sensory data, and it's scored between 3 and 8. So we're going to classify the wines according to their quality by looking at all the data. All right, so that's why we've learned all the different variables within this data set. So you know what I'm going to do? I'm going to just put a picture here to make this notebook look a little bit better, and I'm converting the following cell to Markdown format. And then I'll just drag and drop the image that I've prepared for this cell, and we'll run the code. All right, so look at this, my friends. It's a lot more meaningful with a visual. Okay, so I want to end our lesson here, though, and we'll pick up right where we leave off next time. See you then. All right, my friends, welcome back. So I really do want to continue right where we left off. So now we can work on it because we have loaded the data set. We will continue with EDA. So I'm just going to open a cell in Markdown format here. I'll write EDA in it, and let's run the code. Yeah, so first, we'll get to know the data set a little bit more closely. So I'll say df.info. And see this, my friends? The data set becomes more detailed. So here we can see that there are 1,599 data and 12 columns in the data set. And we've also learned that these columns mean in the previous lesson, so we just have to see that there are no null values in the variables. Okay, so that's a good thing for us. We'll be able to get all the values like we want to. All right, so one of the variables has an integer property, 11, a float, and let's have a look at the number of values in the target variable. So I'm calling the target variable from the data frame in this context, and I'll apply the value underscore counts function to it. All right, let's run that. Okay, so we can see that there are 6 values in the target variable, and all values are numeric. 5 is the most common value among the quality variable. There's a total of 681 values of 5. So the value with a least number, 3, and it's got a total number of 10. So you can see the others, right? But I will want to do a visualization. So that means I want to determine the relationship of all variables with the target variable. Now, instead of writing visualization code for all variables separately, I want to output them together using the for loop. Whoa, so how do we do this? Yeah, so first of all, I just want to get the list of all the variables except the target variable. Now, when we set up a for loop, I want it to navigate through these variables in order. Yeah, so I'll say df.columns, and this will bring us all the variables. Now, we don't want the target variable in this list, right? That's why I'm going to do slicing. Now, within this context, you see how I want to open square brackets, put a colon, write -1, and this way we're not going to get that final target variable. Yeah? Okay, let's run the code. All right, so there it is, my friends. Now we can start our visualization. So, to not take up too much time, I just want to paste the dictionaries that I've prepared beforehand here. Check it out. So we've got a couple of dictionaries, one named title font and one named axis font, and there are various items within them. So these items will regulate the shape of the text on the axis and the title when we make our visualization. Okay, so you're going to see what I mean in a minute. Now I'll continue with, I'm going to start a for loop. I'll say for and set a variable. So I say I. And here I am using the in operator, and I'm copying and pasting the code that we've got the names of the variables above. All right, so we can go down to the bottom row, And here we need to determine how the visualization ought to work. So first, let's set a chart size. So I'll say plot plt.figure, and I'll set the fig size parameter to 10 by 6. And let's go down here. Now I can create the chart. So I'm calling the bar plot function from the Seaborn library. And I'm setting the x parameter as the target variable for the x-axis. And I'll define the y-axis as I because all the variables will come here in order. Okay, so finally I can set the data parameter to df. All right, so now our image is ready. I need to determine how the text ought to look for the title and axes in the chart. So I'll say plt.title for the title. First, I'll write quality hyphen and collect it with the I variable. See, this way the target variable and the name of the variable whose image we encode will be written in the title. And I'll continue with equating the font dict parameter to the title font dictionary. And sure enough, the articles in the title will be according to the item properties in this dictionary. Yeah. Now let's go to work on the axes. I'll say plt.xlabel for the x-axis and white quality in it. And there will always be a target variable on the x-axis, right? So I'm setting the font dict parameter as the axis font. Thus, the text in the image will be shaped according to the items in the axis font dictionary that we created above. Yeah, okay. Let's continue. I'll say plot.ylabel for the y-axis, write I in it. Thus, the names of the variables will be written in order on the y-axis. Yeah. So again, I'm setting the font dict parameter as axis font. Now, there's a small operation left. Then we'll be able to have our visualization. Do you know what I'm talking about? I need to write plt.typeLayout so that the graphics aren't going to actually just be all merged together with each other, right? Just one on top. Well, you'll see. So finally, I'll just end this by saying plt.show. Now let's run the code and you'll see what I mean. All right, so here we have in order, our graphics begin to form. So you see how we can now see the relationship between the target variable and the other variables just with a single loop? Wow. All right, well, let's have a look at it in order. So let's have a look at the first image first. Now you can see a relationship between fixed acidity and quality. There's a pretty balanced distribution here. You got to notice that all the values in the target variable are almost evenly distributed. Yeah, so this means that the sum of acids in a sample is scored closely to each other in terms of quality. Now let's examine the graph below. This graph shows the relationship between volatile acidity and the target variable. And you see there's an increase in value 3 here compared to the others. Now, by the way, there are lines on the bar charts. And you see these lines show the standard deviation within the values. See, so within this context, there is high standard deviation in the number 3 value. Now, you can go ahead and examine all the other graphs just like this and interpret the relationship between the variables and the target variable in your own time. That way, your analysis ability will be greatly improved. I believe in you. Go ahead, take it from here. And we're going to continue where we leave off here in the next lesson. I just want you to be ultra familiar with what we're doing. All right. I'll see you next time. And we're back. So thank you very much for coming back. Yeah. We're going to continue right where we left off in the EDA section. Right. So within this context, we're going to use the heat map graph to see the correlation between the variables. So I want to get started with that by first determining the size of the chart. So I need to say plot.figure and set the fig size parameter 15 by 9. I'll go down and call the heat map function from the Seaborn library, and within it, I'll write df.core to visualize the correlation. And I'll set the CMap parameter to spectral to edit the image's color. All right, so I put the annote parameter to true, and I'll be able to see the correlation coefficients within the image. All right, let's run the code and check it out. There's a great heat map. So now we can see that there's a low correlation between the variables. The highest correlation between the variables is between pH and fixed acidity at minus 0.68. So now let's examine the relationship between the target variable and the other variables. Okay, so there is not a very high correlation, my friends. It has a moderate correlation of 0.48 with a maximum alcohol variable. So the variables with little correlation with the target variable are residual sugar, free sulfur dioxide, and pH variables. So yeah, I'm going to want to drop these three variables from the data set. See, that way I'll insert fewer variables into the model, and that'll boost my efficiency, reduce the cost of the model. Okay, so we'll say, I'll just make these notes and continue. Now, my friends, since our main topic is really understanding the logic of modeling and algorithms, I'm not going to give a whole lot of attention to the EDA parts, but I'm still working through it because I want to help you do analysis. All right. You got to know. Anyway, we're going to continue on, and we're going to move on to the preparation part for modeling. So I'm going to open up a cell in Markdown format here and write preparation for modeling, just like that. So let's run the code. All right, so now we can perform the drop operations according to the analysis that we've just been through using our heat map. So with this in mind, I'm just going to say df.drop and write the columns that I want to drop in a list. I'll set the axis parameter to 1 because I want to reduce it on a column by column basis. And I'll put the in place parameter to true because I want to make changes permanently. All right, let's run the code. All right, so now let's check out the new version of the data frame. I'll say df head. Well, would you look at that? My friends, let's say I want to now do a study. Did you notice the variable quality has 6 different values? So instead of classifying according to these values, I want to convert the quality into binary classification like bad and good. Okay, so we will perform this operation with a cut function from the pandas library. All right, so first of all, I'll need to specify a variable. I'll say bins equals, and now I will select a range in this variable. Now, yeah, since I want the new values to consist of 2 classes, I'll define this range just like this. I'll write 2, 6.5, and 8 in the tuple. Yeah, so the quality variable is between 2 and 6.5. The wine will classify as bad, but between 6.5 and 8, it'll be classified as good, right? Okay. Now, we can set the name of the new classes. So I'll say group names equals and write bad and good in the list. Now, of course, you can change these names, but I'm just going to stick to a simple way. And we can change the quality variable to its new format. So I'll say df quality equals and pandas. I'm calling the cut function from the library. And first, I'll write the quality from the data frame. Now I'll equalize the bins parameter to the bins tuple that we created above. And I'm also going to equalize the labels parameter to the group names list. All right. That way we've got our new values in the variable, and they will be the values in the list. So everything looks ready, doesn't it? Why don't we just run the code? So let's call the data frame again. I'll say df head. And check it out. The quality variable has taken the shape that we were wanting. Yeah. So now let's have a look at the frequency of values with a count plot. So I'm calling the count plot from Seaborn Library. I'll write df quality in it. Let's run the code. Okay, so check it out. We've got about 1,400 that are classified as bad, while more than 200 classified as good. So you see, now we can insert the data set into the model, but we're going to need to convert the target variable into a numeric format. But we can do this easily, right, with a getDummies method. But, yes, I want to teach you something new. This is cool. This will be done with the label encoder. All right, so this is actually a very helpful function that's going to allow us to convert categorical values into numbers. So without explaining any further, let's just do it. I want to perform the import process. So I'll say from sklearn.preprocessing and complete the process by saying import label encoder from within this module. Right, so let's run that code. Yeah, so now we can create a new variable. I'll say new quality equals and call the label encoder function. And now we can run the code. So now we've got an object. Let's create the quality variable again. I'll say df quality and call the object we created with the label encoder. Now I'm applying the fit transform method to it. So my friends, all values will fit this way, and then the transformation will be provided. So I'll write df quality inside the function again. And now let's run the code. Okay, let's recheck the data frame structure. And check it out. Quality is turned into the format that we want, so we can now check the values in it. I'll say df quality and call the value counts method. And let's run the code. Well, look at this. We've got 1,382 zeros and 217 ones. That means we can now move on to the modeling phase. So I need to divide the data into two, right? X and Y. And within this context, I'll say X equals and write df.drop. I'll place quality in it. So the X variable will be all but the target variable. Okay, so I'm setting the axis parameter to 1 as well. I'll create a Y variable and equate it to the target variable. Now let's run the code. All right, so now we can separate the data into training and test sets. So I'm creating 4 variables. Now we know these very well, right? So I'll say xtrain, xtest, ytrain, ytest equals, and I'll call the train test split function. So in it, I insert the X and Y data. I'm setting the test size parameter to be 0.2. Random state parameter, 42. Let's go ahead and run it. Now, we need to do one last thing before modeling, don't we? What is it? Yeah, we got to standardize the data, my friends. The support vector machine algorithm is an algorithm that requires standardization. So let me show you how to do that real quick. I just need to open a cell in Markdown format and write scaling. All right, so run the code. And here I'll define a variable named scalar and equate it to the standard scalar function. So this will create a scale object. Let's run the code. Now here, my friends, we can now apply this operation to our data. So I'll say xtrain equals and call this scalar object and apply the fit transform function. And this will directly fit and transform. So I write xtrain in it again. And then right below, I'll say xtest equals, and this time I'll apply the transform method by calling the scalar object. So I'm putting xtest data in it again. Okay. Now, let me just explain something. In scaling, usually fit transform is applied only to train data, and only the transform method is applied to test data. So you can see fit transform applied to both of them elsewhere, but that is, well, slightly different. Okay, so let's just run the code and you'll see what I'm saying. So my friends, We've got the conversion. So now we can move on to modeling, but I just looked at the clock and yeah, we better wrap it up here and we'll continue with modeling next time. All right, I'll see you on the other side. Okay, my friends, you came back, so this must be the other side. Let's just get back to it. I want to start modeling. So first I want to open a cell in Markdown format and write SVC modeling in it. 2SVC stands for Support Vector Classifier. So let's run the code, and now we can import. I'll say from sklearn, call the support vector machine algorithm by saying svm from it. Now I'm going to need to call the support vector classifier from within this algorithm. So I'll say import svc for this. Now let's run that code. All right, my friends, now we can move on to modeling. So I'll create a model object. I'll say svc model equals and call the svc function. Let's run the code. All right, now it's time to fit the model. I'll say svc model.fit and insert the train data. So I'll say xtrain and ytrain, and now let's run the code. Yeah, so the model has now been trained. We can make our predictions. So I'll say ypred equals, and I'll call the model and apply predict function. And I'll enter test data into it. So I'll say xtest. Okay, so now we can find the accuracy of the model. I want to look directly at cross-validation for this. So I'll say CV scores equals and call cross-val score variable. And in it, I'll set the estimator parameter to be SVC model. So I'll set the X parameter as Xtrain, Y parameter as Ytrain, and then I can set the CV parameter to 10. All right, so let me go to the bottom line and apply the mean function on the CV scores variable. So this way I'll be able to see the average of the model accuracies. Okay, let's run the code. Check it out, 88.9% accuracy. Well, that's an excellent result. However, we need to look for an answer to see whether we can increase this accuracy, right? Don't we? Can't just accept that first one. So let's have a look at our confusion matrix. So I'm going to use a heat map. And first I'll create a variable. I'll say CNF matrix equals and call the confusion matrix function. Now I'll write ytest and ypred. And now we can start our visualization work. Yes, indeed, my friends. I'm calling the heat map function from the Seaborn library. Now first, I'll place the above variable in it. And I'm setting the note parameter to true and the CMap parameter to the following value. And then finally, I'll set the FMT parameter as D. And this will edit the textual expressions on the image. All right, so let's just name the X and the Y axis. So for the Y axis, I can say plt.ylabel and write actual label in it. I'll scroll down and write plt.xlabel for the X axis, and I'll write predicted label inside this function. All right, so now everything looks ready. We can go ahead and run the code. And now we've got our confusion matrix. So here we've got 4 values classified as 1 instead of typically 0. So in other words, the model classified 4 values as good when the wine quality was bad, right? So again, it's classified 36 data as bad when the wine quality should be good. So we're going to need to do hyperparameter optimization to reduce the errors here, but let's have a look at the classification report metric. So I want to say print classification report. I'm putting variables ytest and ypred in it, and let's run the code. Now, look at this. We see here the F1 score metric is 88%. So now we can do our hyperparameter optimization. So I want to open a cell in Markdown format and write hyperparameter optimization with Python. So let's run that. All right, my friends, first I want to create a new model object. I'll say SVC model2 equals and call the SVC function. Let's run the code. Now I'm going to create a dictionary to set the parameters. And to save a little time, I'm just going to paste that dictionary that I created right in here. All right, so let's try these three parameters. These will be C, gamma, and kernel parameters. Now, we talked about it in theory earlier, and anybody who doesn't quite remember, you can go back and watch. We're going to run the code. All right, let's do a grid search CV. So I'm creating a new variable. I'll say SVC CV model equals and call the grid search CV function. Write the model name as the estimator in it. And I'm equating the grid parameter to the above dictionary. All right. And then finally, I can set the CV to 10. Now let's run the code. All right, so let's fit the model. I'll call the model and apply the fit function to it. I'll enter training data in it and run the code. All right, my friends, this process might take, well, kind of a long time. It's going to take some time anyway. I recommend that you just wait for it patiently. But we've still got the hourglass sign here. All right, so now the code has finished running and the training is done. Let's have a look at the best parameters. All right, so I'll say SVC CV model and apply the best params method. And let's run the code. Well, check it out, my friends. We've got our best parameters that the grid search found. So now let's create a new model using these parameters. I'm specifying a variable, so I'll say SVC tuned equals, call the SVC function, and now I'm writing the parameters according to the results from the grid search. So let's run the code. Now it's time to train the model. So I'll say SVC tuned.fit and enter the train data. And let's run that code. All right, my friends, we can now test the model. I'll say ypred equals and call the model and apply the predict function. I can put test data in it, and let's run that. All right, so now we can have a look at the model's accuracy. All right, so I'm going to go up here and paste these three codes below. Now, first, I need to change the model name, of course, and I'm running all three codes. All right, so that works. So if we examine the score from cross-validation, we see an increase of 1.5%. And when we look at the confusion matrix, there's been a decrease in the type 2 error. Well, that's something that we want. So again, we'll have a look at the classification report, and we can see the increase in the F1 score value here. All right, so you see how that works. That's pretty awesome, my friends. We've come to the end of yet another algorithm. So you know what that means? Next up, we've got something else to show you. How about unsupervised learning? Yeah, stick around. I'll see you next time. All right, my friends, thanks for coming back. Welcome. We're going to start a new chapter, and that means unsupervised learning. Yeah, so as you know, up until now, we've been doing supervised learning algorithms, and these were regression and classification algorithms. So to summarize that, we were building a machine in supervised learning from training data, right? We had training data. The machine was learning from these and creating a model out of them. We had a target variable, generally, and we called this target variable labeled data. All right, so unsupervised learning is a lot different from what we've been talking about. We do not have a target variable when we're using this machine learning form. So in unsupervised learning, the outputs are actually not included in the study. The observed units are brought together according to their similar characteristics. Unsupervised learning uses machine learning algorithms to analyze and cluster unlabeled data sets. You see, so these algorithms classify data without the need for any human intervention. So unsupervised learning models are used for three main tasks. All right, my friends, clustering, association, and dimensionality reduction. So don't worry about the terms. We're going to have a look at them in order. So let's talk about clustering. Now, my friends, clustering is a data mining technique, and it's used to group unlabeled data according to their similarities or differences. So, for example, K means clustering algorithms assign similar data points to groups where the K value represents the size and granularity of the grouping. All right. The other task would be association, and it's another unsupervised learning method that uses different rules to find relationships between variables in any given data set. Now, these methods are frequently used in market basket analysis and recommendation engines to generate customers who bought this product also bought these products, those type of suggestions. So in short, the method is also called a recommender system. Now, I did mention one more unsupervised learning task. That would be size reduction. So, size reduction is actually a learning technique used when the number of features or dimensions in a given data set is too high. So the size of this data gets reduced. So it reduces the number of data entries to a manageable size while maintaining the data integrity. Now, what about a few real-world examples so that we can clearly see the difference when we're looking at supervised and unsupervised learning algorithms? Well, supervised learning models are ideal for spam detection, sentiment analysis, weather forecasting, as well as pricing forecasting. And then on the other hand, unsupervised learning is a perfect match for recommendation engines, client personalities, and medical imaging. So there you go. There's a little bit of theory behind unsupervised learning. So we're going to wrap it up here and continue next time. We're going to get into the algorithms. All right. I'll see you then. Well, hello, my dear friends. Welcome back. So we're going to examine our first algorithm within the topic of unsupervised learning. So what would that mean? K means clustering. So my friends, clustering is the separation of data showing similar characteristics into groups in a particular data set, right? So the K means determines the number of clusters and should take this value as a parameter. That's the K value. The two most important goals are the values in the cluster should be the most similar, and the clusters should not be similar at all. All right. So the following steps need to be performed on the algorithm side to realize these particular understandings, right? So we've got to determine cluster centers. We've got to classify samples outside the center according to their distance. And we're determining new centers or shifting old centers to the new center according to the classification made. And then we can repeat steps 2 and 3 until it's stable. So when we're using this method, determining the number of K, well, that is the crux of the problem. There are actually several methods for selecting the appropriate K number. The most applied method in this regard is the elbow method. Have you come across that? Well, my friends, using the elbow method, the sum of the square of the distances of the points from the cluster center is calculated according to each K value. So according to these values, a graph is drawn for each K value. Now on the chart, the bend point where the difference between the totals starts to decrease is determined as the most appropriate K value. All right. So in which areas is this algorithm generally applied? Well, we can have a look at a few. One of the first application areas you might think about is document classification. This algorithm is often used to cluster documents into multiple categories based on the document's tags, topics, and content. Another area of use would be the determination of crime locations. The data on crime available in specific areas of a city, crime category, crime area, the relationship between the two. While this can provide some quality information on crime-prone areas in a city or region. Now, another would be player analysis. Analyzing player statistics has always been a critical element of the sports world, right? And with increasing competition, machine learning has an essential role to play here. Another well-known area would be customer segmentation. See, clustering helps marketers build their customer base, work in target areas, and segment customers based on purchase history, interests, or tracking activity. So you see, classification helps a company target specific customer clusters for particular campaigns. Another area would be insurance. So with this algorithm, you can calculate the average cost of, let's say, motor insurance policyholders and group them to identify fraud, for instance. Earthquake research applications can also be given as a really good example. So you can see the algorithm will calculate the dangerous zones by grouping the observed earthquake centers. And of course, we've got market segmentation. That's one of the most common usage areas as well. So this algorithm will allow you to group customers with similar behavior from an extensive database containing customer characteristics as well as their past purchases. All right, so there's some more theory for you of the k-means clustering algorithm. But don't worry, we're going to get started with practice next time. So come back and we'll get started. And we're back. All right, so that means we're going to practice the k-means clustering algorithm using Python. So let's just dig right in. First, we'll import the libraries that we'll use in the notebook. And we'll just run the code directly here. Okay, so now we can import the data set on which we're going to practice. So we're going to work on the arrest data set for this. This data set is the data of crimes such as assault, murder, and rape committed in the USA in 1973. We're going to do a clustering study by examining this data. Let's go ahead and upload it. I'll say df equals and call the read CSV function from the pandas library. I'll write the name of the data set in it. And bottom line, I'll call the data frame again, and I'm running the code. Now, we've got our data set, but there's a problem with the first column name, yeah? So I do want to fix this. I want the first column to be the index name. So with this in mind, I'm taking the whole code from here, copy and paste it, and I will set the index call parameter to 0. Cool. Now let's rerun the code. All right, so the data set is now in the format that we want. We can start our work. So we got to get to know the variables, don't we? The index consists of state names in the US of A. The first variable is the murder variable. This variable is the percentage of homicide per 100,000 incidents. So if you look at the first line, you can think of 13,200 out of 100,000 cases are murder. Okay, so the percentage of this situation would be 13.2, right? So this data represents a rate. So now we can look at the assault variable right next to it. This variable represents a crime of attacks committed in 100,000 incidents. Again, rated data. And we'll continue urban pop variable. This will indicate the percentage of the urban population. Okay. And now we've got the rape variable. Now, this is again proportional data of rape crimes committed in 100,000 incidents. All right, so let's get to know this data set a little bit more closely with our info method. So first I'll open up a cell in Markdown format. Right, getting to know the data set. Let's run the code. All right, so now we'll examine the data set with our info method. I'll say df.info. And check it out. This is a pretty small data set. Consists of 50 lines. There are 4 variables in total. 2 of these variables have float and 2 have integer structures. And did you notice any missing values? No. So now let's see the basic statistics with our describe method. So I'll say df.describe. And here we can see all the other statistics of the variables, such as mean and standard deviation. Now, you know what? We're not going to do any EDA work here. I want to go directly to the modeling stage. And of course, anybody who's curious about the relationship between the variables can go ahead and find it using your visualization techniques that you know and love so well. Or at least it gives you an opportunity to practice them. But we're not going to do it now. All right, but just a hint, you can come up with a visualization of the differences in crimes city by city. In any event, I would like to apply the Hopkins test before proceeding to the modeling phase. And I know I should have brought that up earlier when we were talking about theory, but just let me talk about it now while we're writing the code and you'll get what I mean. Okay, so I want to open up a cell in Markdown format and just write Hopkins test in it. Now run the code. So do you know what a Hopkins test is? Well, this test will actually allow us to investigate the clusterability of a particular data set. Yeah, so it's actually necessary to load a module. So here I will write the installation code, and if you still need to download it, please go ahead and do that. You won't be able to do this test without it. All right, so I'm not going to rerun the code because I installed it beforehand. I'll just leave it as a comment in this cell. Okay, so now I'm importing the necessary libraries. So I'll say from PyCluster end, I'll import the test by saying import Hopkins from this module. And it's important to import the scaling function. So here I'll say from sklearn.preprocessing. And I import scaling from this module just by saying import scale. Okay, so this is how we do this test. I'll call the Hopkins function, and first I'll give the data. However, I'm going to provide scaled data because the k-means algorithm is an algorithm that requires scaling. So see here, I'll write scale df. And Hopkins also wants shape from us, so I can write this directly. It was 50, right? Now, to avoid making a mistake, I'm going to call it officially. So here I'll say df shape, and I want the 0th index in it. So this will give us the row count of the data frame. All right, so yeah, let's run the code. All right, so we've got a result, and we've got an output like 0.38. So how do we interpret this, you might ask? Well, according to the document, if the Hopkins value is less than 0.5, it is unlikely to have statistically significant clusters. Right, so the score was low in this data set. However, the reason why it's low is partly due to the scarcity of data in the data set. So if I were to get such a result in larger data sets, I would think about it a little bit more. However, since our data set is small, I still want to do clustering, all right? So we're going to be covering clustering next time, but aren't you glad you know about this now? Okay, so we're going to wrap it up. I'll see you on the other side. All right, hello, my dear friends. Welcome back, because we're going to move on to modeling. So we'll get started right away. I want to open a cell in Markdown format and write k-means modeling in it. And let's run the code. So first I want to perform the import process. So within this context, I'm going to say from sklearn.cluster and complete the process by saying import k-means. So now we can start modeling. I'm creating a variable. I'll say k-means equals and call the k-means function. Now I'll specify the n-cluster parameter in it. Whoa, so we need to determine how many clusters should there be with this parameter. So we'll start with 2 first. Okay, so I'm going to say n clusters equals 2. All right, so I'm going to set the random state parameter to be 42 to get the same result every time. All right, so now it's time to fit the model. So I'll write the variable and apply the fit function to it. Here I will operate for the first time and put the data frame structure directly inside the function brackets. Now I wonder, did you notice the training and test data sets are no longer available because we're now working with unsupervised learning algorithm? Okay. This is so that we can see very clearly the difference between the two. So now the model's been trained, I need to do a visualization to see how the clustering that we've created, what it's looking like. So for this, I'm first assigning the labels created by the algorithm to a variable. I'll say cluster equals, call the model and apply the labels function. Now I'll call the variable again and check it out. The data gets classified into two clusters. Yeah, so now we can go ahead and proceed to visualize so that we can make our analysis that much better. You remember how to call the scatter plot from the matplotlib library. So first I want to write df.iloc, I-L-O-C, and now I will slice through the data frame. So yeah, I want the first column, so I'll open square brackets and put a colon and write 0. So this code will make the first column of the data frame on the x-axis. Yeah, so for the y-axis, I'll write df.iloc and open the square bracket again. And I'll put a colon and write 1. So this time the second column will be on the y-axis. All right, my friends, that's the data positioned on the graph according to the first two variables. So now I need to add a third dimension of the chart. So I'll create and equate the C parameter to the cluster's variable. You see, so the data on the chart will be colored according to the labels. And I'll continue to set the S parameter, and that'll be 75 to determine the size of the points on the graph. And finally, I can set the CMAP parameter for the colorization of the graph. And everything is ready to go. Let's run the code. Now, check it out. The classification of the two sets is right before you. Actually looks good. So now I want to do a new study and add the centers of clustering to the image. So for this, I want to detect the clustering centers. Right? So with that in mind, I can set a new variable. I'll say centroids equals, and then call the model and apply the cluster center function to it. So we'll run the code and call the variable. All right, so let's have a look at this. The data of the centers of gravity came after clustering, and here is the center of gravity data on the x and y axes according to the 4 variables. So the first list in the array represents the x-axis, while the second list represents the y-axis. Now let's add them to the graph and see where the centroids are. So first I'll take the scatter plot code above and then copy and paste it down here, and I'll create a new scatter plot. Okay, so this newly created graphic will actually overlap the previous graphic and will form a binary structure. Yeah, you'll understand that a little bit better when I create the image. So continuing on with this image, plt.scatter, and after that I slice by calling the centroid variable inside. Then I open the brackets, put a colon, and I'll say 0. And I'm writing the variable again, but this time I'm opening square brackets and putting a colon, and then I write 1. Yeah, because I want the centroid point to appear red, I'm going to set the parameter C to red. And now I want to make the size a bit larger, so that's why I'm going to set the S parameter to 250. Now finally, I want to set the transparency of the dot. So with that in mind, I want to set the alpha parameter to 0.75. All right, so you see what I'm doing. Let's run the code. All right, so what you're looking at is the center of gravity of the cluster created by the model. All right, so it clustered the two classes by calculating around their centroids. Okay, so it looks fine. But now I want to ask a question. Is the number of clustering, namely the n cluster parameter, the best value? Well, yeah, but how do we know if it's the best value or not? Well, we need to look at it with the elbow method, right? Yeah, I talked about that earlier, but now it's going to be time to do it. Okay, well, maybe not right now. Next time, all right? Let's save that for the next video. I'll see you on the other side. All right, welcome back. We're going to choose the best clustering number in this lesson using the elbow method. So, we will determine the best k value. All right? Now, I want to show you two methods. Here, first I'm going to create an empty list, and I'll say rate equals and open square brackets. So I choose a range of values for k. I'll say k equals and call the range function and write 2, 10, and I want to try the values in this range one by one. So I need to set up a for loop. I'll say for I n and write the k value here. Then I need to set up the model for each k value. So with that in mind, I'll say k-means equals and call the k-means function. And within it, I'm setting the value of n clusters to be I. All right, so now you know it's fit time. I'll call the model and apply the fit function to it. And I'll put the data frame structure inside the function bracket. Yeah, so now I will put the loss functions obtained from the models in the empty list above. But wait. What's the loss function? All right. K-means aims to find the k values that minimize the loss function, inertia. So we're going to choose the breakpoint on the elbow according to this inertia value. Follow? So with that in mind, I'll say rate.append and write k-means dot inertia. Let's check it out. So here I'm going to call it, and you're looking at the values. So let's examine these values using visualization. So here I want to say plt.plot and write k for the x-axis and rate for the y-axis. And I'll say the color of the graph, red, and let's name the x-axis. I'll say plt.xlabel and write k in it. Now we'll name the title. I'll say plt.title and write elbow in it. All right, so now that everything's ready, we can run the code. Well, check it out. That looks great. So we've got a graph. Now we need to find where the refraction is. So it would look like 3 if you notice. However, for the sake of a guarantee, we can also choose the value of k to be 4. You see? The choice is going to be up to you. But for me, I'm going to choose the best value of k as 4. And that is one way of using the elbow method. But I did mention there are two, and I want to show you the other method. Here we're going to work with the yellow brick library. Yeah, so my friends, if this library actually is not installed for you, you do need to install it first just by saying pip install. All right, so if you got it, we can continue now. So first of all, I want to create a model object. I'll say k-means yellow brick equals, and I'm calling the k-means to function. And I am creating a new variable. So I'll say graph equals and call the k-elbow classifier function. All right, so I write the model object that we created above. And then I can determine the k-value range. So I'll say k equals and write 2 and 10. Now let's fit the variable. I'll say graph.fit and write the data frame structure. Now, you see here, I'm writing graph.poof. And this way, the graph is now ready. So let's run that code. And here, my friends, I would say, not to be judgy, but certainly a more elegant visual is now in front of us, right? So here it sees the K value according to the calculations that we did. But if you look at the image, we should actually choose K to be 4. Yeah, we reached the same conclusion above, but isn't it a lot clearer here like this? Now, we can create the model according to the new K value, just like that. So I'm specifying a new variable. I'll say new K-means equals and call the K-means function. And then in it, I can set the N cluster parameter to be 4 and the random state parameter 42. Let's run the code. Now let's fit the model. So say new K-means.fit and insert the data frame structure. Let's run the code. All right, so you see that the clustering is now complete. We want to check the cluster labels. So I'm creating a new variable. I'll say labels equals and call the model and apply the labels method. Now let's run the code. Okay, so let's call the variable again. And now we have variables assigned to clusters. All right, so I actually want to add this as a new column to the data frame structure. So say df cluster ID equals and write the labels variable here. Let's run the code. Now let's call the data frame structure again. I'll say df.head. And look at that. The last column now has clustering values. Now, we're going to wrap it up here, but next time we're going to look at the silhouette and ARI score of the model using these values. So you can look it up, but I'll tell you what, I'll tell you all about it next time, all right? See you in the next video. All right, my friends, welcome back. So we're going to look at these two metrics to evaluate the model's success. I mentioned them before. What are they? Silhouette score and ARI score. So, silhouette scores are going to measure the separation distance between clusters. It displays how close each point in a cluster is to points in neighboring clusters. So this measure has the range of -1 to 1, and it's an excellent tool for visually examining cluster similarities and differences. The higher the silhouette coefficients, closer to +1, the samples of the cluster are, the further away it is from the neighboring cluster instances. Right? So a value of 0 indicates that the sample is close to the decision boundary between two neighboring clusters. Negative values indicate that these instances may have been assigned to the wrong cluster. By averaging the silhouette coefficients, we can arrive at a global silhouette score that can be used to describe the performance of the entire population with a single value. See how valuable that would be. So we're going to perform this metric in Python. And first of all, I'm just writing a header. I'm writing silhouette score in Markdown format. And now I will import. So I'll say from sklearn.metrics and end the process by saying import silhouette score. Right, so now we can look at the score, and I'll write print f silhouette score n equals 4, and I'll open up curly braces and call the silhouette score function inside. First, I'll place the data frame inside the function parenthesis, then I can place a labels variable. All right, so we've completed the process. We can run the code. And check it out, we've reached the 0.50 result. So this value is closer to 1. That's better for us. And looking at the score, well, this score is correct in the middle. So in other words, the model is neither very good nor very bad. But we understand, though, when we saw that it wouldn't be perfect clustering by using the Hopkins test. That's why I had to throw that in there. So to say close to 1, well, just means that the clusters are separated from each other very well, just like we were talking about. So according to this logic, you can see the silhouette scores that will be taken for different K values. Yeah. So now we can do a visual study to see the clustering made by the model when the K value is 4. And to save you a little time, I'll just take that graph code from above and I'll just paste it in here below. Now I'm going to have to change some values, right? And for this bottom line, I'm just changing the model names. And for the centers of gravity, I'll write the formula here. I'll change it to cluster centers. Okay, so now I can run the code. And look at this, my friends, visuals according to 4 different clusters. So we see here the parts where the centers of gravity are in red. Now, let's examine another score. What would that be? Remember, ARI? Adjusted Rand Index. So, ARI, right? Adjusted Rand Index score. So we're going to open up a cell in Markdown format and write ARI score. So let's run the code. And now I need to import this metric. So I'll say from sklearn.metrics.cluster, and I'll end the process by saying import adjusted RAND score. Yeah, so this score, when external data comes to the model, it is the score value given by the model according to the clustering. So I want to do an example here. We'll take an example from the data frame, and let's learn the working logic of the score together. So I'm creating a new variable. I'll say new df equals and typing df.sample, and I get 15 samples from the data frame. Now I'll also set the random state parameter to 42 because I always want to get the same result. And let's go ahead and call it the new data frame structure. All right, so my friends, will add a new column to this data frame structure. And this will be a column showing which cluster the data should be in. And I'm just going to paste this right in here to save some time, and we can run the code. Now let's call the data frame again. So here, the cluster ID is the name of the labels after the model clusters according to the data, and the actual label is the name that the labels should be. All right, so now we can move on to the metric. And, well, first of all, the adjusted RAND score, I call the metric, and I'll put the labels determined by the model. Then I place the tags. Okay, so let's just run the code. Oh, look at this. It's calculated 0.21. And that's a bad result, don't you think? Right? ARI ranges from -1 to 1. So the closer the ARI value is to 1, the better the model is. Right? So when it gets closer to -1, it means that performance of the model deteriorates. So we got this result using artificial data right now. I mean, that's why, who cares if it's low? Here, the aim was how to use and interpret ARI scores. All right. So in other words, yeah, we need to wrap it up here. This is the end of yet another algorithm lesson. So I want to show you a new algorithm in the next one. All right. See you then. Bye for now. Well, hello, my dear friends. Welcome back. I'm glad you came back because this is the hierarchical clustering algorithm theory lesson. So in this lesson, we're going to learn about the theory that's all behind this hierarchical clustering algorithm. So let's get started. So hierarchical clustering, it's another unsupervised machine learning method that you can use to predict subgroups based on the difference between data points and their nearest neighbors. So each data point is linked to its nearest neighbor based on the distance matrix you choose. Now, I know it might be a little confusing, but consider this analogy. Just imagine for a second that you are a geneticist and you want to identify functional gene groups by analyzing gene expression profiles, or profiles that identify all genes active in a cell. Now, you decide to apply hierarchical clustering to identify these groups based on the distance between data points in the gene expression profile and their closest neighbors. Data points that are most similar are clustered into the same genetic functional group. Okay? So hierarchical clustering predicts subgroups within data by finding the distance between each data point and its nearest neighbor. Also, by linking up the most nearby neighbor. So in other words, you can find the number of subgroups suitable for a hierarchical clustering model by looking at a, wait for it, dendrogram. So a dendrogram is a tree graph. It's useful for visually viewing taxonomies, origins, and relatedness. Okay? So a few popular use cases for hierarchical clustering include hospital resource management, business process management, customer segmentation analysis, social network analysis, many uses. You're going to like this. So for the hierarchical clustering model, you'll need to tell the model how many centroids to use. So you can look at the dendrogram to find it. So I'll show you how to use a dendrogram. So imagine that you only want a maximum distance between a point and its nearest neighbor. You want this maximum distance to be 10. Well, first, you set what kind of dendrogram you want to draw. Then you set up a line where y is equal to 10. Then you look at each point along this line where your dendrogram intersects the y equals 10 line. So if you have 1, 2, 3, 4, 5, if you want a maximum distance of 10 between each point and its nearest neighbor, you have 5 cluster centers. You could also set the maximum distance between points to be 30. And in that case, you would have 2 cluster centers. You follow? So this is what we will do in our coding demonstration. But before we get into that, I do want to tell you about these important model parameters. So you're going to have set parameters for distance metrics and linkage parameters. Distance measurements can be set to Euclidean, Manhattan, or cosine, and the link parameters Ward, complementary, or an average. So you basically try every possible combination of parameter settings with hierarchical clustering. And the model that gives the most accurate results is the model that you want to go with. All right, my friends, so that's the theory behind hierarchical clustering algorithms. So we'll end this lesson here, and then in the next lesson, we'll do some Python exercises, and we'll have a lot of fun. So I'll see you in the next lesson. All right, well, we're back. So that means you want to learn yet another algorithm. So here we go. We're going to practice the hierarchical clustering algorithm with Python. Let's get into it. I need to import necessary libraries, and I've already prepared these, so I'm just running it directly. Now see here, there's an import that you will need to pay attention to. You got to see the make blobs module. Okay, so we will generate a synthetic data set using this module, and we're going to work on it. And that way you'll learn how to produce a synthetic data set. Okay, so now I want to write a new title. I'm converting the cell to Markdown format, and I'm creating a synthetic data set in it. And we can now create the data set. So I'm creating a variable. I'll say example data equals and call the makeBlobs function. And I will enter some parameters into it. So what am I going to do? I'm going to first write the nSamples parameter. And this parameter refers to the number of data that we will generate in the data set. For example, I'm typing equals 300. All right. So yeah, now let's just set the size. So I want to create 2D data. That's why I'm putting the parameter nFeatures equal to 2. So now I'll need to determine the centers of our synthetic data. Now with that in mind, I'll set the centers parameter to be 3. And yeah, the data is going to be scattered, but generally there will be data collected in 3 different centers. So now let's determine the standard deviations of these data within themselves. So with that in mind, I'll say cluster std equals, and we'll set this parameter to 1.3. That ought to work. Of course, you can choose any value between 1 and 2, but whatever. So finally, I'm going to set the random state parameter to 42. That way, we'll always get the same result. Okay, so let's run the code. And now let's call the data set. So I'll say example data. All right, so it's here in the form of an array. And we've got 2 structures here. The first structure shows the data in 2 dimensions, while the other shows how the clustering is done. Now, see here, since we have created a 3-center data set, there are values of 0, 1, and 2. All right, you ready to go? We're going to process the first structure. So in other words, we will use the x and y coordinates of the values in the data set. All right, so that means I will index and get the first piece in the data set. So for that, I need to create a new variable. I'll say dots equals and get the 0th index from the data set. So the first structure will be in the dots variable. Let's run the code. Yeah, so we can call it the variable. And look at this. We now have the structure we want. That's quick. So now we can do a hierarchical cluster analysis using a dendrogram. You remember what that is, right? Dendrograms are the most effective visualization tool used in hierarchical cluster analysis. I'll show you. So the dendrogram enables the results obtained by the hierarchical clustering method to be easily understood. So you'll see. I'll first import by saying import scipy.cluster.hierarchy, okay, scipy. Then I'll say as sch, because I want to call it with an abbreviation, right? So when we say sch, we have to understand that we're calling the hierarchy module. Right, so let's run the code. Now we can go ahead with the creation of the dendrogram. So I need to create it in a variable. So I'll say dendrogram example equals, now let's call the function. So I'm typing sch.dendrogram. I'll enter the dendrogram properties inside the function by first writing sch.linkage. Yeah, I always want to use word value from linkage methods. Yeah, the wards method is what that's from. It's basically a method that will minimize the loss of information associated with each grouping and measure this loss in an easily interpreted way. So ward will define information loss as the sum of squares of error. The method does not combine groups with the smallest distance, but structures that do not increase a certain measure of heterogeneity too much, those with a minimum variance value, right? You follow? The purpose of the ward method is to combine the structures so that the diversity within these structures doesn't increase too much. That's all. it creates structures and clusters that are as homogeneous as possible. Okay, so that's that. Let's just do the applications. I'm putting the piece that we got from the above data set. I'll say dots. And I'm setting the method parameter to be ward. That's why that. Okay, so are you ready? Let's run the code. All right, so the code runs. And yeah, it sometimes takes a long time to run. But here you see, my friends, a dendrogram is formed. Now the distance between the clusters is seen on the y-axis of the produced dendrogram. So on the x-axis, there are the ID label numbers of the data points that form the clusters. And as you can see, this lower border crosses 3 vertical columns. So it says that there are 3 sets representing our data set. So now why don't we create a scatter plot to see the clusters in the data set? So for this, I need to first determine the chart size by saying plt.figure, set the fig size parameter is 10 by 7, and we can then draw the graph. So I'll say plot.scatter. Now I want to enter the x-axis data in it, and I'll need to write the entire first line from the dots variable. Okay, so I'll write the second line on the y-axis. I'll type dots in this context and open square brackets, and I'll put a colon and write 1. So I'm doing indexing here, right? I'll say plt.show, and let's run the code. All right, so there you go. There's a scatter plot of that synthetic data, and the 3 centers are visible. Now, when we examine them with our dendrogram, we can see the positions of clusters. Yeah? Check it out. Now, we're going to wrap it up here, but we're going to do a new study in the next lesson. So that's when we will create a hierarchical clustering model, which I know I promised you before. Okay? So we're going to wrap it up here. I'll see you next time. Bye for now. All right. Hello, my dear friends. Welcome back. I know I promised you a hierarchical clustering model, and we're going to do it. All right? So we're going to try to cluster the data that we created artificially. So let's get started. So we need to first import the library. I'll say from sklearn.cluster. Now it's time to import the algorithm from this module. So I'll say import agglomerative clustering. Now let's run the code. So here I'm creating a new variable. I'll say hierarchical clustering equals and call the agglomerative clustering function. Right, so first I'm going to determine the number of clusters within this function. So let's do something a little different. Let's ask it to create 5 different clusters. So I'll set the n clusters parameter to be 5. Then I'm going to set the affinity parameter as Euclidean and the linkage parameter as, you guessed it, ward. Now the affinity metric is used when we're calculating the distance between samples. Okay, so we'll run the code. And now it's time to fit and make our prediction. So I'm writing a new variable. I'll say y higher plus equals, and write the model that we created above, hierarchical clustering. Okay, so I will apply the fit predict function on this object. Yeah, so this function will first fit the model and then generate the prediction output. So I can now finally place the synthetic data set inside the function brackets. Run the code. All right, my friends, let's have a look at the estimate. So I'll say y higher plus. Now you're having a look at the predictions of the algorithm. Now, since we wanted a total of 5 clusters, it made 5 different estimates, right? So why don't we do a visualization? So here I'm going to use a scatter plot. So I will first determine the size of the graph, and I'll say plt.figure and set the fig size parameter 10 by 7. All right, so now we will write a different code for each cluster. Yeah, so we'll start with the first set. And I'll specify the X and Y axes in the plt.scatter. I'll say dots for the X axis and do conditional indexing. And I say Y higher plus equals 0 by 0. Yeah, so see, I'll get the first index of data that is 0 in clustering. I'm also going to do something like this in the Y-axis. So to save a little time, I'm taking this code and paste it. And I'll need to change the index to 1. And you see, we have obtained the first index of the data clustered as 0 here. So moving along, I'll say S equals 150 for the size in the image and C equals blue for the color. And now we've got the image of the first set. Now, since there will be 5 clusters in total, we'll need to do some visual work in the same way 4 more times. So without taking up too much time, I'm just going to copy and paste 4 times, bada boom, bada bing. But I will need to change the code slightly. For the data clustered as 1, well, I'll make this part of code 1 and change the color to yellow. And for clustered data number 2, I'll make this part of the code 2 and change the color to red. And for clustered data number 3, I'll make this part of code 3 and change the color to cyan. And then we've got clustered data number 4, and this part of the code 4 is changed to the color black. All right, so all the cluster visualization work is done. So I'll enter the code block's end and type plt.show. Are you ready to run the code? Well, look at that. Looks pretty good, if I do say so myself. So we wanted, most importantly, 5 different clusters. The algorithm looked at the data and did its clustering based on distances, right? So the algorithm clustered the data in 5 different ways. Now, yeah, the data with the same color belongs to the same cluster. Now, I do want to draw your attention to something here, my friends. I wonder if you notice, since we first created synthetic data with 3 centers, the data was divided into 3 centers. But then we told the algorithm that we wanted 5 different clusters. So the algorithm also did clustering accordingly. You see that? So some colors appear to be very close to each other, but this is the way to make an excellent clustering, my friends. All right, just remember that we've been using synthetic data, but now you know how to make synthetic data as well. Okay, well, we need to wrap it up here. I want you to go ahead and on your own apply hierarchical clustering algorithms to real data, and you'll see the benefit. All right, see you next time. All right, hello, my friends. Welcome back. I want to introduce you to a new concept. What is that, you might ask? Principal component analysis, PCA. Yeah, so my friends, PCA is a proper statistical technique used in recognition, classification, and image compression. So in fact, PCA is a technique whose primary purpose is to keep the data set with the highest variance in high-dimensional data, but to provide dimension reduction at the same time. Yeah, so finding available features in overdimensional data reduces the number of dimensions and compresses the data. Some features will inevitably be lost with size reduction, but the intent is here that these disappearing traits contain very little information about the population. So this method actually brings together highly correlated variables. It creates a smaller number of artificial variable sets called principal components, and these are the ones that make the most variation in the data. All right, so PCA is actually a very effective method of revealing necessary data information. The basic logic behind PCA is to show multidimensional data with fewer variables by capturing the essential features. Okay? So now why don't we have a look at why we would possibly need the PCA algorithm by creating a very good example. So, in cases where the size of a data set is very large, for example, 10 rows or 150 features, the training process is going to take a long time. Perhaps training processes that take so long actually might have too much influence on the model scores. But really, why would that be? Well, like I just mentioned, some features may be correlated with each other or similarly provide information. So it can actually be difficult for us as data scientists to handle this situation just one by one. Therefore, don't you really wish there was an algorithm that would give to us back our multidimensional data by reducing its size with very little data loss? So that's exactly what PCA does. Because it's impossible to visualize multidimensional data and then analyze these images in a meaningful way. That's why PCA is also used for data visualization. So let's get started with some of the details of this analysis called PCA. So my friends, how would we go about reducing the data from a large to a smaller size? All right, well, first off, you got to imagine that we've reduced the data shown on the left side of the screen down to one size. Should we prefer the one with a purple axis or the green axis like this shown on the right? Well, it might be healthier for us both to choose a single dimension, like with the green axis. But why would that be? Well, because of data, the green axis representation also provides a more dispersed and better presentation. So that's an intro to the logic and the theory. I'm going to spare you a detailed explanation of the math behind the algorithm. But those who are curious, that's great. I applaud you. You can go ahead and research that on your own time. But for us, for now, it's enough to just know how to use the algorithm in the next few lessons. All right, so my friends, let's talk about the parameters that we can use in the PCA algorithm. So we'll first examine the components parameter. The principal axis in the feature space represents the maximum variance directions in the data. The number of components can be entered while the algorithm is set up. And another parameter is the explained variance parameter. So it describes the amount of variance explained by each of the selected components. Now moving on to the explained variance ratio parameter. Yeah, it's a mouthful, but it represents the percentage of variance explained by each of the selected components. Now, for one of the most used parameters, the n components parameter, this is going to help us determine the estimated number of components. And the last parameter that we might need here to examine is the n features parameter. So this is just the number of features in the training set. Yeah. All right, so that's pretty much that. But the primary purpose of just running through the explanation here, just to give you some awareness about these parameters of PCA. You're going to understand how to use them a lot more clearly when you practice in Python. So, we do need to cover a few critical questions about PCA first. A common question that comes up is PCA a feature selection technique? Well, that would be a good question, my friends, because PCA detects linear combinations of features, creates different features, and enables us to represent the data in another way. So it actually is not a feature selection technique. Now, let's take another question. You in the back there, why is scaling of data necessary in PCA? Well, that's a good question, too. You should be sitting up here closer to the front. Yeah. I want to tell you that scaling is essential because of the way PCA is calculated. So it's computed by singular value decomposition. And this finds the linear subspaces that best represent the data in a squared sense. Okay, so if one variable is on a different scale than another, that's going to create some problems, right? So basically, we will scale the data before inserting it into the PCA algorithm. Sorry, what's that? Another question? Yeah. Is the PCA algorithm used in large data sets? Well, that's another good question. Thanks for asking it. The PCA object is handy, but it certainly has limitations for much larger data sets. The most significant limitation is that all data processed in PCA must fit in the main memory. Okay, so that's enough questions for now. Save the rest for the end of class. But my friends, I want to talk about the PCA algorithm's advantages and disadvantages before I let you go. All right, so as always, we start with advantages. So PCA removes correlated columns and improves algorithm performance. With multidimensional data, the model may run very slowly, so model performance increases with PCA. And sure enough, PCA reduces overfitting. One of its most essential advantages is in its visualization power. But that does leave us with a few disadvantages, my friends. Because with PCA, the independent variables become less interpretable. Yeah, because after applying PCA to the data set, your original features are going to turn into fundamental components, right? Now, key components are linear combinations of our original features, but key components are less readable and less interpretable than the original features. Now, a distinct disadvantage is the size reduction. There is going to be some loss of information compared to the original data. All right? Keep that in mind, and we're going to wrap it up here. But next time, we're going to practice in Python. I'll see you then. Bye for now. Well, hello, my dear friends. Welcome back. So yeah, we're going to do principal component analysis with Python. So first up, I need to run the code of imports that we'll use most frequently. All right, so now we can get to know the data set that we're working on. So I'm going to open a cell in Markdown format here and write getting to know the data set. So run the code. All right, so now we can import the data set. Now in this notebook, we will work with the digits data set built in the Seaborn library. So I want to load up the data set first, and then we'll talk about some of the details. Now, I do want to perform another import operation to load the data set. I'll say from sklearn.datasets and complete the process just by saying import load digits. Now I'm creating a new variable. I'll say digits equals and call the load digits function. Let's run the code. And sure enough, my dear friends, there we have a data set loaded. Okay, so the properties of this data set come in the form of arrays, and we'll need to convert this data into a data frame structure. So let me just explain first what we're going to do. Now, see, for example, I want to call the data part digits. And as you can see, it's an array, and the values of the variables in the data set are in here. So I'll say digits target. And yeah, see, the data of the target variable in digits is protected in a separate place. So we'll continue. Again, I'll say digits feature names. And check it out. The names of the variables are kept separately as data. Now we'll convert the digits data set to data frame format using this data, and give complete information about the data set after converting it. Okay, so in this context, we're going to first make the data frame. df data equals, I'll say, and I'll call the data frame function from the pandas library, and I'm importing the data that I want by typing in digits data. Then I'll set the columns parameter to the value of digits feature names. Okay, so the variable names will match the variable data. Now, you see the data frame is ready to run the code. Let's check the data frame. I'll say df data head. Okay, so look at this. All the variables have been converted to data frame format. So we can now look at the shape of the data set. I'll say df data.shape. Well, would you look at this? There's a data set consisting of 1,797 rows and 64 columns. Now, what's the story of this data set? Well, I can first add an image here. I'll open a cell in Markdown format and drag and drop the image that I've prepared before. So let's run the code. All right, so now we've got an image. All right, my friends, so this data set consists of 1,797 8x8 images. You see that? Each picture is a handwritten number, as shown below. Now, to use an 8x8 figure like this, we'll first need to convert it to a feature vector of 64 units, right? So 64 variables in the data frame represent these features. Now, you can use this data set with both classification and clustering algorithms. You should also add target data to this data frame structure if you operate within supervised learning. I'm not including target data because we're just using it for clustering right now, but go ahead, play with it. So, what's the kind of logic that we're talking about here? How are we applying the PCA algorithm to this data frame? So you noticed, of course, there are 64 columns in total. If we put all of this into the machine learning algorithm, that's going to come at a tremendous cost, don't you think? So I'm just going to transform the data here into components using PCA. Thus, the variables will be compressed within the components and will make fewer data to be included into the model. Well, that's the goal anyway. You think we can do it? Well, now that we know the data set, we'll wrap it up here and get to that next. Well, how do, my friends? Welcome back, right? So we're at the preparation stage for PCA, and let's get to it. So first, I'll open up a cell in Markdown format and write preparing for PCA, and we can run the code. Now, my friends, we do need standardization before putting the data into the PCA algorithm. So for this reason, I am importing the relevant code. I'll say from sklearn.preprocessing. Finish the process by saying import standard scalar. Let's run that code. Now I'll create a standardization object. I'll say scalar equals and call the standard scalar function. Then I'll create a new variable. I'll say scaled data equals and call the scalar object. And yeah, here I'm implementing the fit transform function on it. So the object will be trained first and then transformed. All right, and then after that, I'm putting the data frame structure inside the function. All right, so let's run that code. Yeah, my friends, our data is now standardized. So we will need to convert this new data into a data frame structure because the scale data comes in an array format. That's not a problem though, is it? I'll say df new equals and call the data frame function from the pandas library. Then I'll put the scale data in it, and then I'll set the columns parameter to the value of digits feature names. And we can run that code and call the data frame structure again. So say df new dot head. And now you see our data. Okay. So we can now actually switch to the PCA algorithm. But you know what? I'm going to save it for next time. I'll wrap it up here and see you in the next video. All right. Hello, my dear friends. Welcome back. So we are going to perform the PCA algorithm. Are you ready? Yeah. Let's not waste any more time. First, I'll open up a cell in Markdown format, and I'll write PCA with two components. Now, did you notice we'll create a two-component PCA first? So we'll continue. I'm importing the library. I'll say from sklearn.decomposition and complete the process by saying import PCA. Now let's run the code. Yeah, so now I'll create a PCA object. I'll say PCA equals and call the PCA function. Now, at first, we want a two-component PCA. So I'll set the nComponents parameter equal to 2. All right, run the code. Great. So now it's time to fit and transform this object. So I'm creating a new variable in this scope. I'll say df PCA equals PCA. I'm applying the fit transform function to it. I'm adding the data frame structure inside the function, and I'll say df new. All right, let's run the code. All right, so we've created the components with PCA. Let's have a look at the shape of the new data. So I'll say df PCA.shape, and check it out. The conversion is made, and we now have 1,797 rows and 2 columns. Now, you remember, right? There were 64 rows before. And now the number of columns is 2. So let's see how to use these components. So I'll create a new data frame. I'll say component df equals and call the data frame function from Pandas library. Now in it, I'm going to equate the data parameter to the df PCA data that we created above. And since there will be 2 components, I'll name the columns parameter as follows. First component, second component. Yeah. So the data frame structure is now ready. I'll call the data frame by saying component df. And check it out. The data consisting of 64 columns has been converted into 2 components, okay, in total. There, that's cool. So you can see the components on the screen. Now, it might be a little confusing, but I'm going to do a little repetition and you'll see what I mean. So I'm going to the first version of the data frame. Now, as you can see, there are a total of 64 rows. We can reduce this row to the number of components that we want with PCA. So we first converted it to 2 components. Yeah, we did, but how much efficiency can we actually get from the 2 components? Well, remember we talked about various functions and parameters while examining them in theory? Well, now we'll be able to satisfy our curiosity by using those parameters, right? So we're going to first apply the explained variance method. Remember, the explained variance parameter explains the amount of variance explained by each of the selected components. So let's have a look at the value. So yeah, I'm going to call the model object and apply the explained variance method. Run the code. And look at this, my friends. The variance amounts explained respectively with 2 components are now on the screen. Now let's say that we want to see these proportionally. Well, the method that we'll use for that is the explained variance ratio method. So this method represents the percentage of variance explained by each of the selected components. So I'm calling the model object and applying the method. Let's now run the code. And now we've got the rates. So each value represents the ratio of a component. Now, can we see the percentage of variance explained collectively? Yes, of course we can. If we add these 2 values cumulatively, we can get an aggregated value. So I want to use here the cumulative sum method in the NumPy library for this. Let's do it right now. I'll say np.comSum, and then I'll take the code above and paste it into the function below. So let's run the code. And now the last value gives us the aggregated result. Okay, so the total variance explained with the 2 components is 21%. So there's one last thing to do before we wrap it up. I want to make the number of components 4. So for this, I'll open a cell in Markdown format and write PCA with 4 components in it. Let's run that. Now I'm going to create a new variable. I'll say PCA new equals and call the PCA function. And in it, I can set the end components parameter to 4. And let's run the code. Now let's fit transform the object according to this number of components. And I'm creating a new variable for it. I'll say df new equals and call the PCA object and apply the fit transform method to it. And here I'm placing the data frame structure inside the function, and I can run the code. So my friends, let's have a look at the components, right? So I've copied the data frame structure above and pasted it down here to save some time. And here I'm changing the model name, and I add 2 more column names to the column names because now it's going to be a 4-column data frame. Yeah. So now everything's ready. Let's run it. Okay, so as you can see, that PCA structure with 4 components is now here. We have a data frame totaling 1,796 rows and 4 columns. Well, let's have a look at the variance amounts explained by each of these components. So I'm taking these 3 codes from above and copy and paste it below. And here I'm just renaming the PCA object. All right. Let's run that. And look at this, my friends. The first code shows the variance explained by all components. The second represents the ratios of these variance amounts. And the third means the cumulative sums of these ratios. Yeah, so you see 4 components in total explain a 36% variance. All right, my friends, we got to wrap it up here. I'll see you next time. All right, my friends, welcome back. Because now I want to introduce you to the recommender system. And now, my friends, since this topic is kind of a separate field on its own, if we wanted to practice Python, we'd need to create a whole other course for it. So that's why I'm just going to take you through the theory. All right. So within this context, I just added this course into the curriculum to raise awareness about the recommender system and to show you the general logic. Okay. So let's just get to it. All right. So recommender systems, they've become increasingly popular. It started to be used in many different areas, from products found on e-commerce sites to the music industry. So most e-commerce sites, including Netflix, Amazon, of course, and Alibaba, use recommendation systems to provide customers personalized service with their favorite products, right? So if we were to just say that 35% of Amazon's revenue comes from their recommendation engine, well, you could see very quickly that recommendation systems are something to get into, right? So what's the technical definition of recommender systems? Well, recommendation systems and personalized algorithms are frequently encountered in our daily lives and have incredible benefits for data scientists. Now, we can understand from the name that recommender systems will allow the application to make personalized suggestions. The product that might be of interest to users based on their previous preferences, this would be a system that offers content such as a service or certain information, but aims to keep their interest at the maximum level, right? So basically, recommendation systems anticipate the future preferences of the user and reveal them. Now, why would this system be so important? Well, you know why, my friends. One of the most important reasons we need recommender systems is that there are too many options in front of people due to the amount of inventory that the World Wide Web has for us in modern society. Just for an example, look at YouTube. There's an enormous amount of video content, right? Don't even want to get into those stats. But you see where the recommender system would come into play. Now, just like that, the system filters according to the user's wishes and then brings these requests right in front of the user. So yeah, we can look at the data of companies that implement this type of method to understand the system's importance just a little bit better. Right, so here's some hard facts. According to McKinsey, which analyzes the economic policies and decisions of the public and private sectors. They prepare reports for this direction and provide management consultancy services, in fact. But according to them, 75% of what people watch on Netflix is due to recommendations. Now, in 2016, at the Global Shopping Festival in China, Alibaba increased the conversion rate by 20% using personalized pages. And now, again, according to McKinsey, 35% of sales on Amazon come from recommendation systems. You thought I just made that number up. But another example, recommendation systems are responsible for 70% of video watch times on YouTube. But here we go. Here's another big example. Using the recommender system makes Netflix a profit of about $1 billion every year. Now, that might be a considerable amount of money to some people, a drop in the bucket for others. But anyway, you now understand how important this system actually is. So we'll examine the technical infrastructure of the recommender system in a little bit more detail. All right? So obviously, there's going to be more than one type of recommender system. We're going to have a look at a few of them. There are basically 4 popular types of the recommendation system. All right, so there are popularity-based recommender systems, collaborative filtering systems, content-based filtering systems, and we've got a hybrid system as well. Now, we're going to get into the details of these types in the next lesson, so I hope to see you there, because right now, it's bye-bye. All right, my friends, here we are, and it's time to get into this, examining the most preferred types of recommendation systems in order. All right, you ready? So we're going to first examine the popularity-based recommender systems type. So this system is probably the simplest among any of the others. It can actually be done with very little data. So it's recommended to the user what is popular at the moment. You've seen the trending topic or whatever. It could be a book, a movie, product, whatever. All that needs to be done is to have a look at sales figures, for instance. This filtering can be applied by categorizing them as bestsellers. It can be improved if there's some data about the user, although it could be more personalized. But here's the general logic. If we know which type of products the customer would prefer, we could obviously present the most popular of them. Now, we'll examine another type of recommendation system. That would be collaborative filtering systems. Now, this method focuses on the behavior of users. So let's say, for an example, that user A likes Harry Potter, The Lord of the Rings, and Spider-Man movies. User B likes Harry Potter, Lord of the Rings, but Batman. You see, so based on this information, we can say that A and B are these users. They have similar tastes, but it means that user A will most likely like Batman, and user B will most likely like Spider-Man. You see? So there you go. It's pretty simple. Now, one of the distinct disadvantages of this type of suggestion system, if no one has bought or left any feedback on a product, it's not going to be recommended. All right, so we'll continue with another type of recommendation system. What would that be? Content-based filtering systems. So you might guess what that is, right? So it's based on the content of the products preferred by the user. It works on the basic principle that if the user liked a product in the past, they're going to like it again. Products similar to the favorite product are selected and recommended to the user. But this method also comes along with some disadvantages. For example, one of them would be that different types of products will not be offered to the user. So as a result, even if the user likes that genre, they wouldn't be able to try other types of products. So, for example, if the user only watches videos with the category science on YouTube, well, the videos to be recommended in the future wouldn't be in any other type but science, you see. So my friends, as you can see, collaborative and content-based filtering system have both advantages and disadvantages. So that's why, to eliminate some of those and make more consistent suggestions, perhaps more actionable suggestions, hybrid recommendation systems are now widely preferred today. So let's have a look at hybrid systems. The hybrid recommendation systems are comprised of collaborative and content-based filtering systems. So in this way, the problems that would occur using methods alone are eliminated and more accurate results can be obtained. Now, of course, this system is going to require a lot of data. However, it also becomes the most suitable option, you see. So my friends, now you know what these recommender systems are and how they work. Well, at least you're aware of them anyway. If you do want to study some more details of that field, and listen, a lot of them were done with coding, you're going to be interested in courses that examine recommender systems alone. So I'll leave that with you, and I want to see you next time because, as always, there's more great stuff to learn. And I hope you have a lot of fun doing it.